have from f of x times x into f of x a morphism in the category C prime, namely f of pi. Now, if we have this isomorphism here, then taking the composition of the inverse isomorphism together with this composition with this f of pi, we get a morphism on fx times fx into fx. We get a composition on fx. So, provided f commutes with formation of the product x times x, which in order to define this, to get a meaning to the sentence, we have to assume already that x times x belongs to C. We see that the composition law on x defines the composition law on f of x. And then we see that provided f commutes also with threefold products, and using the diagrammatic expression of associativity, we see that if the composition law pi is associative, then the corresponding law on fx is also associative. And assuming that f commutes with forming final object of C, that f transforms the final object of C into final object of C prime. Then the existence of a two-sided unit for the composition law given on x implies the existence of the two-sided unit for the composition law given corresponding composition on f of x. And the same for a statement, for unlabelled statement rather, for a passage to inverses. If the composition law admits for inverses, assuming, let's say, that it turns x into a group object, then the corresponding composition law on f of x will turn f of x into a group object. However, once we grant this fact, I think, which is easily granted, then we have a functor that commutes with all the kind of inverse limits, mostly products, that occur in expressing the axioms of a particular algebraic structure, that f commutes to these particular finite inverse limits, that then f will transform a structure of this type in C into a structure of the corresponding type in C prime. Well, I mean, that's something that is pretty understandable, so we have explained it. In the case of a group, it's true for rings, for modules over rings, for objects on which group operate, etc. Well, I think then the diagrams have, for most situations, performed their function, and one can forget about the diagrams and recall the definition of an object with a composition law in terms of the initial description by, for instance, structure on the x of C's. Alright, now these explanations were longer than I expected them to be, so we won't have too many time left for giving examples. Of course, we are now interested in algebraic groups. So we have to state first what is the category we are working in. So as at the beginning of this afternoon, we fixed a cumulative ring. And we will denote by C the category of what we call affine algebraic spaces over K. This category was contained as a full subcategory by definition in the category of all functors going from K algebras to the category of sets. And in fact, it was exactly the category of representable functors going from K algebras to sets. That means if the category of K algebras is denoted by C lower K, this category here is equivalent to the category opposite to CK, and the inclusion of this category by the fully faithful functor in here, in the category of functors, is just the one I have erased that we wrote down, which allows us to embed here not any category into a category of contrarian functors, but the opposite category of any category into a category of covariant functors. That was the second setup I explained. So the category we are working in with will be the category of affine algebraic spaces over K, and later we will identify this up to equivalence with the category of so-called affine schemes over K. But it doesn't make a difference. What is really important is that we fix the category C up to equivalence, that we say in which category we are going to work. And you can view of this category, you can think of this category as being the category of opposite to the category of K algebras, not necessarily of finite type over K. And we are interested in group objects of this category CK naught. That's what we would call co-group objects in the opposite category, which is the category of K algebras. So, an object, let's give another name of this to this. So C would be the category of affine algebraic space to K, that's all right. So if X is an affine algebraic space, then to give X is essentially equivalent with giving an algebra A over K and by associated level algebra, the affine algebraic space VA represented by A. So X of K prime, if K prime is an arbitrary variable algebra, this K prime plays the part of our Z. X of K prime is equal to 1 of K algebras of A into K prime. Now, what is, if you have such an algebraic space, what is, let's say, group structure in this algebraic space? It means that for every Z in C, X of Z is endowed with the structure of a group in such a way that this should be functional with respect to Z. But to give a Z, as we have explained, is just the same as to give an algebra K prime over K. Z being then just Z of an algebraic space represented by K prime. And what is X of Z? This is a set of homomorphisms of Z and X within the category of affine algebraic spaces, which is, because this category is opposite to the category of algebras, the set of homomorphisms from A into K prime. Homomorphism of K algebras, that's also just X of K prime. So interpreting X, viewing X as we should, by definition, as a functor going from algebras over K to sets, to build a group structure on this is just the same as to build a group structure on each of the xk primes, on each of its values, in such a way that this group structure should depend functorally on the variable K prime. So, group structure on X is the same thing as group structure on each x of K prime, that you can interpret if you want as from of A prime, never mind, of K algebras, in such a way that it's from trigonally such that whenever we have a homomorphism of algebras K prime into K second, the corresponding map from xk prime into xk second should be a group homomorphism. So that's all. So to give a group law on the affine algebraic space X is just to give factorization of this functor which goes to sets through a functor which goes to groups by following it with the forgetful functor, consisting of forgetting the group structure. And now, so in order to give an algebraic group in this general sense over ring K, an affine algebraic group, I should say, that is an affine algebraic space over K together with a group structure on it, is just the same thing as to give a functor going from arbitrary K algebras K prime to the catalog of groups in such a way that the functor which you obtain by forgetting the group structure, which is functor going from the catalog of algebras to the catalog of sets, turn out to be representable. And therefore, in order to define algebraic groups, what you really will do is to define group functors and then check that these group functors are representable as functors within sets. And now let's give, I think it's about time to finish, let's give the first two evident examples, and you will check yourself, perhaps if you have a few minutes at home, that they are representable. Take, for instance, the so-called additive group, GA over K. This will be the group functor which associates to every K prime itself together with the addition. So you will see that this is a representable functor, so that this defines an affine algebraic group over K, which will be denoted, as I said, by GA. It's called the additive group. The multiplicative group is the following. It associates to every K prime the group of invertible elements of K prime star. So this is another example of an affine algebraic group. Both these affine algebraic groups are commutative because for every K prime, these two groups, K prime plus and K prime star, are commutative groups. Now let's give one which is not necessarily commutative. Let's give an integer at least equal to 1, let's say. And let's look at the full linear group scheme, algebraic group of order n. You will note by GL and K. This is the functor from algebras to groups which associates to every algebra K prime over K. The group of n by n matrices with coefficients in K prime which are invertible. I take it as group law on this, the product of matrices. Alright, so next time we will see if it's clear for everybody that these functors are representable. I mean, it's a little exercise, and we will give a bunch of more examples of group structures. So now we should take care, perhaps, that nobody remains without somebody to drive him back to Buffalo. Alright, so we have in our left so we gave a few examples of affine algebraic groups last time. And what we did was to define a few group functors and then check that these group functors are representable by that as functors to sets, in fact, they are representable by commutative algebras. We define that, in fact, most conveniently as being covariant functors from K algebras to sets. So let's write down on the blackboard the few that we had considered. So GA, which corresponds to the functor which to a variable K prime associates K prime with the additive structure. GM, which to a K prime associates the multiplicative group of invertible elements. Of course, we could also consider another type of object which wouldn't be a group object, which would be an algebra object, K algebra object O, which associates to the K prime itself that viewed as in K algebra. And then GA is just O, but together with addition only, and because it defines something a little larger than GM, namely the rule of O, but with multiplicative structure, or at O upper point. So GM, together with its multiplication, is contained in O upper point. It's the largest subgroup object contained in the monoid object, O upper point. All right, and we had G and N, which to K prime associated with a group of n by n matrices. Maybe we write down on the side also the rings that represent here the rings that represent these functors are K of T, K of T again, here K of T, T minus 1, here we have polynomials in n squared variables, in the square depending on variables Tij with Ij between 1 and n, but to which I adjoin delta minus 1, where delta is the determinant of the matrix Tij. And then I had the orthogonal group of a quadratic form Q, and we have seen just half hour ago that more generally, I mean, we can, if whenever the linear group operates on anything, whatever, in any affine algebraic space, we can take the stabilizer of anything. It need not be a quadratic form, it can be anything else. So here it associates to every K prime the subgroup of the full linear group in n variables consisting of those linear transformations which leave a certain quadratic form invariant. So in order to show that this functor is representable as a functor with two sets, we made an explicit commutation, but I gave half an hour ago a little nonsense argument in terms of stabilizators of points, which does it once and for all for these kind of examples. So we have also seen the triangular subgroup Tn of GLN, which corresponds for every K prime to taking the triangular subgroup Trn K prime. Maybe we can write down what the algebra is. So what we are taking are for variable K prime matrices which are 0 below the diagonal, lambda 1, lambda 2, etc., lambda n, invertible elements on the diagonal, so that the determinant is invertible, and anything above. So it's representable. So as a functor with values in sets, to give we can identify this functor to the functor which associates to every k prime a set of elements, a set of all systems of elements xij, where I and j vary in such a way that I is at most equal to j. That means that we don't have to consider what happens below the diagonal, but only what happens on the diagonal and above, where all xij's are elements of k prime, and where xii is in fact in k prime star for every I. So except for this condition, we would have affine space of dimension equal to the number of pairs satisfying this condition, which is, I think, n plus 1 over 2, something like this. Is it so? If n equals 1, we get 1, all right, yes. So it's but we have these conditions, so what we get is in fact the product of the functor which would correspond to taking these systems, but for I strictly smaller than j, which corresponds to what is above the diagonal, plus n times n factors, which correspond to taking n times invertible elements in a k prime star. So that means that it's represented here, this functor, by the polynomial algebra in variables tij on the one hand, for I strictly smaller than j, then in other variables, I will call tii for I between 1 and n. So let's take the variables I at most equal to j. Let's include also the case I equals j, but I and j are between 1 and n. But now I have to add the inverses of the variables t11 up to t and n. Now there is a strict triangular subgroup of the full linear group, which for every k prime consists in those matrices for which are triangular, but for which the diagonal elements are ones. So this is represented by the algebra of polynomials now, with respect to variables tij, where I is strictly smaller than j, and both vary between 1 and n. Is this clear? Now, all right, I'm giving examples, but perhaps some of you could give some more examples of some subgroups of full linear group or other groups.
1xy to 1.
And
1xy to 1.
xy equals 1. And what do you take as a group structure? Aha. So x and y therefore should be invertible elements. All right. Take the hyperbola. That's it. Take g contained in E squared. You see? That's it. Of course, x, y equals 1 implies that x and y are. Yeah? Defined by the value of the functor on k prime is the set of elements x, y in k prime squared such that x, y equals 1. The multiplication being by coordinate-wise multiplication. All right, now this we can either represent in terms of a quotient of this embedding here is a closed embedding. G is represented here directly as a closed algebraic subspace of standard affine space, E2, and this corresponds to the representation of its algebra as a quotient of the polynomial ring in two variables by the ideal generated by xy minus 1. But in fact, this here is canonically isomorphic to the multiplicative group Gm, because to give two elements in the ring K prime whose product is 1 is the same thing as to give an invertible element x. And in fact, and we know also that this here is just one way of constructing K of x to which I join x minus 1. I want to make invertible an element. I add another variable. And then I write down by an equation that this variable is the inverse of the element which I want to make invertible. So that's the standard way of expressing this thing. All right, do you have some other examples in mind? Yes.
How would we do GL2 modulo the square root?
That's a quotient group, you see. That's kind of more unpleasant. So I think we can't deal with quotients right now, you see, because we have to do it with some care. But we can, however, we can define the projective. Could we here now? We don't have projective space either. For the time being, no, we couldn't for the time being define the projective. Yes, we could, in fact, because we have a realization of projective group as being the quotient of the special linear group by the diagonal matrices, which are special linear, which is a group of n groups of unity, and we have a faithful representation. But it would be hard to find this by taking the n tensor power of the standard representation space of SNN. So this would be, I think, a little too subtle for what we can do now. Yes, so let's perhaps notice that all the groups we have constructed here in all GM is a particular case of GLN. And O of Q's or small groups, the triangular groups, the strict triangular group are defined as subgroups of GLN. In fact, GM is a particular case of a linear group, namely this is GL1, but we can also embed it into the full linear group, as you said. Let's see how we can define this homomorphism. That means that that we have a functional homomorphism from K prime star into the full linear group GLN K prime. For variable K prime, this should be this should be a functional homomorphism. And what we take is the following: we associate to every invertible element of K prime the diagonal matrix consisting of lambdas on the diagonal and 0 elsewhere, which is just lambda times the identity endomorphism, which is invertible if and only if lambda is an invertible scalar. In fact, it can be shown, but I will not insist on this point now, that of course GM is a monomorph, goes to GLN as a monomorphism. Lambda is known when we know the matrix it defines. And that in this way GM is identified to the center of this group founder. But I don't want to define now the center of the group founder, because it's not clear that it's always represented by, in our case, by a affine subgroup. All right. So there are other ways, by the way, of mapping GM into GLN, for instance, by mapping as invertible scalar lambda into the following matrix: 0 above and below the diagonal, and on the diagonal we have elements 1 except at, let's say, the ith place. There we put lambda. That means that we're looking at linear transformations of K prime to the n, which don't move the base vector except the ith, on which is multiplication by lambda. This is another group morphism of groups. Now this is not central, yes, this here is much nicer. This is central one. This is not very often that one has to use it, whereas this one here, the central inversion, one has to use all the time. Let's see what it means that the homomorphism of groups is central. Let's assume that we have a homomorphism from H into G. When would we say that it's central? Another exercise on syntax. Or let's say modulo, we have an object in the category C, we're working in, H, we map it into a group object. H need not be a group, and U therefore need not be a group homomorphism. And we see what that means for H goes to G to be central. All right, so we can say, as we don't insist that Z should be a group, let's rather call it Z. So we have an homomorphism U of some Z into G. Now, there are two ways one might think of expressing it. You see, one can either say to give a morphism of Z into G is just the same thing as to give an element of the group G of Z equals Hom lower Z, the set of all homomorphisms of Z into G. All right, now we have an element U, and we can ask that this element should be a central element. But this wouldn't be a good definition, I think, because if Z goes into G as central, and if you have a homomorphism, so consider the condition that U is a central element of GZ, namely is in the center of the group GZ, and commutes with every element of the group GZ. Right, we can consider this condition. Now we'll see that it's not too nice a condition because it's not compatible with composition, with change of Z into Z prime. Because look at now at the morphism from Z into Z prime. This defines a group homomorphism from GZ into GZ prime by composing a variable element in here, variable homomorphism with this fixed arrow. Now, if you have a central element in G of Z, this doesn't mean at all that its image in G of Z prime will be a central element of GZ prime. A homomorphism of groups does not necessarily transform the center, does not map the center into the center. And therefore, if we look for a variable Z, if you look at the center of G of Z, this wouldn't be a functor with respect to variable Z. So what we have to do is to force the definition to be invariant under base change from Z prime to Z. Which means the following. I say that U from Z into G, would this be the correct thing to say? Let's see. What I will do, in fact, is to define a subfunctor of G, which will be called the center of G, which may not be representative, I don't know, and we will say that Z goes to G is central if Z goes to G maps through the subfunctor. So I will define this here. So I will have to define what is, perhaps I rather, in order not to have various C's around, I will rather call the center. I want to define C. So I have to define the subfunctor for variable Z, C of Z, and G of Z as a subgroup, depending contrarily on Z. And what I will do is the following. Yes. So G lies over the final object, and to give a morphism, any object Z lies over the final object, to give a morphism from Z into G is the same thing as to give a section of G over Z by the universal property of the fibered product. So I'm interested in sections of the group object GZ over Z. Where now I'm replacing the category of group objects over K by group objects over the ring of Z, let's say A, okay, let's say K prime. All right? Now, if I have, or this is k prime if you want. Now, if I have a group G prime over the ring K prime, I will have to change our ring. And if I have an element G prime in J prime of K prime, if I have a section of this group over the final object of the category of an algebraic group, so if I have a K prime valued point of G prime, then I can define the interior automorphism defined by this. It will be the automorphism which on K prime valued points would be x goes to, as usual, to G prime x, G prime minus 1. But not only on K prime valued point, but for every algebra over K second, I look at the group of points of G prime with values in K second, and this formula defines as an automorphism of this group, which depends punctually on the variable K second. Therefore, if I have a group object in a category, let's say, of affine algebraic spaces over a ring K prime, it may be in any category in fact, never mind. Then any section of this group object or the final object defines us an automorphism of this group object. So the so-called interior automorphism defined by G prime. And we will say that this section is central if the interior automorphism defined by the section is a trivial automorphism. So I can say the following: if I have a group object G, then in a category, then the reflection I just said gives us an operation of G on by automorphism of itself, with a map of functors from G into the functor automorphisms of G. And the kernel, by definition, of this homomorphism of group functors is the center. I'm sorry, I denote as the center. So the center of a group object in a category is perhaps not a sub-object within this category, it's a sub-functor. When you interpret the group object as being a functor going from, constraint functor going from the category C to groups, it's a subgroup functor which is defined as being the kernel of the interior homomorphism which goes from G into the functor of automorphisms of G. This is a functor which associates to every Z the group of automorphisms of G over Z, the base change of G and Z. So what does it mean that an element is in the center? Let's again take elements of G with values in K prime. That means sections of J prime over K prime. That means that not only when we let G prime operate on the group G prime of K prime do we find the trivial operation, but also if we allow any base change on K prime, and if we let in the same way operate it on the group of points of G prime is going to K second, should it belong to the center, should it operate in a trivial way. That means let's drop the K prime and K second because this is a little special to the situation of specific situation of affine algebraic spaces. But let's take the situation with a general category. So we are interested in the points of G with values in any Z, that is of sections of GZ over Z, which have the property that not only do they operate on the set of on the group of points of G with values in Z trivially by interior automorphism, but the same is true after any base change. That means precisely that not only is the element which we have in GZ in the center of GZ, but whenever we map GZ into GZ prime, by Z prime being mapped into Z within the category, the element remains central in there. All right, so we have defined a subfunctor of any group functor, and in particular of any group object of the category C, which is the center. Now it turns out that if G, but this is not so trivial, so we want to find, Google for the time being, if G is an affine algebraic group over any field K, then the center is again an affine algebraic group. If K is not a field, then one has to assume something like the algebra of G over K being a free module over K or something like this. It's a little tougher. But in fact, we need not worry so much about the fact whether or not C itself is representable, whether C is in the category C. Whether C is in the category, I'm sorry, there's still another C, which is the category. But it's a round of like space over K. It makes a very good sense when we have a morphism within the category to say that this morphism center, namely that it factors through C. Namely that's the element of C of C, of G of C, which we have, is a central element. And we see, of course, that the morphism which we have here from GM and to GLN is central. This comes from the fact that whenever we have a diagonal matrix, all of whose diagonal elements are the same, which is just a homotopy. Therefore, as a linear endomorphism of K prime to the n, then this commutes with every other endomorphism. And it commutes even when we take matrices with constant K second, because the diagonal, so element of the matrix, even when viewed as the matrix with constant K second, remains a homotopy. All right.
How about OpG?
Yeah?
OpG.
Hmm?
The functor OpG.
Well, I mean, that has a tendency not to be representable now, really. Even when K is a field, you see. Take the ideal additive group GA over a field of characteristic greater than 0, or over the ring Z, let's say, or such a thing. Then the functor odd of GA is not representable. Neither by an affine group nor by a general group scheme. It's in fact an end. It's represented by an end affine scheme, you see, by a direct limit of filtering direct limit of schemes with transition morphisms being monomorphisms. It's a funny thing. But however, the yoga here is that, all right, we define a certain number of functors and play around with them, and if they are representable, all the better. If they are not, in fact, we can play around with them in many instances just as good, just as well. And if they're not representable, I mean, they are always representable in some way or other. Not in a strict technical sense, but they're and representable or they're something. I mean, they're always pretty close to something like that. At least those most functors of this type are one.
So yeah.
So here I embedded GM and GLN. GA also can be embedded in GLN in various ways. Let's define a homomorphism of GA into GLN. All right. So lambda now is a scalar which is any scalar, lambda in K prime. So I have to define a group homomorphism of the additive group of K prime into the group of n by n invertible matrices which represent K prime, and homomorphism should be functional with respect to K prime. And I may take, for instance, lambda is mapped to the matrix which has, let's see, zeros below the diagonal, ones on the diagonal, zeros everywhere else, except in the right upper corner where we put the little silly lambda. This can be interpreted in the following way. First, lambda is mapped let's say GA is mapped into GL2K prime by mapping lambda into K prime, is mapped into GL2K prime factorially by mapping lambda into the matrix 1, 1, 0 and lambda in the upper corner. And these are just the automorphisms of affine space of dimension these are the automorphisms of vector space of the free module of rank 2 by K prime, which respect the extension structure of this as an extension of K prime by K prime, so which induce the identity on the first coordinate subspace and the identity in the quotient. This can be identified to home of the quotient into the submodule and into K prime with additive structure. So that's it. On the other hand, GL2K prime is mapped into GLNK prime by viewing automorphisms of the space of the free module of rank 2 as defining automorphisms of the free module of rank n at least equal to 2 by completing it by the identity on the supplement defined by the n-2 next base vectors. And that's way of obtaining it. So in fact, you see that all groups we have written down so far can be viewed as subgroups of a full linear group. And in fact, there are theorems which say that this is a general situation, more or less. Let's say if you have a field, any algebraic group of finite type, namely which as an affine algebraic scheme is of finite type, namely which is a spectrum of an algebra of finite type, can be realized as an subgroup of the full linear group GLN for some n. So this is for that field, not necessarily an arbitrary boundary, and possibly we will prove this later. So that explains why the examples we have written down so far have a tendency to be just subgroups of the full linear group. Now let's give some examples which are less tied up with coordinates as previously were. Let's give a module m over k, and let's look at the functor which associates to every k prime m tensor k prime over k, the tensor product, the module which I deduced from m by base change from k to k prime. Now this is a group for the addition. In fact, it's better than this. It's in module over k prime, and therefore this functor, which I will denote by w of m, is in fact a module over the ring functor O, which associates to every k prime, it associates k prime. So Wm is better than just a group functor, it's a module functor over the ring functor O. And now I wonder, when is this functor representable? And certainly it's representable if m is free. If m is free of finite type. If m is isomorphic to kn for some finite integer n, then this functor here is isomorphic to the functor k prime to the n for variable k prime, and therefore we get that w of k to the n is just standard affine space of dimension n. So that gives, but here we have an intrinsic representation to see. When you have a module over k which is free of finite type, but not necessarily with a fixed basis, then we associate to this in a completely functorial way. And affine algebraic group over k, which is even better than affine algebraic group, it is in fact an affine module over the ring variety, over the ring space O. All right. Now we have a slightly more general case when Wm is representable, namely, it's all right if M is a direct factor of a free module of finite type. Then also Wm is representable. Now the direct factors of free modules are the so-called projective modules. And those which are direct factors of free modules of finite type are projective modules of finite type. So these are quite important modules. Geometrically speaking, they kind of generalize nice, locally trivial vector bundles over the algebraic space defined by K, the final object of the category in this case, over the spectrum of K in terms of linear terms. Never mind. Let's prove that in this case the functor Wm is representable. So M being a direct factor of a free module, so it can be embedded in the free module L, L of Kn, S being the kernel of 1 minus P, where P is a projector within L. So that's the way of making explicit the assumption. You can find a projector in the free module L as an off to some Kn, such that M is the kernel of 1 minus P. Or P if you want, but 1 minus P is another projector. Never mind. All right. Now, this means that M tensor Kk prime, as M is a direct factor of L, M tensor Kk prime, M prime, what I deduce from M by making the base extension K prime, can be viewed as being a direct factor of L lower K prime, namely it is the kernel of 1 minus P tensor over K, K prime. The endomorphism of L prime equals L tensor K, K prime, reduced by 1 minus P by making the ground ring extension. Now if, therefore, the functor Wm has now been represented as a subfunctor of the functor Wl, which I know to be representable, and in fact it's the kernel of a certain homomorphism of Wn into Wl, namely the one which we can write as being 1 minus P. So being the kernel of the homomorphism of group objects, we have seen the lesson before, it's representable. It's representable as a fiber product of the unit section of Wl with Wl over Wn by 1 minus P. So there are some cases when we know that the functor Wn is representable, and we have in principle a way of determining its alpha in algebra. In fact, we'll come back to this in a minute. Here we do it in the most silly way, in a way, to determine the representability. We will find a more intrinsic way a little later. But in fact, let's play around a little bit and let's show that the sufficient conditions which I have proved here for Wm to be representable are also necessary. So that's the only case. For Wm to be necessary, it's less than sufficient to be representable. It's less than sufficient that M should be projected of finite type. Let's prove that. So let's give two, in order to prove this, we will use two properties of representable functors on the category of K algebras. If F is a functor going from K algebras to sets, and if F is representable, then for every map of K algebras, K prime goes to K second, which is injective, then F of U, which goes from Fk prime into Fk second, should be injective too. Because remember that if F is representable by some algebra A over K, then F of K prime are just the set of K algebra homomorphisms of A into K prime, and F of K second are the K algebra homomorphisms of A into K second. So if K prime goes into K second is injective, certainly the map on the homes is injective too. But also, it implies that our functor commutes with arbitrary inverse limits, and in particular, not only finite inverse limits, as any representable covariant functor does. And in particular, F commutes with products. The natural map which goes from F, the value of F on a product of algebras Ki to the product of the F of Ki's is bijective. Now I will use these two facts in order to prove a converse. Maybe I can erase. So let's apply this to the functor Wm, which turns K prime into M tensor K prime. So we want that whenever we have a homomorphism of algebras which is injective, then M tensor K prime goes to M tensor K second should be injective. We want to have this implication. Now this means that the module M over K is flat. By definition, a module M over ring K is said to be flat if and only if for every homomorphism n prime goes into n second, which is an injective of K modules, M tensor n prime goes to M tensor n second is injective too. And it's pretty evident, let's not dwell on this, that instead of taking modules over K, we can take algebras. You see, that's the same property, because of course it's true for modules, it's true for algebras, which are just the tensor product is just constructed. It's a tensor product of modules. So this implies certainly that for every homomorphism of algebras over K, which is injective, M tensor K prime goes to M tensor K second is injective too. But the converse is true also, as we see by applying this assumption to the case of the algebra K plus n prime, where n prime appears as an ideal of square 0, which is mapped to K plus n second, which is the algebra K where n second is written as an ideal of square 0, and this map here is deduced from this map here. So writing that for this homomorphism of algebras, M tensor this into M tensor that is injective, just means that this is injective. Right. So M has to be flat, which is a strong property for a module. Of course, when you have a field, this is not too strong. If you have a field, or if K is a field, our assertion here just means that M is a finite type. But the fact that M should be a finite type will come from this property here, which means that M tensor with the product of algebras Ki identifies to the product of the tensor products. Now let's take all the Ki's equal to K here. So this means that M tensor with k to the I, some power of k, by the natural map identifies to product of copies of m tensor kk, which is m, identifies to m to the I. Now let's see what this means. The elements in here are finite linear combinations of elements of the type x alpha tensor y alpha, where x alphas is finite sums like this, alpha between 1 and n, where the x alphas are in m, and where the y alphas are in k to the I. Which implies that this here is a union of the images of the tensor products m alpha tensor k to the I, where the n alphas runs through all finitely generated submodules. So every element in here belongs to the image of the value of the corresponding functor for variable m for submodules m alpha of m of finite type. Like m as being the direct limit of the submodules which are finitely generated. So this being so here, if you have an isomorphism, this would mean that m to the I, you see, is the union for all alphas of the images of m alpha to the I. But if capital I is infinite, this means that every family of elements of M indexed by I belongs to a submodule of M. I big enough, you see, why not? So we take the family of all elements of M, they must belong to finitely generated submodule. All right. So M is finitely generated, and it's flat. Now, this is very close to being projective of finite type. There's a theorem which says at least that if K is a Noetherian ring, then modules which are finite type and flat are projective of finite type. So in the case of a Noetherian ground ring, projective of finite type is the same thing as flat of finite type. But we want to give a proof without Noetherian assumption. So let's go a little further, and let's prove that M is a finite presentation. M of finite type means that M is a quotient, isomorphic to a quotient of a free module of finite type, called L. So it means that we have an exact sequence 0 R L M 0, where L, M is a module we're interested in, L is a free module of finite type, and R is some submodule of M of L, and we want to prove saying that M is a finite presentation means that R is a finite type. And in order to prove that R is a finite type, I will prove that R satisfies the same relation as here for any set of indices I. And then I'll be through. So all right, let's transform this exact sequence by the two functors with respect to a variable m, so to say, which we have on both sides. Tensoring with k to the I, rotating the i's Cartesian power. Now, because m is flat over k, this exact sequence remains exact after tensoring with anything. And that's another alternate way of expressing flatness. If something flat appears as a quotient in a short exact sequence, the sequence remains exact after tensoring with anything. All right, so we have the exact sequence 0, m tensor, getting m tensor k to the I, getting L tensor k to the I, getting R tensor k to the I, getting 0. Of course, a sequence, if we take a Cartesian power of an exact sequence, it remains exact. So we have also 0 gets m Cartesian power I, gets L Cartesian power I, gets R Cartesian power I, gets 0. And we have the vertical arrows, which are just the canonical arrows. And we know that for M, it's an isomorphism. We know, because L is free of finite type, it's an isomorphism too. And by the 5 lemma, or whatever you call it, I mean, this here, now this arrow is identified by these isomorphisms to this arrow, and therefore these two are just the kernels of two isomorphic arrows. So this arrow here is an isomorphism 2, which means that R has the same property as M with respect to taking tensor products with Cartesian powers of K. That means that R is finitely generated. So M is flat and of finite presentation over K. That's what we have to prove. Whenever Wm is representable. And now there is a theorem of commutative algebra, which is too hard, which you will find in Bugatti, that for a module to be flat of finite presentation is equivalent to saying that M is projective for finite time. Alright, so that ends our little. So we have to be cautious with some functors. They may not be representable. So there are two things which represent the functor from being representable. Mainly, M may not be flat, so it may lie kind of irregularly over K when K is not a field. And second, A may not be of, let's say, finite type or finite presentation. So in the case of a ground field, the only trouble is that M may not be of finite dimension as a vector space over K. But now we will define another functor which will be representable however big and however irregular M, a functor in terms of M. So I again take a module M over K, and I take the functor V of M now. Before this was W of M, which transforms every K prime into the set of homomorphisms as K modules of M into K prime. Now this again is a module over K prime, and the module structure depends functorially on K prime. In other words, V of M again is in fact a module functor over this canonical ring functor O. And now I contend that this module functor, whatever M, is always representable. Now, is there any suggestion of how to prove its representability? So to say that this functor is representable means that we can find in algebra A over K such that this functor is isomorphic to the functor of K algebra homomorphisms, not K module but K algebra homomorphisms of A into K prime. That is, in a module over K, we want to send this module into algebras, and we want to show that this can be done by factoring it in a universal way through a homomorphism of this module into a particular K algebra, and then mapping this to the arbitrary K algebra. So we are looking for a universal way of mapping a module into an algebra. Now,
Can
yes?
Tensor algebra.
That's the symmetric algebra. Yes, let's use it. In fact, the thing that represents the functor is a symmetric algebra of M, which is the direct sum for all n's to 0 of the nth symmetric power of n. So if m is a free modulo of rank n, then the symmetric algebra is just the polynomial algebra generated by n indeterminates. But in fact, this here makes good sense. Whatever the module m, it need not be a free module of higher type. So V of m is the affine algebraic space represented by the symmetric algebra over K of m. Now this will be of finite type over K if and only if m is a modulo of finite type. And I guess it will be a finite presentation over K if and only if m is a modulo of finite presentation. So if you want to insist that your objects, group objects should be affine algebraic spaces of finite type over K or finite presentation, then you should insist here that m should be of finite type of finite presentation. Anyhow, we don't have to put any flatness assumption on m, unless we insist that the group object which obtained should be flat over K. Let's not insist on such a thing. Now, what's the relation between Wm and Vm? So these are functors which look kind of similar. One was obtained using tensor product with an arbitrary k prime, and the other was obtained using a Hom functor with Edison k prime. So if we view as these group or modular objects of the category of affine algebraic spaces, if we view them as depending on m, we see that W of m depends on a covariant way on m, whereas V of m depends on a contrariant way on m. So we have, in fact, we have two functors m goes to W of m and m goes to V of m, which are two functors going from the category of arbitrary k modules, arbitrary, no, that's right. I'm sorry, Wm wouldn't be, however, an algebraic group. It will be just a group functor. From this into the category of functors which are modules over the ring O. But one is covariant and the other is contrariant. So the first is contrariant, it's covariant. The second is contrariant. The situation. Now I want to make a point, namely that we recover the module M up to unique isomorphism when we know either Wm or V of m according to choice, but not only when we know it not as a group object, but as a modular object. We can recover, in fact, a vector space over a field of positive characteristics when we know the associated additive group only. There are troubles which come from the fact that the additive group over a field of characteristic P has group endomorphisms and group automorphisms, which need not be linear, which need not be commute with scalars. Therefore, if we want to recover wholly the M module M in terms of the over K in terms of the module functors they define, we have the we have to use the modulus function of these functors. And now, while it begins to be a little late, I don't want to give full details, but what I'm going to say is pretty evident to check. Let's say the following. These functors here are fully faithful. I will recall what this means. That means that for any two modules m and n over k, the map which goes from hom mn as k modules to hom of wm wn, but here I take homomorphisms as functors of O modules, is bijective, and in the same way, the map which goes from the same hom k mn into the hom in the opposite direction, hom as O modules, functors of vn into vm, now we have a constant functor, is bijective. And we know that this implies that if you have a module, an object in the second category of module functors over O, which comes, which is isomorphic to the image of an element in here, this element here or there, this element is determined up to unique isomorphic. So this here is not hard to prove. And the representability of V whenever, which is representable of W whenever it is, which is not generally true, is of absolutely no help in order to prove this. You just directly work with the functors and you look, it comes out rather trivial. You take what you do is define maps in the opposite direction. That's the compositor. Are the identities. In order to get maps in the opposite direction, you, for instance here, you just take the points here as well as in K. If you have a morphism between the functors, and will deduce a morphism between the K-valued sets or modules. So you get a morphism from M. The K-valued points of this are M, and the K-valued points of this are N. So here you get already the map in the opposite direction. That's out. It checks nicely. So, in fact, this shows us a priori that WM and VM must determine each other mutually because they determine already M. And now, let's write down the relation between the two. Well, I mean, it's pretty much suggested by these dual definitions. The relation is the following. Of course, we have a pairing of VM times WM into O because for every K prime we have a pairing of M tensor K prime and hom M K prime, which is the hom of K prime modules of M tensor K prime and K prime. See, we have a pairing of these two into K prime. So we have a pairing like this, which is functorial, except that this is a covariant functor and that's the contravariant functor, so one has to be a little careful by saying what one means that's functorial. It means that if you have a map from M into N, you see, then WM is mapped into WN, and Vn is mapped into Vm in the opposite direction, and this here is mapped into O, and this diagram commutes in the following sense. If we start with, what should one say? One starts with an element here and an element there, then taking the image there and pairing it to here, or taking the image there and pairing to here, gives the same result. But there's a nicer way of expressing this compatibility by saying that this pairing for value K prime defines a homomorphism of Wm into hom underlined lower O of Vm and O. I take here the functor of O homomorphisms of this module functor into the standard module functor O, the free module of rank 1, about itself. And this compatibility means that this map corresponding that these pairings they correspond to a modular homomorphism of the module Wm into the home module. And the same in the opposite direction. The two statements are equivalent. Vm is mapped to home underline over Wmo. I'm sorry, I was mixing up two different things here. You see, I'm sorry. These both functors Vm and Wm are covariant functors with respect to k prime, of course. To have a k prime, just SO. And this is actually a homomorphism of covariant functors with respect to k prime. But when I want to say that this homomorphism is functorial with respect to m, double m, then I have to use the fact that one factor is covariant, the other is one factor is covariant, the other is contrariant with respect to m. But to have such a pairing, such a linear pairing of functors is the same thing as to map Wm into this here. And the functoriality means that this, with respect to Wm, means that this arrow here is functorial with respect to m. Or it amounts to the same to saying that Vm is mapped into the home underline of Wm into O. And now the relation between W and V is that these two are isomorphisms. And that's an easy consequence of the fact that these functors are free phase request. Do it as an exercise if you want. So there's a funny biduality theorem. So whereas taking biduality for modules doesn't work, you see, except for modules which are projective of finite type. It does work when we correspond, if you consider the functors associated to these modules, one in a covariant, the other in a contrariant way. These are duals of each other, so that each one is its own bidual. Very funny relation. So when you work with module objects in the category of affine algebraic schemes, or modularly of module functors on the category of algebraic of K algebras, then for these you see the duality relations become nice, and they have a tendency to be reflexive, to be their own bidual. Now let's give an alternative description of V of W of M when M is projective of finite type. In this case we said that W of M is representable, but we know that if M is projective of finite type, then M is the dual of another module, namely of its own dual. Then we have biduality in the usual sense. And of course, Vm then is equal, Wm is equal, canonical isomorphic, to V of n, because Wm transforms K prime into an M tensor K prime over K. But this here, because M is projective of finite type, is just the same thing, up to canonical isomorphism. S home over K of n is in K prime, where n is the dual of n. And therefore, Wm, as disregarding its group or module structure, just recording it as a functor going through sets, is represented by the symmetric algebra of n, namely of its dual. And now this is a direct proof of portability, which gives, in an intrinsic way, the affine, the ring that represents this functor, without having to choose a free module of which is a finite type and doing such kind of nonsense. All right, so maybe these examples will suffice for today. at the functor which will by k prime associates say a set of homomorphisms over k prime of nk prime into nk prime. Why not? So this functor here can be denoted by Hom underlined. It's the Hom functor for the O-module structure of V of m into V of n, where V of m, I recall, was the functor which turns k prime into m tensor k prime, but viewed as being a module over k prime. So for variable k prime, we get that Vm as a modulo over the ring functor O, and the same for Vn, and the functor of homomorphism of Vm into Vn is just the same as this functor by what we have stated last time. So view it either way, and we can wonder whether it's representable. Now, what in the particular case when m is pretty simple, when m is equal to k itself, it's a free of rank 1, then this becomes Hom or k prime of k prime into nk prime. In this case, this is just a functor k prime goes to nk prime. This comes from the fact that v in this case is just O itself, and Hom underlined of over O of O into some module is just the module itself. So we get in this case the functor v of n, and we have seen that this is representable if and only if n is projective of finite type. Therefore, we shouldn't expect this functor to be representable, except if n is projective of finite type, because already if m is so very simple, phi of finite of rank 1, it isn't unless n is projective of finite type. So therefore, assume for representability, we will assume that n is projective of finite type, and we will show that in this case this functor is representable. And therefore, we will rewrite this Hom as being Hom over k prime of m tensor n Czech, and Czech is a dual of the projective module of finite type, lower k prime, this is an nk prime. Because to give a homomorphism of a module into a projective module of finite type over some ring k prime is the same thing as to give a homomorphism of m tensored with a dual of this one into, into the ring k prime. That comes from the fact that n is its own, that nk prime is the dual of its own dual. So to map mk prime into nk prime is the same thing as to map it into the dual of this module, which means the same thing as to give a pairing from mk prime times nk prime Czech to k prime, and to give such a pairing is the same thing as to give a homomorphism of the tensor product of mk prime tensor and Czech k prime and k prime. But on the other hand, because n is projective of finite type, taking the dual commutes with base change. So therefore, this here we should write in fact mk prime tensor nk prime Czech. Now nk prime Czech is n Czech k prime, and taking tensor products commutes also with base change. Therefore, this can be written like this. And therefore, this is the functor here, which we had called v of m tensor n Czech, which associates to every k prime the set of homomorphisms of the same module, but where we've changed the base to k prime into k prime. And we know that this functor is representable. So this Hom underlined, therefore, is just the same thing as v of m tensor n Czech, which is representable by the symmetric algebra of m tensor n Czech. The tensor product here is taken by k. Yes?
This is only when n is projecting finite type in this class.
Yes, because we need on the one hand biduality for not only for n but for n k prime after any base change k prime. So this will practically be true only if n is projective of higher type. And also we need that taking the dual of the module n should commute with base change. So I mean we have very heavily relied on n being projective of higher type. I mean this is quite natural because we kind of know that the functor is not representable if n is not projective of higher type. Already in the special case when m is the free module of rank 1, this we have seen last time. But in this case the functor is just v of n. And I'm sorry, I'm confusing my own notations, I'm afraid. That's the function which is called W. It's a function associated in the covariant way. All right. You could also deal as an exercise with Hom underline over O of Wn into Vn. I think because this here is W and V are the module functors associated to a module, one in the covariant, the other in the contrariant way. I think that this is always representable. Maybe you won't deal with this here. I think this will be enough for what we are going to do. Maybe you can try to do it as an exercise if you feel like I should. I think that without condition on m and n, either this or the opposite one. Don't quite remember. It's always representable. Now, for instance, assume that m is equal to n. Then the functor which we have here, so we assume that n is again projective of finite type. The functor then is a functor n defined by n is a functor which we might call armed underline of n. It's a functor which associates to every k prime the andomorphisms of n lower k prime. Now these andomorphisms make not only a k prime module, they make in fact a k prime algebra. But now be careful, it's not a commutative algebra. So therefore, this functor here a priori is a functor of algebras of the ring functor O. And it's representable when we assume n to be projective of finite type. So it's representable by, in this case, by the symmetric algebra of n tensor n shape. So it's an algebra object over O in the category of affine algebraic schemes over K whenever n is projective of finite type. And now let's show that whenever we have an algebra object in a category, or let's say a ring object, not just a commutative ring, but associative with unit, in a category where there are finite inverse limits, that then the subfunctor of invertible elements is again representable. So this, assume we have a ring object, how will we call it R if you want, initial of ring, in a category C, which will be, in the case we're dealing with the category of affine algebraic space over K. So we identify R to a functor going from to a ring within C hat, and a functor which associates to every Z in C. R of Z equals from ZR that is endowed with a ring structure depending concretely on variable Z. So that's the thing. And now I look at the subfunctor, call it R star, which associates to every Z this group of invertible elements of the ring R of Z. of course, a ring homomorphism transforms invertible elements into invertible elements, whether cumulative or not. So in the case which we have here, this would be the functor which associates to every k prime the automorphisms over k prime of nk prime. So that's the functor which we could call aut underlined over O of n, or of, if you prefer, of Wn. One then writes just aut underlined over k over O of n by just identifying n and Wn in the notation. So that's the functor we are concerned with, and I claim it must be representable because of the general fact that in the category C we have a ring object, and if the category C has finite inverse limits, then the R star subobject belongs to C again. Now let's see this. We essentially have done already the argument in the commutative case, in fact, in the case of the group GM, because when is an element of RZ, when is an element invertible, if and only if, by definition, there exists a y in RZ such that xy is equal to 1. And this y then will turn out to be unique. Hey, xy equals 1 and yx equals 1 too. Let's see. I never remember. No, it doesn't imply xy equals 1, it doesn't imply. Well, why not write this to yx equals 1? Never mind. All right, now look at the product R times R, and look at the subfunctor of R times R whose points is within Z are the pairs xy which satisfy these conditions. This subfunctor is equivalent, is isomorphic to the functor RZ star, by what we just said. And now we want to prove that this subfunctor is representable, which means that RZ star is representable. And, well, we will express these equations by looking at two maps of R times R into R. One is the composition law by multiplication, and the other is the opposite law. Xy goes to yx, x comma y goes to the product yx. It's the same, but composed with the symmetry in R times R. And I will take, on the other hand, I have the one element in R which can be viewed as being an homomorphism of the final object of the category into R. So the equation xy is equal to 1 just is expressed that we take the subfunctor of R times R, which is the inverse image of this here, which means that I'm taking the final product here, call this sigma prime if you want. That corresponds to representing the functor of pairs xy such that xy is equal to 1. And now here, we do the same thing for the other equation. We have the one homomorphism of the final object of the category into R. We take the inverse image by pi prime. This is called sigma, the first subobject. Now we have the subobject sigma prime. And now we are interested in the intersection of these two subobjects, sigma and sigma prime, which can be interpreted as being the finite product of sigma and sigma prime over R times R. So using final object, the product of R times R, and the finite product of sigma and sigma prime over R times R, we have expressed the functor we are interested in, namely R star, by finite inverse limits in terms of representable functors. And as C is stable under finite inverse limits, this means that R star is in C. Now, this implies, for instance, that in the case here, the functor aut over O of n is representable. And in fact, that's a generalization of the fact that, of course, that the group which we had called GLN, the group functor GLN, is representative. This would be the case when n is a free module of rank n. And we could give a description, in fact, of the affine algebra of this group object, just as in the case of the matrix group. You see the call this R, and then we have R, which is represented by the algebra sim star over K of n tensor n Czech. When n was free of rank n, then n tensor n Czech was free of rank n square, and this is just in the polynomial in n square variables. And R star now here, the subfunctor, which corresponds to an epimorphism of ranks of this into some other ring which we have to find. And if this ring here is A, it can be shown, maybe you do this as an exercise at home, that we can find a well-defined element delta in A, which plays the role of the determinant in the case when n was a free point of rank n, in such a way that the ring that represents R star as A delta minus 1. This comes from the fact that whenever you have an automorphism of a projective module of finite time, the determinant of this automorphism, or an endomorphism, more generally, if you have an endomorphism of a projective module of finite time, then the determinant of this can be defined. And this is a function on the functor R of all endomorphisms of n. The homomorphism of R into E1 that corresponds to an element of this ring, delta. And to say that an endomorphism of a projective module of finite time is invertible means that its determinant is invertible. And therefore, the singlet represents R star, so that's an alternative proof of the fact that the functor is representable. We get it represented by A of delta minus 1, where delta is the particular element in A I have alluded to. But I won't insist here on the definition of the determinant of projective module of finite time. It's pretty easy to find and to look at problems. So this is just in disguise, so to say, it's a full linear group in n variables. Good as an algebraic scheme over n, except that we have done it in a more invariant way. So, I guess that gives us a number of examples. Maybe we'll give it a few examples of small groups, of finite groups. Yeah. Let's take, for instance, the homomorphism of the multiplicative group into itself, which turns lambda into lambda power n. So it's just GM, the multiplicative group is just an abelian group functor, and we just take its additive notation, multiplication by n. In the multiplicative notation, that would be raising to n's power. So this is something which is canonically associated to any abelian group structure on a functor. So GM is a functor that transforms K prime into K prime star. And now on this functor we look at the homomorphism lambda goes to lambda to the n. Therefore, alright. Now let's look at the kernel of this homomorphism. This is denoted traditionally by mu lower n. So what would this mean? Mu lower n of K prime, that's the set of all elements in K prime star such that lambda to the n is equal to 1. So it's a group of nth roots of unity in K prime. In fact, here instead of saying lambda in K prime star, we can say lambda in K prime. That amounts to the same. Because if lambda to the n is equal to 1, lambda must be invertible. And the inverse of lambda is lambda n minus 1. So it doesn't matter how you write it. And that's a group for the multiplicative structure, depending factorially on K prime. And of course, because it appears as a kernel here of a homomorphism of algebraic, affine algebraic groups in itself an affine algebraic group, and in fact, μn appears here as a closed algebraic subspace of Gm. But let's see how we represent it. Well, I mean, it's pretty clear. The equation which we have written down here for an element of K prime is lambda n equals 1. So we see that μn is just represented by K of t divided by the ideal t power n minus 1 equals 0, divided by the ideal generated by t to the n minus 1. Because once again, to give a homomorphism of this quotient ring if this quotient algebra into K prime is the same thing as to give a homomorphism of Kt into K prime, which means an element of K prime, which would be the image of t, which moreover vanishes on this ideal, which means this element should satisfy the equation lambda n minus 1 equals 0, and lambda n equals 1. So this algebra here, over K, has the property of being free as a module. It's a free module of finite type. Free module of rank equal to n, I guess, yes. It has a basis if the image of t in kt divided by t to the n minus 1, if you call it, what do I know? If you call it psi, for instance, psi equals the residue class of t modulo this ideal, then the ring of μn has a basis formed by 1 psi up to psi n minus 1. Psi n is equal to 1, so we shouldn't add it to the base. Now, more generally, if we have a affine algebraic space over K, which is represented by an algebra A, which is a module of finite type over K, then we will say that the affine algebraic space is finite over K. So here we have an example of a group that is finite, an algebraic group over K that is finite over K. Now, what are the geometric points of μn? With values in a field, for instance. Well, these are just the elements of the field that are n smooths of unity. If the field is algebraically closed, for instance, if you look at the points of μn with values in an algebraically closed field, then, I mean, one thinks of the existence of n, exactly n roots of unity, and one thinks that the group of n roots of unity is a cyclic group of order n. Now, that's not quite true in general. It's true for when the characteristic of the ground field is equal to n. So that's a well-known theory of Eller's theory of, what's the name of the name of the polynomial? Cyclic polynomial. But otherwise, if the characteristic of the ground field divides, things are altogether different. In fact, then the number of points of this group, the group of these points is a cyclic group of order n prime, where n prime is n divided by the highest power of p that divides it. In fact, it's well known that in a field of characteristic p, there are no p's root of 1 except 1. In fact, we know that if we have a ring of characteristic p, then lambda goes to lambda p is a ring endomorphism. So if you have a field of characteristic p, lambda goes to lambda p, it's an injective homomorphism. It's field to itself, and if it's algebraically closed, it's a bijective homomorphism. It's a field with itself. Anyhow, the kernel of this homomorphism on the multiplicative group is reduced to 1. It's the same if we, of course, if you replace p by a power of p. So therefore, if we look, for instance, at the case of the group mu p, let's say, homogeneous to the groups mu p to the I, and if you look at this group on a ring which is of characteristic p, which lies over the prime field of characteristic p, then the groups, the points of this group with coefficients in a field of characteristic p are reduced just to one element. The group of points with coefficients in a field is just the unit group. However, it is not true that this group object in the category of affine algebraic schemes, affine algebraic groups over K is a unit group. If it was a unit group, it would mean that it's a final object of the category of affine algebraic spaces. That would mean that it's the spectrum, that it's associated to the K viewed as the K algebra. But the algebra is written down here. It's K of T divided by T to the n minus 1. It's an algebra which is of rank n, not of rank 1 over K. So we have here an example of a so-called infinitesimal group, I mean a group which has, such that the group of values of this group, that's a group of points with values in fields, is reduced to the unit group, but without necessarily the group being the unit group. Now, these kind of groups wouldn't have been considered by algebraic geometers. Classically, they would have just been ignored as being the unit group because they looked only at points with values in fields. So they wouldn't see the points that occur when you look at rings that are no fields. And however, these groups like mu p to the I play an important part in the theory of algebraic groups. For instance, they appear as kernels of group homomorphisms. Let's be very well, for instance, of this group homomorphism, let's say, but also of, you can't refuse to look at this one. You see, when you take points with values in perfect fields, this homomorphism becomes an isomorphism. Then use an isomorphism on groups of points or values of GM, of groups of points with values in any field of characteristic P when n is the power of P, let's say. But however, we don't want to say that this homomorphism is an isomorphism because, I mean, on the rings, for instance, of GM, I mean, it corresponds to a ring homomorphism, which by no means an isomorphism, which corresponds to the homomorphism of kt t minus 1 goes to kt t minus 1, which transforms t into t to the n. So the image of this thing within here. Let's put different letters for the determinants. The image ring would be k here of t to the n, t minus n. You certainly wouldn't like to call this an isomorphism of algebraic spaces, although it induces an isomorphism for the groups of points with values in perfect fields of characteristic P. So that's one of the main advantages of the point of view I'm explaining here, which is that you get a good hold on inseparability phenomena which are tied up with the existence of groups which are purely infinitesimal, but which are not the unit group. For instance, yes, why not look at the full linear group in n variables over k, and the special linear group in n variables over k, which sits in there as a kernel of the determinant homomorphism, which goes from the full linear group in n variables to the multiplicative group. All right, and now look at the subgroup GM of the full linear group, which we have obtained this embedding by mapping the point lambda, element of K prime star, into the matrix, the diagonal matrix, with all lambdas on the diagonal. Or in terms of photomorphisms of three modules of rank n, we have associated to lambda the homotopy by lambda. Now, this embedding, as I said, is quite natural because it turns out that GM is just the center. Maybe we can make the exercise, or I can indicate how it's shown that GM is just the center of GN and K. This means the following, that if we have a point of GN n with coefficients in K prime, some field, some ring, K prime over lying over K, and if G is in the center of this group and remains so after any ring extension from K prime to K second, we want to prove that G is a homotopy, that G is a diagonal matrix with elements on the diagonal all equal. Now, I guess the way of doing so is to prove that if we look at here in K prime as being embedded as a group of invertible elements in the algebra M and K prime of n-by-n matrices, then it generates this as an algebra over K prime. So any matrix can be written as a linear combination of invertible matrices. And therefore, if you have an element, let's admit this point. I think it's pretty easy to check. And so we don't even have to bother about K second here. All right, now if you have a G which commutes to every element of G and K prime, it implies that it commutes to every matrix, because it commutes to every linear combination of invertible matrices. And it's well known that a matrix that commutes to every other matrix is a homotopy. And being a homotopy and being an invertible matrix, it must come from this embedding. And of course, once we know this, it turns out that this will be also central in every G and K second. In fact, here it turns out that elements of the center of this group are already points of the center of this group function. All right. So this shows how that's really this inclusion here is a very natural inclusion. GM appears as the center of this group. Now look at the intersection of the two, of SLN and GM within this big group. So this is a subgroup of GM which is a kernel of this composite map. Is this not clear? Because SLN was defined in GNN as being the kernel of this. Now what is a composite map? This is precisely the map. Lambda goes to lambda to the n. Matrix of the diagonal, the determinant of the diagonal matrix lambda is lambda to the n. And therefore, this is just mu n, the intersection of the two. And in fact, as any matrix is a product of, when essentially the same argument as before, we see that mu n appears as being the center of SLN. So the group mu n can be interpreted as being the center of the group SLN. So I mean, it has a very natural interpretation. That means that if an element of SLN K prime commutes to every element of SLN K prime, then it's a diagonal matrix of the with lambda. It's a homotopy. And well, you see, every matrix will be a linear combination of elements in here and of scalars. I guess this would be pretty clear. So the same argument should apply. Now, when we will be able to pass to quotients, to take quotient groups, so this will be a little later, we'll speak about this. Then we will construct the quotient of the linear group by its center, which will be the projective group n variables over k. And it will turn out that this will be also the quotient of SLN divided by mu n. Therefore, we have a very important group, the projective group, which when viewed as being the quotient of the special linear group, appears as the quotient of the special linear group by this particular subgroup mu n of nth root of unity. If now n is equal to p, let's say, and if we are working over rings of characteristic p, this means that the projective group is the quotient of the special linear group by a purely infinitesimal subgroup. And certainly, I mean, even in characteristic p, you don't want to identify when actually the group SLN and GPN are not isomorphic. The homomorphism of one into the other is a purely infinitesimal covariance, certain isomorphism. So this is just a digression in order to explain the importance of admitting groups like mu n, like mu p and characteristic p, which are purely infinitesimal and still which are not a unit group. This comes out here very naturally that we will admit them, whether we want or not. I mean, they just turn up because of the very context in which we are working. Namely, functors of arbitrary rings, not only of rings that are reduced from integral domains or fields or such things. Let's give still another example of a group that an algebraic group that exists now, however, only in characteristic P. So assume K is of characteristic P, P being a prime, by which I mean that P becomes 0 in K. So that means also that K is an algebra over the prime field with P element. Then I said that for every such ring like K, which is of characteristic P, lambda goes to lambda P is a ring endomorphism. So this being true for K is also true for any algebra over K prime over K, which is also of characteristic P. Therefore, this can be viewed as being a ring endomorphism of the functor for variable K prime, let's say of the ring functor O, and a fortiori of the underlying additive group structure. Therefore, in particular, in the additive group, we have an endomorphism raising to P's power. It's a kind of endomorphism of the additive group which is unusual from the point of view of characteristic 0, because there the only endomorphisms of the additive group which we know of are scalar multiplications. Here we have raising to P's power. Of course, taking iterates of this, we get also that raising to the P to the i's power is an endomorphism of this group. And of course, we can still take linear combinations of these endomorphisms with coefficients in K. And in this way, in fact, it turns out that we get all endomorphisms of this algebraic group. Yes. They are just finite linear combinations with constant K of these particular endomorphisms. Never mind, take one of these, let's say raising to the P to the i's power. And now let's take the kernel of this. This kernel is traditionally designated by alpha lower P to the I. So it's a functor which associates to every K prime the set of all elements lambda in K prime such that lambda to the P to the I is equal to 0. And this turns out to be a subgroup for the addition. In fact, it's even a submodule, it turns out. Because, as I said, lambda to lambda P to the I is a ring endomorphism of the ring functor O. In fact, the kernel is an ideal it has a modulus over O. We are mainly interested in the group structure of this. Now, of course, very clear that the points of this group with coefficients in any field or moduli with coefficients in any reduced ring must be reduced to the zero group. Because if lambda has a power which is zero, then lambda must be zero in a field or in a reduced ring. So this is another example of an infinitesimal ring, of an infinitesimal group. Now, of course, this group is not the unit group, because this functor is not the trivial group functor, because there do exist algebras over, except when k is equal to 0, of course. There do exist algebras over k prime, which have elements lambda, such as lambda to the p to the I is equal to 0, and which are not 0 themselves. Take, for instance, a ring of dual numbers, such a thing. So that lambda square is equal to 0, lambda not being 0. Another way of seeing this is to look at the algebra that represents alpha p to the I, and of course, by just looking at the equation that defines alpha p to the I, we see what the algebra should be. Alpha p to the I is represented by the algebra k of t divided by t to the p to the I, which is a free algebra of rank p to the I over k. Now, if you have an algebraic space over K, which is represented by an algebra A, which is of finite type over K, if you're lucky, in the two cases which we have considered so far, this was so, it may be that A is even a free module of finite type over K. And in this case, it has a well-determined rank, at least well-determined if K is not 0, which we call N. And the affine algebraic space over K will then be said to be of rank N over K. So the rank will be just the rank of the algebra that represents it, due to being a volume. And one likes to think of this rank as being the number of points in a set, in fact. But some points must be counted with multiplicities. So, for instance, if X is a group object over K, then we would say that X is a group of order if X is finite over K and represented by an algebra which is free over K, then we will say that X is of rank is a group of order N over K if the rank is N. So mu of N, mu over N here, is a group of order N over K, and alpha p to the I is a group of order p to the I over K. But however, the points of this coefficient in the field of a group of order N, is it from a group of order at most N? It may be smaller than N. See, and here, for instance, in the purely addition case, it may be just equal to 1. Let's still give a last example of, yeah?
You can get some non-abelian groups this way by taking quotients. GLA, for example, is a non-abelian.
Well, the projective group is non-abelian.
Finite non-abelian, sorry. Finite non-abelian. The examples that we had just now were...
Yes, I will give you another example. Using again the raising to piece powers, you see. But it will be a purely radical group again. You see? Take any group. Well, let's give. We could start with any group defined over the prime field Fp with p limits. But let's be specific, and let's take, for instance, G equals GLN, the full matrix groups, or any one of the subgroups we have defined so far. I assume that the ground ring over which we are working is of characteristic P, lies over Fp. And now, look, I will define a homomorphism, which will be the Frobenius endomorphism of G, Fg, which for every k prime will be a homomorphism of the group of n by n matrices with coordinate k prime into itself, which will transform a matrix lambda ij into the matrix lambda ij to the p, where every one of the coefficients is raised to the p's power. Because raising to the p's power is a ring endomorphism, it's a homomorphism of rings k prime goes to k prime, it's clear that it defines a homomorphism of GLN k prime into GLN k prime because GLN is a functor. Turns out that here k prime is equal to k second in this arrow, that's all. And of course, this endomorphism of GLN k prime is functorial with respect to k prime. So we get an endomorphism therefore of the functor, that means an endomorphism of the group object, and we can take its kernel, call it small g if you want. So the kernel is a functor which associates to every k prime the matrices with coordinate k prime, for which we have lambda ij power p is equal to 0 if I different from j, and lambda ijp is equal to 1 if I is equal to with respect to variables tij, I and j varying between 1 and n, which we have to divide, or by the equations written down here, by the idea of tij power p, denoted by tij power p for I different from j, and tii power p minus 1. You have to divide by the idea denoted by the elements. And the group is not commutative. It's purely radical because these equations in a reduced ring, you see, lambda I to the j power p equals 1 can also be written down as lambda I j minus 1, so lambda I minus 1 to the power p equals 1, because raising to p's power is a ring homomorphism. Now, if in a reduced ring these conditions are satisfied, this means that each of the lambda ij's for I different from j is equal to 0, and lambda I is equal to 1. That means in a reduced ring, the points of this group are, this group is just the group of points. This values in a reduced ring is just a unit group. But however, as soon as a ring K prime has nilpotent elements, the group will no longer be the unit group. And we have a perfectly good group function, but by no means trivial. And it turns out that this homomorphism Fg from G into G is an epimorphism in a certain sense, which we will have to make explicit. When you embed group of, when we embed the category of affine algebraic spaces into a certain category of sheaves, let's say, and that therefore G can be viewed as being the quotient of G by this infinitesimal subgroup. But Fj by no means is an isomorphism, of course. It's a passage to quotient by a radical subgroup. Now I want to give a common generalization of groups such that as mu n, the group of n's root of unity, and Gm, the multiplicative group. Yeah, do you have a question? So let's give an abelian group M, any abelian group. But I mean, 2 is abelian group, not a group object in abstract category. Maybe Z or, I just think of things like C or Z to the N.
Group
or
object
Z
in
or
set.
NZ.
Group objects in sets, yeah.
All right. And in terms of this, we will define a functor which will be denoted by d of m. D is the initial of dual. It will be something like a dual of m. It will depend in a constant way on m. It transforms k prime, variable k algebra, into the set of homomorphisms of abelian groups of m into k prime star. So for variable k prime, that's a functor from over z if you want, like a form of z modulus, m into k prime star. That's a functor of those in abelian groups. Now, if, for instance, m is equal to z, then we get so z homomorphism of z into k prime star, then it's just a functor k prime star. The homomorphism of z into a group is just the same thing as to give an element of it. So this functor is represented by Gm in this case. So we get back this. Now if m is equal to z divided by the ideal nz, then to give a homomorphism of z over nz into an abelian group is just to give an element of this abelian group, which is of order n. It's a homomorphism of z into it, which becomes 0 on n. And therefore in this case we get mu n. Therefore we get that Gm is d of z, and mu n is d of z over nz. So maybe, so we suspect that this function is representable. If M is a group of finite type, then M will be a sum of groups Mi, which will be isomorphic either to Z or to a group Z over NZ. And of course, this functor here depends additively on M in a constant way. And therefore dm will be isomorphic to the product of the dmi, and as each one of the dmi's is representable, so is their product. So at least, in fact, it will be in this case, if M is a group of finite type, dm will be a algebraic group of finite type over K, because each of the dmi's, each of the factors in here are either gm or mu n, they are of finite type. But now we want to represent the function in general without using such fancy decompositions. But so what will we do? So we have to interpret homomorphisms of M into multiplicative groups, into multiplicative group of variable algebra. All right, so multiplicative homomorphism of M into K prime mapping 0 into 1 as corresponding to homomorphisms of an algebra which we have to construct into K prime in such a way that A should carry the universal homomorphism of M into the multiplicative group. So is there a universal way of mapping M into the group, the multiplicative group of a K algebra? So that's the question. And there's a well-known construction, which is the construction of the so-called group algebra of M. We look at the group algebra K of M, which is the free group generated by elements of M, but taking as a multiple structure on it, the one which is induced by the multiple structure on the base elements. So Km is the free module generated on elements in one-to-one correspondence with the elements of M. I will, however, denote them by a different notation. Let's say E lower M, where small n goes to capital M. I will use something which suggests exponential notation, because the multiplication in Km will be the addition in M. And the multiplication in Km is a unique multiplication, K-linear multiplication, such that En times En prime is equal to E in this M plus index M plus M prime. Of course, when we have a map already defined on the base elements, it extends in a unique way to a bilinear map Km times itself to Km. And it's associative, that's just associativity law on M. It's commutative, that's just commutativity law on M. So we have a commutative ring, which is called the group algebra of M. If M was not a commutative group but an arbitrary group, then K of M would still be an algebra, but it would no longer be commutative. And this relation between groups and group algebras is well known in algebra. It's something pretty standard. All right, and it's about evident. What do I say? Well, to give a map of M into an algebra K prime module into a K module amounts to the same as to give a K-linear map of K of M into the same K module K prime. And if K prime over carries a multiple structure, then one sees at once that this map from M into K prime is multiplicative if and only if the map that extends it from Km into K prime is multiplicative. Whatever is checked on the base elements will carry over. Of course. And that means that if K prime is an arbitrary K algebra, then any homomorphism of M into multiplicative K prime factors in a unique way through the natural homomorphism of map into M into K of M, associating to an element of M the corresponding base element here. It factors in a unique way through a homomorphism of K of M into K prime, through a K algebra homomorphism. And therefore we see that D of M as a group function is represented by the algebra K of M. If, for instance, M is a group C, then choosing a generator, called the generator T, for instance, then we see that the group algebra is just K of T, which we adjoin T minus 1. Because the powers of the generator T are just the multiples in N of the element which we have, but we get this way only the elements, the natural integers, not the negative ones. So we have to add T minus 1 to it. So algebraic groups that can be obtained in this way are so-called diagonalizable. Groups. When M is of finite type, it's easy to see that these are also the subgroups. These are also the groups which can be embedded in the group of diagonal matrices of GM, of n by n matrices. That means these are the groups which can be embedded in GM power R or suitable R. At least when they are over a ground field. That's equivalent. That's why they are called diagonalizable. because they can be embedded into the group these are exactly those that can be embedded into the group of diagonal matrices. So certainly they can, if M is a finite type, because in this case you get products of copies of Gm and Un, or by various values, possible values of n, and it turns out that the converse holds. That every subgroup of Gm power R over a field is of such a type. We want to use this. All right, so I think I will stop here with the examples. A fair list of examples. Affine algebraic groups. So once again, the philosophy here is that in order to define the group, most times the best is to define a group functor and check it's representable. In order to define relations between groups like homomorphisms and intersections of subgroups, etc., you just define it on the functors. It will automatically come from homomorphisms on the representing algebras. So, are there any questions? Does John Duskin about here?
What about terminology on that? The term radicial group and infinitesimal.
Well, it's synonymous.
Okay.
Did I say both?
No, yes, you said both and
So a group object over K, an affine group, let's say, but even a group functor, affine algebraic group or a group functor, G is said to be radicial or infinitesimal by definition, if and only if, for every K prime over K, K prime reduced, let's say, G of K prime is a group reduced to just one element. And so as examples we had mu pi, alpha pi, or the kernel of Frobenius in GLN in characteristic P in prime characteristic. In fact, such phenomena have a tendency not to occur in characteristic 0, at least when we're working over a ground field and it turns out that if we have ground field of characteristic 0, if we have an affine algebraic group which is radicial, then this is unit group. But it's not a trivial term. I guess we will come to it. We have time. We'll see why it is so. It's true without restricting to groups that are finite type. So these inseparability phenomena, they are mainly present in characteristic P. That doesn't mean that in characteristic 0 it's useless to work with important elements. But it turns out that as long as we are just doing group theory, of algebraic groups, it's quite often, it's not so imperious as when dealing with sort of algebraic spaces, not only group spaces. So I guess maybe we should kind of stop and we'll just say what we're going to do next time. Namely, we know that to give an algebraic space over K is the same thing as the algebra A over K. And now, of course, it's a mere matter of translation, an exercise to translate what it means to give on this object G a group structure in terms of quantitative algebra. It will turn out that this corresponds to giving a bialgebra structure on this algebra, compatible with this algebra structure. So this we are going to explain tomorrow. So the last two of the terms on algebraic groups, we have given loads of examples. Are there any questions about those, perhaps? Or is everything clear? The last one I think which I gave was the diagonalizable group E of M over K corresponding to an abelian group M, which was defined by the functor K prime goes to home of Z modules of M into K prime star. In fact, we can interpret it as D of M as being the home functor of group objects of M, viewed as being the constant functor with value M, with values M, the multiplicative group Gm. Because this functor, by definition, this home functor, is a functor which associates to every K prime, that denoted by M lower K if you want, the constant functor defined by M on the capital of K algebras. So this home functor is a functor which associates to every K prime, the set of homomorphisms of functors in the capital of K prime algebras now, of mk prime into gm K prime, the restriction to K prime of the functor gm on K. Here, the group homomorphisms. But M being a constant functor, constant group functor, you see, to map it into any group functor is the same thing as to give a group homomorphism of M to the set of values of this functor on K prime. It's quite general. I mean, if you don't have group structures, if you have a constant functor, to map it to any functor, the same thing as to map the set, which defines a constant functor, into the set of values of the functor here on the final object, which would correspond here to K prime. And when we have group structures involved, which want to respect, we have to take the group homomorphisms. And gm of K prime is just K prime star. So in fact, that's really the right way to interpret D of M. It's so to say the dual of the abelian group M, or of the corresponding constant group functor, the duality being taken with respect to the multiplicative group Gm. And a little later we will see that there's a biduality theorem which says that if you take the dual of dm with values in Gm, you get back essentially M. The constant functor mk accepts it. Well, we have to sheafify it a little. You see, what we can say is that we have a pairing of dm times the constant functor with values k into gm. That means just that dm is mapped into the one underline or groups of mk, so in gm. But also we can do this as meaning that we have a homomorphism of MK into home underlined for the group structures of GM. And in a while we will see that this is essentially an isomorphism, except that the MK, instead of taking just the functor, we have to amplify it a little bit with respect to the topology. Never mind, it will be essentially true. If we take a functor very slightly from the concept. All right. But what we want to do now is to interpret group structures and the like on affine algebraic spaces in terms of commutative algebra. So we are working over the ring K. We are looking at affine algebraic spaces X over K. They just correspond by the arrow reversing device to algebras A over K. And let's see, for instance, what does it mean that we have a composition law on such an object X. It just means that we have a morphism X times X into X. Never mind now about, that's an interior composition law. Never mind about axioms in it. Now, what does it mean on the other side that we give such a thing in terms of the algebra? X times X corresponds to the algebra A tensor A over K. And to give a homomorphism from X times X into X means that we give in the reverse direction a homomorphism between the rings. This means that we give a homomorphism of A into A tensor A. Now this is the initial datum of what is called a coalgebra structure on the K module A. Or if you want to use the fact that A is already an algebra over K, and that this here is an algebra homomorphism, it means that we have a bialgebra structure on A, except that the algebra structure that corresponds to it that we have here is already supposed to be pretty much specific. It's commutative, associative, and with a unit, whereas we don't make any assumption about this arrow for the time being. It's just a homomorphism of this algebra into the tensor product algebra. That's all. Alright? And the same way, if we have an other object y over k, and if you want to see what it means that x operates on y, that means that we have a morphism from x times y into y, while y corresponds to a ring, to an algebra B over k. The product of x times y corresponds to the tensor product A tensor B, and to give a morphism of x times y into y is the same thing as to give an arrow like this of k algebras, modes of k algebras. So this much about composition laws in general, but they have no axioms. And now we are going to express the various axioms one can put in terms of commutative algebra. So what about associativity? That just means for the composition law x times x goes to x. That means that a certain diagram, which we wrote down I think several times, is commutative. Let's call pi here the composition law. And here we put pi, here we put pi, and here we put pi times identity in x, and here we put the identity in x times pi. So that's associativity, the commutativity of this diagram. And now, when we translate this in terms of the dual category of k algebras, what do we find? Well, I think I was wrong to write our arrow in the same direction. I could have written it into the opposite direction to make this clearer. So A stands for this, A stands for that, and the arrow is in the opposite direction from pi. Alright, now I will write just the diagram corresponding to this in terms of protective algebra. So we have A in the corner here, which is mapped into A tensor A in two ways. We will call by the same letter the arrows on the left side and on the right side. Call it pi. Pi and pi here. And now A tensor A is mapped also in two ways. To complete the square into the threefold tensor product, I won't write down the index k to the tensor product. So all tensor products are taken by k. And what are they? So I have to express what corresponds to this map here, pi times identity on x. And when we just do the translation, I mean, it's quite trivial, we see that this as a map corresponds to the map on algebras, which transforms x tensor y into pi x tensor y. So it's the identity, it's pi tensor with the identity on A. As identity, where pi goes from A into A tensor A, so pi tensor on the right with identity on A, we get something from A tensor A into the threefold tensor product. And the same way here, this arrow is the arrow identity on A tensor plus pi. So that's all. So the commutativity of this diagram expresses associativity of the composition law. Now, if we want to express the existence of a two-sided unit for composition law, we have seen that such a two-sided unit being unique, things expressed nicely in terms of corresponding functors, but here we want to have a diagrammatic interpretation. So x lies over the final object of the category of affine algebraic spaces, and what does it mean that we have a section first of x over the final object? This means in terms of the algebra, here x corresponds to A, the final object corresponds to K, viewed as being a K algebra, and an arrow from E to X, I mean the arrow from X to E is just a unique K algebra like this, and a section of X over E is just a homomorphism of A into K. So to give a section of X over E is just to give an augmentation of the K algebra to K. Call it epsilon. And now we want to express what it means that this augmentation is a left unit or right unit or two-sided unit with respect to a given composition law here. By expressing this composition law in terms of this homomorphism of things. So let's erase, well, why not keep the diagrams here. Just make some space here. So let's recall what does it mean that we have a left unit. We have to write in diagrammatical terms that Ex equals to X. So we look at X times X goes to X by pi, and we map X into X times X using the morphism epsilon by taking epsilon times the identity in X. So this would be the map X goes to E comma X, and this composing it would be EX, and we want that the compositum should be the identity. That's the left unit, and the right unit would be the same, except that we would replace this arrow here by the arrow identity in X times Cartesian product epsilon. Of course, I use that X times E is equal to E times X up to canonical isomorphism is equal to X because E is the final object. I have used this identification. Now let's look on the other side. We have to reverse the arrows. So A is mapped into A tensor A by pi. Now, here the map from x into x times x corresponds to a homomorphism from A tensor to A. You have to say what it is, and it would be epsilon tensored. I mean, it would be the map, what would I say? Well, yeah, that's epsilon tensored with the identity on A, which would be a priori homomorphism, which goes from A, because epsilon goes from A into K. Epsilon from the identity tensor the identity goes from A tensor A into K tensor A, which is just A. And the composition should be the identity. And that expresses that epsilon corresponds to left unit. And when we want to express it as corresponds to the right unit, we write the same diagram, except that this arrow is replaced by identity in A tensor epsilon. And if we have a composition law, namely, here it would be a co-composition law in terms of the dual category, namely a morphism pi of A into A tensor A. If you have an epsilon in augmentation from A to K, which makes these two diagrams commutative, then it must necessarily be unique. This comes from the fact that if you have a two-sided composition law set theoretically, then it's unique. All right, what would it mean that the composition law is commutative? So this associativity, this here, is existence of unity. That's right commutativity. That means that if you look at the composition law pi here, and if you look here at the symmetry, S on x times x, which is just given by xy equals to yx, such that which interchanges the first and the second projection on the product. I'm sorry, here we have pi, and here we have pi again. That's the triangle here is commutative. That pi is not changed when we compose it with symmetry. Now, this just means, if you look at it the opposite way, pi corresponds to morphism from A into A tensor A. Here we have the symmetry of A tensor A, which transforms X tensor Y and Y tensor X. Isomorphism. And here we have pi, and symmetry means that this is commutative. Commutativity of the composition law means that this diagram is commutative. So we have expressed associativity, we have expressed existence of unity, and we have expressed commutativity. And now, so now we know how to express the fact that the composition law turns, for instance, X into a monoid. Just means it's associative, it says unit. Or into a commutative monoid, it just means that moreover this is satisfied. If we want to have a group law, then we have to write one more axiom, the existence of an inverse. So we can do this in various ways. So the one I had started with when we made the nonsense on the blackboard at the beginning of this course was, I think, by saying that there should exist, a morphism from X into X, how would we call it? Symmetry sigma, let's say, which will be unique, fortunately, such that the following would hold true. We want to write that G, sigma G, to be equal to 1. That's what we want to express. That sigma on points associates to every element and inverse. Good. Alright, now let's express this. Look at x times x morphed into x by pi. And now we have to give a morphism from x into x times x, which associates to G, here the pair G comma sigma G. So this would be identity comma sigma. To give a morphism of x into a product of the same to the two components, which I wrote down here. And now we should build the constant map, you see, which associates to every G as a composite term, which associates to every G just the element 1. And this means that it should be the same thing as mapping G into the final object by the unique morphism from X into the final object. And here we take epsilon. The morphism that defines unit in X. And this would be commutative. That's what expresses the fact that sigma defines a passage to inverse. Isomorphism is in the category of an algebraic space. And in fact, whether it's an isomorphism or not, in fact, if we can find a sigma having this property, when we know that when we have already an associative law with unit, then the sigma must necessarily be an isomorphism, and it's uniquely determined. And now let's express this diagrammatically by dualizing everything. So as A mapped into A into A by pi mapped into A by x tensor y goes to. So we are looking for a sigma which should be homomorphism from A into A. That's if we are expressing a property for the sigma. And here x tensor y will be mapped to x times sigma y. That's we get in this way homomorphism of A tensor A into A. You see, in order to give such a homomorphism, we have to give it only on the two factors arbitrarily, and we take x as the identity and sigma. And we should get the same thing as taking here epsilon, which is the given augmentation of A, which we have here, and here we take the unique homomorphism of K into A. And this diagram should be commutative. So this is here the existence of inverses. Alright, so everything is expressed in a completely mechanical way. The diagrams are not particularly exciting. It's fortunate that one rarely has to use them explicitly, because all group functors which we have looked at, I mean, they turn out to be a group functor in an evident way. We didn't have first to check such diagrams. Sometimes, however, it's good to know that a group law on this of an algebraic space associated to an algebra A just corresponds to giving such a pi, an epsilon, and a sigma in such a way that the diagrams written down here, there, and there, not necessarily this one, these three ones, should commute. And of course, in this case, the general nonsense about group laws show that on the one hand, epsilon is uniquely determined, and second, that sigma here is uniquely determined. Sometimes sigma is called the what is it? Well, it has a name, but I forgot the name. Never mind. People working with hot algebras, what is the name they give it?
Or you must.
No, they have a funny name. Never mind. It resembles to this, it's not suggested. Never mind, anyhow. It's not so important. So pi is quite often called a co-multiplication. Either on the module, if A is just a modular, but in our case it's an algebra, so if you want it to be an algebra co-multiplication, then it has to be a homomorphism of algebras here. Epsilon, because So this co-multiplication is said to be associative if this diagram here, which is constructed in terms of pi commutes. So if pi is a co-multiplication, then we define what it means for pi to be associative. That means that the diagram 1 commutes. What does it mean that it's commutative, which it often will not be in what we are doing? It means that diagram 2 here commutes. Then we will say that the multiplication is commutative. We will say that it has that it's unitary, let's say, if there exists an epsilon going from A to K, which is called the augmentation. The augmentation corresponding to the co-multiplication, such that the diagram, the two diagrams embodied in 3 commutes. And it's known then that epsilon is uniquely determined. And it's called to be Now, that there is a, they don't call it contraposition, I think that's what I would call it. And one says that there exists a contraposition for, let's say, I'm not sure that that's the standard name, I think I remember it. I think like something like this. No, it's not contraposition. I could look up in some old seminar notes somewhere. Contraposition. Sigma A to A. We say that there exists a contraposition when we assume already, I guess, that it's associative and unitary. If there's such a homomorphism, sigma A goes to A, which makes this diagram for commutative. And in this case, this contraposition is uniquely determined. Now, all these notions are pretty common in algebra when dealing with co-multiplication, for instance, in dealing with Hopf algebras when one has more overgraded structures. But here, in our context, there is no reason to assume that our algebras are graded. Now, in fact, all these notions make in fact a sense even if we don't have an algebra structure on A. If A is just a K module. So forgetting about algebraic spaces, we have such a homomorphism of modules makes good sense. And one can put these various axioms that it showed, it turns out one can still show that if epsilon exists, if the augmentation exists satisfying the condition, and here it's unique and the same for sigma. So such a co-multiplication without assuming a priori that A has an algebra structure will turn A into a co-algebra. If, well, it's just like with algebras. According to the circumstances, one assumes or not doesn't assume that algebras are associative, have units and the like. You see. So let's assume here that we take is that coalgebra structure will mean that you have a co-multiplication pi, which is associative, unitary. It is when the K module A has both a co-multiplication pi and a multiplication which turns it into an algebra, so a co-multiplication which turns it into a coalgebra, the multiplication which turns it into a coalgebra, and in such a way that the two are related through, let's say, the coalgebra structure pi being an algebra homomorphism, not only a modular homomorphism. But it turns out that this is equivalent to saying, that's funny symmetry, that the homomorphism called pi prime of modules which gives the algebra structure, namely A tensor A being mapped into A, that this homomorphism is compatible with the comodule structures. This homomorphism of this viewed as a comodule by as a tensor product of comodules being mapped into A. So I mean there is quite a number of general nonsense one can say about relations between algebra structures and coalgebra structures, which can fill a number of pages in algebra text. But for us it wouldn't be in fact so important. What is really important to remember is that, and there are pretty evident diagrams of K-algebras that express those axioms which have been put on composition laws. Let's go on slightly more and see what it means if you have a group or monoid object X. Then it means that it operates on an object X. Well, X was already the group object, so maybe you call it G now. So G just corresponds to A. Now G would be, let's say, a monoid within the category of affine algebraic spaces, and we will see what it means that G operates as a monoid on an object X of the category of affine algebraic spaces. That is, if you have a composition law G times X into X, what it means that it's associative. So let X be the spectrum, let X correspond, to the K algebra B. Therefore, this morphism from G times X into X just corresponds to a morphism from B into A tensor B. Call this here, what do I know, omega, so operation. Here we have omega then. And how will you express the axioms which are sensitively expressed by saying that G applied to G prime X is equal to G prime X, and that 1 applied to X is equal to X. We have to express these two axioms of the measure of a monoid on a set. All right. So here we have the three arguments G, G prime, and X. This shows us that we have to look at G times G times X. We map it into G times X. We are first looking at this side here by using the composition law in G and multiplying it by the identity in X. So to a triple G, G prime X, we associate the pair G, G prime, comma X, and now we use the operation here to map G times X into X, and we can do it the other way around. G times G times X goes into G times X by the identity on G times pi to the pair G, G prime X, to the triple G, G prime X. I associate the pair G, comma G prime X. And now again, I use omega here, and this diagram to commute. That's one of our axioms. So let's write it down here. sorry?
One is
Here, this is omega, this is omega 2. Look at this formula, you see, I multiply.
Yeah, but pi is a multiplication of the group, right?
Yes.
And you want the identity plus omega.
Uh,
Don't you want that identity plus omega from g plus x into g plus x?
One side, that's G operating
Oh, I'm
on
sorry,
the result
yeah.
of operating on it,
Yes.
two different sets.
Yes. Right. Yes, that's it. Yes. Now it's correct. All right, now let's transpose this diagram. We have x which corresponds to b, mapped into a tensor b, which corresponds to g times x, mapped into a tensor b, and on the other hand, b is mapped into a tensor b through the same omega. And we have here another arrow, and now these arrows here, they correspond, we said, to pi times identity, so here we have to take pi tensor the identity on b, and here we have to take the identity on a, I guess, tensored by omega, and this would be commutative. So this expresses associativity, but we have still to end this axiom except when it's a group that operates. Do they have to end this axiom or not? I think they have to end it anyhow. Yes. Yes. In order to express that the group operates on a set, I think associativity doesn't suffice. One has to write down, I think, that one operates like one. Doesn't one?
Yeah,
Yes. True or not? I mean, it's not a relation, it's not its consequence of transitivity. Of associativity. Because yes, there's a trouble with projectors in a set. Yeah. Yeah, I guess so. All right, so now we have to express that one times x operates as x. Now, what is this? We take g times x goes to x by omega, and I map x into g times x by taking epsilon. We call it, we have an epsilon which goes from the final object to x times the identity in x, and the compositum should be the identity. I guess that's it. And when we transpose this, we get b goes to a tensor b by omega, and this goes into b by using epsilon tensor identity in b, I guess, and the compositum should be the identity. All right. So this here, which we have kind of separated from the diagrams, let's write rather about the diagrams. We have B mapped into a tensor B in omega. Therefore, to have a monoid object G operate on another object X of the category of affine algebraic spaces just means that we have another algebra B over K, that we have a homomorphism of algebras of B into B tensor into A tensor B, homomorphism of algebras. So, and that moreover, this extra data satisfies these two axioms here, in which, let's see, we use phi, which defines the comodule structure in A. The coalgebra structure in A, omega, which is this thing here, is omega, and of course the epsilon, which is associated to the coalgebra structure in A. It turns out, therefore, that these two axioms do in fact explicitly use the multiplication law in A nor in B, you see. Just forget that A and B have multiplications. Just recall that their modules were K. And then in this module A, you have a co-multiplication here, pi, and an augmentation epsilon from A to K, which satisfies axioms here listed, which may turn A into a unit and into a coalgebra over K, associative and unitary coalgebra over K. On the other hand, we give a homomorphism of K modules like this, omega, and we assume that these diagrams that can be formed in terms of these data is commutative. So, I mean, this makes a good sense, forgetting completely about algebra structures anywhere, working throughout with the coalgebra structure of data. Then we say that such data turns B into a co-module over the coalgebra A. So all we have, moreover, is that B turns out, in our case, the case we are not interested in, that B moreover carries the structure of a K algebra, and that, and A also, and that all arrows that are written down on the back. So the important things are pi, epsilon, omega, are algebra homomorphisms.
Is this equivalent to giving a homomorphism inside from G into, say, n XX, as you define it, a natural transformation?
Yes, that's the same thing. To add, that's a configural nonsense, you see, which is valid in any category. If G is a monoid object, and to let G operate on object X is the same, we're looking at the group object of automorphisms of X, the group functor, which need not be representable anymore, which is just an object of C hat, C being the category we're working in. Then it means that we just give a homomorphism of monoids of G into this here. So that's just nonsense. But it would be hard to express this directly, you see, in diagrammatic terms, so that we can express it in terms of commutative algebra. I mean, according to, when we have to do extra computations, you see, in terms of rings, you see, we have to sometimes to come back to these diagrams, and then really we have to use things like this G times X goes into X. Whereas when we are working with the functors and with the points of these functors, then this way of doing things is generally more intuitive, more handy. All right, so this shows that for all the affine algebraic groups which we have constructed so far, I mean there are a few dozens, the algebra set, and we have constructed explicitly in most cases the algebra that represented these group functors, but these algebras carry in a natural way a structure of a bialgebra named a coalgebra structure which is related to its algebra structure in the way I've said, so that the co-multiplication is a algebra homomorphism. And it would be easy in every case to make explicit this coalgebra structure. It's a trivial exercise. But in a way, it is, one rarely has to use explicitly this coalgebra structure. And doesn't pay in a way, in most cases, writing it down. We can, however, do it, you see, in the case of a few groups like the additive group and the multiplicative group, let's say. So the additive group corresponded to K of T, you see. And so we have to see what is the coalgebra structure in K of T. So we have to map K of T and K of T tensor with K of T, which is also the Polymer ring in two variables, T prime and T second if you want, by taking T prime to be T tensor 1 and T second to be 1 tensor T. Now to use a homomorphism from KT into a ring is just, in algebra is just the same thing as to give the image of T. So this diagonal homomorphism, pi, this co-multiplication is defined when we know pi of T. Can be any, a priori any element in here, but we have to find which. And we immediately find that pi of T is equal to T prime plus T second. That just means that the multiplication is expressed by, in the group, let's say, if you look at homomorphism of KT into K prime, these just correspond to giving the images of T and K prime, namely to giving elements of K prime, and to say that the group law that we put on the set is the addition of K prime, just expressed by saying that's diagonal homomorphism. Maps T into T prime plus T second. Maybe you should check it after all, why not? So, to give a, you have to express the following, that this diagonal homomorphism has the following property. If we have two morphisms of the two factor of this tensor product in here, into the K algebra K prime, call one of them lambda prime and the other lambda second, which therefore will define a homomorphism of this tensor product into K prime. Alright? And if I compose this with pi, I get the homomorphism of KT into K prime. I want to write down that, let's call lambda this homomorphism. I want to write down that lambda is the product for the group structure which we put into this set of homomorphisms of lambda prime and lambda second. Now, homomorphisms of KT into K prime, whether lambda prime, lambda second, or lambda, are just identified elements of lambda prime, of K prime, I'm sorry. So what I want to write is that lambda is equal to lambda prime plus lambda second. That's the relation which I have to write down here, and to see which is the homomorphism pi which achieves this. Now, if I have two elements lambda prime and lambda second of K prime, which correspond to homomorphisms like this, they correspond to homomorphism of this tensor product, which transforms T prime into lambda prime and T second into lambda second. And therefore it will transform T prime plus T second into lambda prime plus lambda second. And now if I look at the homomorphism from KT into here, which transforms T into T prime plus T second precisely, you see, then if I compose it with the homomorphism I have here, that it will transform T into lambda prime plus lambda second, which was what I wanted. Now let's look at the multiplicative group. This is the spectrum of KT T minus 1. Now, this could be mapped by a diagonal morphism corresponding to this, the tensor product of KT T minus 1 with KT T minus 1. Now, when we look what this tensor product looks like, introducing again the same variables t prime and t second, which is t tensor 1 and 1 tensor t, we get the polynomial ring in two variables t prime and t second, to which we adjoin the inverses of the two variables t prime and t second. And what we have to do is to define a homomorphism of this ring into this ring here. And that's the same as to define an element of this ring which is invertible, as we have seen. So we have to define a pi of t, which should be some invertible element in here. And we want to express now the composition law, lambda equals lambda prime, lambda second, identifying homomorphisms lambda prime and lambda second of kt t minus 1 to k prime to be just elements of k prime star, invertible elements of k prime. And looking at the homomorphism it defines from the tensor product to k prime, I want that the composition viewed as being an element lambda of k prime would be just the product. And this is achieved by taking pi t to be just the product of the coordinates t prime and t second, which is invertible because t prime and t second are invertible in this ring. So the fact that we take addition here and the multiplication there is just expressed by the fact that we take addition rest multiplication of the natural indeterminates in these tensor product rings to express the diagonal homomorphism. So we could, of course, go over, take again all the examples we have seen. I think it's not worth it. And then of this, maybe we should express in terms of commutative algebra what it means that a monoid G over K in affine algebraic monoid operates on a K module M. So if I make it K module M, then M, as we have seen, defines a functor on K algebras, which I denote by Wm. K prime goes to M lower K prime. That's one of the ways of associating a functor from K algebras to sets, let's say, in fact, groups, abelian groups. In fact, Wm was better than just an abelian group object. It was a module over the standard ring functor OK. And now I will say that G operates linearly on M if it operates on this functor Wm by, well, yeah, by automorphisms, let's say by automorphisms. That is, if you have a homomorphism of G into the functor odd over O of Wm, which is just, we have considered this functor already. This is a functor which associates to every K prime the set of automorphisms of the K prime module M lower K prime.
Can you think of G as a monoid and odd as N?
And odd it was?
And odd as N, the homomorphisms of.
No, I rather like to take the automorphisms here. Yeah, I think, yeah. Never mind, if you feel safer, take G to be a group after all. Then if you let it operate in an associative way so that unit operates by unit, you see that it operates necessarily by automorphisms. So, therefore, to say that G operates on the module M, by which we mean that it operates on the module functor Wm, just means that for every algebra K prime over K, the group GK prime operates on the K prime module in the usual sense, M lower K prime equals M tensor K prime, in such a way that this should be functional with respect to M K prime, in such a way that if K prime is mapped into K second, so that the group G K prime is mapped into the group G K second, and that the module M K prime over K prime is mapped into a linear way, K prime linear way into M K second, we want that for every element here, when we look at the operation here, and its image there and the operation there, this arrow should be compatible with the operation we have here and there. That's what it means. But by operating, we mean that it operates in a transitive way. It's unit operating as a unit. Now, and we want to express this in terms of commutative algebra by expressing the group G in terms of an algebra A over K endowed with the bialgebra structure given by the co-multiplication pi. All right. Now, how are we going to do this? So recall that this every group GK prime or module GK prime should operate on M tensor K prime. Now, of course, we can, one way of seeing things is if we take the universal case when K prime is equal to A. We have a universal point of G with groups in some K prime, namely the canonical point G, element of G of A, which corresponds to the identity homomorphism of A into A. And therefore, this universal point of G is in the ring A should therefore define an endomorphism of M tensor Ka as an A module. An automorphism, I'm sorry. So call this automorphism. Let's say, well, so U of course, to give a homomorphism of a tensor product into something is the same thing as an A linear homomorphism is the same thing as to give a K linear homomorphism of M into this A module. So to give U an A linear homomorphism like this, or to give U naught a K linear homomorphism like this is the same. But still, as we insist on having automorphisms, well, we need not insist on it after all, because at the end it will come out from the other axioms automatically. So let's say that we have a homomorphism like this, and this corresponds an A linear homomorphism which corresponds just to a K linear homomorphism like this. Now we reconstruct the operation of G on M from the knowledge of U or of U naught, because of functoriality of these operations, because if we have now any point in G of K prime, you see, call this point, what do I know, G prime if you want, and if you want to see how it operates, so how G prime operates on M tensor K prime, we just remark that this point G prime is the image of the point G by a well-determined homomorphism from A into K prime, which induces GA goes to GK prime. All right. And therefore, we must have a commutative diagram like this. Let's work in terms of U if you want. We have here M tensor K, K prime. We have here the homomorphism for U or G prime. That's what's the one which we want to describe. And this diagram should be commutative. And this here should be K prime linear. But of course, if you give a homomorphism like this, there's a unique homomorphism of a K prime linear homomorphism like here, which makes the diagram commutative. That is the one which is induced from U by making the base change in this A module from A to K prime. That means if we don't consider the axioms on the action, namely transitivity and unity, acting as an entity, if you just want if we forget about the group homology structure of G, and we just want to say that an object without structure in the category of an algebraic space operates on M in the most trivial sense of the word, that such an operation is the same thing as to give a homomorphism of M tensor Ka into M tensor Ka. Or what amounts to the same, an A linear homomorphism, or what amounts to the same, a K linear homomorphism, U naught of M into M tensor A. Now, however, we have to express the associativity law and the unity law, and I will just say what the result is. One has to. So, unity is expressed in the following way. We have a homomorphism of A into K, that's the augmentation, and therefore we can look if M tensor A goes to M tensor K, which is M. This would be epsilon. This would be identity in M. I'm sorry, I wrote G on the right, on the left of M when I wanted to have a G operator on M. So maybe I better write the tensor product like this. I think this will be better. So I multiply epsilon by the identity of M tensorially, so I get the homomorphism of A tensor M into M. On the other hand, I have already a homomorphism from M into A tensor M, which is RU naught. So I can look at the composite term, and this would be the identity. So that expresses the axiom that 1 operates as 1. And if we want to express associativity, what we will get is the following. Let's see. If M is mapped into A tensor M, and this will be mapped into A tensor M. This here is U naught, and this here is pi tensor identity in M. But I can also, let's see, map M into A tensor M by U naught, and then map it to A tensor M by identity in A tensor by U naught, and this would be commutative. So this here just expresses that one operating on x is equal to x. And now 1 is a point of g rational over k, and so we just have to express it. I mean, it's just look what this means and write it down as this, and we get this diagram. Should I do it? I gave the description of seeing how an element of the group operates on a point. So we just make it explicit. And the other relation which we want to write is that gg prime x is equal to gg prime applied to x. So this would be a relation for two general points g and g prime, arbitrary points, you see. And of course, in order, there's a universal way of getting a pair of points of g with values in some k prime. It's to take, for k prime, to take A tensor A. You see, by taking the two homomorphisms of A into A tensor A, which correspond to x goes to x tensor 1 and 1 tensor x. That means, in reversing the arrows, to map an object of a category, if you want to look at pairs of arrows in a category to a given G, there's a universal way of getting such a thing. It's by taking Z to be equal to G times G and take the two projections. And if you want to check a thing for any pair of morphisms here, such that if it's true for a pair, it's also true for the inverse midgets of this pair obtained by composing, then you have to do it only when, in the case when Z is equal to G times G and then you take the two projections. All right. And therefore you write down this formula in the case when k prime is equal to A tensor A. That's the group which we have in here. And you just make it explicit and it comes out with the commutativity of this diagram. So now let's look what we have obtained as a result. So we started with a group object in the category of affine schemes, that is with an affine group, which corresponds therefore to an algebra over K endowed with a co-multiplication satisfying two or three axioms. That's it. And we want to see what it means that this group operates on a K module M, and we have seen that this means that the homomorphism of modules now of M into this tensor product. So in order to make a sense out of this, we don't need in fact the algebra structure of A, just the K module structure of A. And we want that this homomorphism should satisfy these two conditions here, should make these two diagrams commutative. Now in these diagrams, what has been used in order to write them down? Of course U0, which was a structure which defined the operation. On the other hand, we had to use the augmentation of A, epsilon here, and here we had to use the co-multiplication of A, and that's it. In fact, we didn't even use the algebra structure of A. It's kind of funny. In fact, we just used the co-algebra structure of A together with the augmentation that could be defined anyhow in terms of the co-algebra structure as being the unique augmentation, which was a two-sided unit for this co-multiplication. Now, then we have a co-algebra over K defined by co-multiplication I. Then we say that we have a co-module over the co-algebra. If you have a K module M together with such a diagonal homomorphism of M into A tensor M, so we say that A co-operates on M instead of operates on M in such a way that these diagrams, which are kind of dual to the diagrams saying that an algebra operates on a module, here it's a co-algebra that cooperates on a module, that these two diagrams are commutative. So the category of K modules on which G operates doesn't depend in fact on the role of G, it depends on much less, it just depends on the co-K algebra defined by G. It doesn't depend on the multivariate structure of it. It is just the category of comodules over this coalgebra. So we see that we get a certain standard notion, a certain number of standard notions of algebra from the theory of affine algebraic groups and representation of these groups. Now what I said here is true in fact whether G is a group or monoid. It would be still true if G is a monoid. But it is not clear then that having G operate on M, that G will operate by automorphisms. It may operate only by endomorphisms, as we pointed out. If you wanted to operate by automorphisms, we may have to insist that the endomorphism of A tends to M, the A linear endomorphism corresponding to U naught, should be an automorphism. That's all. Something that you could check, but which would be, by looking at the diagrams, is that to have G operate on X, G is by K, let's say G is a, let's say, monoid object of the category of affine algebraic spaces. X is an affine algebraic space. Let's say X corresponds to B. That to have G operate on X, in the sense I have explained, not necessarily by automorphism, by the way, having it operate on endomorphisms, but if G is a group, it will be necessarily by automorphisms. Which we have seen means that we give a homomorphism of B into A tensor B, you see. It is the same kind of data that we have written down where M was instead of B. It's the same thing. I have to have G operate on B, which is after all a module over K, so it makes a sense that G operates on a module. But respecting not only the K module structure, but the K algebra structure. By which we mean that if we look at points of G as well as in K prime, and if we look at the endomorphism of the module Bk prime defined by these points, in virtue of the fact that G operates on the module B, then these endomorphisms should be in fact algebra endomorphisms of the K prime algebra B. That means in fact, in terms of what we have written down here, this means that in the generic position it should be an algebra endomorphism, which also means that this homomorphism, that M is replaced by B, should be a homomorphism of K algebras, no more, no less. And when you just look at it from this point of view, you will just see that the comodule axioms just expressed the fact that G operates on X with this little supplement. But this was a kind of trivial a priori, you see, because B and X, so to say, determine each other mutually, not only over K, but also when you make a base tangent to K prime. Therefore, the functor of endomorphisms of X or the functor of endomorphisms of the algebra functor defined by B are just the same, except that we have to do something, the usual error reversal. So, saying that G operates on the left on one on X means that G operates on the right one one B one has to be careful with this. If G is a group object, however, then one need not distinguish between the two because you have message to inverse, which allows to consider only F. All right, so this was this exercise. Perhaps next time what we will do is to see what this gives in one or two particular cases. For instance, what are the linear representations of a diagonalizable group? It's kind of a nice application of this concept. Maybe the reason for the difficulties I pointed out, which are not really difficulties, I mean, things are always as they should be, but in mathematics. But it's because, you see, when I associated Turing A, the spectrum of A, as being just a topological space, and then looking whether this functor from, which goes from, let's say, affine algebraic spaces to topological spaces where this commutes with products or finite products. In a way, I was missing an important point, namely that that means that the topological structure on X is only a small part of the structures that you should put on X. In fact, X, as we will now see, is a ringed space. And once we look at our functor as going as being a functor which goes from the category of affine algebraic spaces to the category of ringed topological spaces, or more specifically locally ringed topological spaces, then this functor again behaves perfectly well. It transforms finite products into finite products. It just turns out that the product in the category of ringed topological spaces, or locally ringed topological spaces, rather I should say, finite products are not compatible with the set-setting formation of products. So that's all. And I mean, topological space. Then to give a sheaf on this topological space is the same thing, which means a pre-sheaf on the space satisfying certain extra conditions, or controllant functors from open sets to sets, let's say, satisfying certain negative conditions. Well, it's amounts to the same to give a sheaf on the space of open sets, namely to give a controllant functor going just from these particular open sets to sets, and which satisfies the exactness condition with respect to covering of such precise open sets by other open sets of the same type. Therefore, to define a pre-sheaf, to define a sheaf on X, this was in sets, let's say, afterwards we will look at possible structures on X, is just the same thing as to give a functor, controllant functor, which associates to every subset of the type XF for the sheaf F, if you want. A set F of XF, and whenever XF is covered by open subsets XFI, if you look at the intersections of the XFIs, which are just the XFIFJs, XFI intersects XFJs, then we should have a commutative diagram. Fxf is mapped into the product by taking the products of restrictions. F of x, fi is mapped into the twofold product of x, f, x, f, ij. And we have this diagram, whatever, by the way, the functor we have, and to say that f is a sheaf means that this diagram is exact for every covering of xf by sets xfi. So that's how we will describe the category of sheaves on the logical space X. in terms now essentially of commutative algebra, because let's write simply, you see, this here, let's write it, what we know f of small f, instead of maybe in order to have it easier to state the things, let's call G the sheaf we want to describe. That's G of xf, let's call it this just G of f. And we will see, so every element of the ring A that should be associated as set, and we will now see what are the data to put on this collection of set, and the conditions to put on these data in order to have a sheaf. All right. So I was a little short here when I said that I had a function from the xf's to sets, because let's now make it completely explicit. So first of all, for every f in the ring A, we should have a set gf, and if you want a sheaf of modules, it should be a sheaf of groups, let's say it should be, this gf should be a group, and if you want a sheaf of rings, it should be a ring, etc. And on the other hand, for every pair f and g in A, such that xf is contained in xg, I want a map where restriction map, as we will call it. I will see if I have introduced some notations there. I didn't. All right. Restriction map rho fg if you want, which goes from g of g to g of f. And now I will have to interpret in terms of commutative algebra what it means that xf is contained in xg. This means that the complements, which are just v of f a and v of g a, are in the opposite relation, so that the closed set defined by f contains the closed set defined by g, which means also that the radical ideals associated to fa and ga are in the opposite inclusion again. So that xf contained in xg means that fa is tilde is contained in ga tilde, which means also that that this ideal fa is contained in this ideal, or also that f is contained in this ideal. So this means that f is element of ga tilde, or also it means that there exists an integer n, positive or zero, such that f to the n is a multiple of g, that f to n belongs to the ideal ga, namely that f to the n is equal to gh. So there exists an integer n and an h in a such that f to the n is equal to gh. So it's something that can be expressed in terms of divisibility relations in the ring A. A power of f should be divisible by g. That's what it means that xf is contained in xg. And for every such pair, I could have a map from gg into gf. Now, with transitivity, if xf is contained in xg and is contained in xh, it turns out that the relation between f and g, which I have written down here, the existence of n and h such that f to the n is equal to gh, the transitive relation, it's essentially the reverse of the divisibility relation, except that I introduce powers still. All right. Then I want that g of h mapped into g of g mapped into g of f, that the composite term should be the map from g of h into g of f. And also, if f is equal to g, so xf is equal to xf, of course, in this case. Also, this I should, yeah. Then I should have that gf goes to GF should be the identity. So in fact, what I have expressed so far is that I have a pre-sheaf on the category of open subsets of the particular type XF, which we have interpreted now in terms of pre-sheaves on the category whose set of objects would be A, and whose category structure comes from the order relation on A, which is written down here between elements F and G of A. But these pre-sheaves in themselves, you see, wouldn't have too much topological significance, because it's not sheaves on the space of open sets that are independent of the spaces, but it's the sheaves. So now I have to write down the exactness property, and exactness property is here. So let's, however, write it down in terms of quantitative algebra, writing down the conditions. When the F in A and elements Fi in A indexed by any set capital I, if XF is a union of the XFIs, then I want that the diagram written down here, which makes sense whenever the XFIs are contained in XF, so that one can take the restriction morphisms. So call this diagram but right now S. The diagram S should be exact. Namely, should identify this first set to the subset of the second, formed of elements whose images by the two arrows we have here are the same. Now, in order to make C a condition of quantitative algebra, we have still to interpret what it means that XF is a union of the XFIs. All right. So let's make this explicit here on the toner. And then we have made the whole thing explicit in terms of quantitative algebra. So on the one hand, it means, of course, that XFI for every I, XFI is contained in XF, which means, I recall, what was it? That there exists n lower I, it may depend on I, of course. And there exists an H, which depends on I also, such that if I to the power ni is equal to fhi is a multiple of f. So that's one thing. And now, that means that the union of the XFI is contained in XF, and now we have to express the converse relation. We have to express that XF is contained in the union, so that means that VF contains the intersection of the VFIs, which is also V of the ideal generated by the FIs. So that's what we have to express in terms of quantitative algebra. Still, it's expressed in topological terms here. Now, this means that we have the inclusion in the opposite direction between the radical ideals associated to these ideals, and it means that F A tilde is contained in sigma FIA tilde, and this again means that F is contained in this radical ideal, that means there exists an N, and there exists elements phi I in A such that F to the N is the linear combination of the Fi's with coefficients of phi I. Sigma Fn is equal to sigma, or call it Gi if you want. You can find the power of F, which is a linear combination of the Fi's, which belongs to the ideal generated by the Fi's. So Fn is equal to sigma Gi Fi. Now we have interpreted everything in terms of commutative algebra. In fact, you have reconstructed, as we would say, the site of the open sets of the type x lower f. Site means just on one hand it had to be plus the covering data in terms of commutative algebra. And we are going to construct, in fact, a sheaf of rings according to this recipe. But at the same time, it will be handy to construct something more general. And also at the same time, the sheaf of rings and some sheaves of modules over this sheaf of rings. So we will start with a module M over A, which will vary eventually, an A module. And to this we will associate a sheaf on X, interpreted in this way. And when M is equal to A, then the sheaf that we will construct will be in fact a sheaf of rings. Or maybe now so it's a sheaf M tilde that we want to construct, which will be called eventually the sheaf of modules associated to the A module M. So we have to construct M tilde of F for every element F of the ring. And what we will take is the localized module MF, which can be described in various ways. Now I will have to make a little parenthesis of algebra. MF, so M can be described as being, for instance, the Dirac limit of copies of N, but M equals Mi, let's say, M equals M alpha, indexed by the positive integers, but M alpha is mapped into M alpha plus 1 by multiplication by F. So in this way MF appears as the Dirac limit of A modules, and therefore it's an A module. And we have, of course, the canonical homomorphism of M into MF, because M can be viewed as being just M lower naught here, the initial step of the Dirac limit. And so we have a homomorphism we have constructed in terms of M another module MF. F now will be fixed for the time for a little while. And M, we will allow it more to vary in a minute. And look at the homomorphism of M into MF. We are going to characterize it by universal property. Namely, remark that in this module, M lower F, multiplication by F becomes invertible, becomes an isomorphism. Because multiplication by F is just, in fact, also the transition morphism here, which we took, and then we take the Dirac limit of these transition morphisms. So in the limit, things level out, and F becomes an isomorphism in the limit. Every element of the limit, you see, belongs to one of the M alpha, or take M alpha plus 1, takes the next one. It's the image of something by F. And here, on the other hand, if let's show that F. So this shows that F acting on MF by multiplication is surjective. On the other hand, let's show it's bijective. That's injective. Let's take an element of the limit which is annihilated by F, so it belongs to one of these M alphas. And so the multiple of this by F maybe is not 0 in M alpha, but in some later thing. M alpha plus R if you want. All right. So we can assume, therefore, that provided we replace alpha by alpha plus R, that the element which we have in here is annihilated by F. but then its image in M alpha r plus 1 is 0. And therefore its image in the limit is 0. All right, I mean, it's the most trivial way of constructing a module in which f becomes invertible to take diagonals of copies of M vector to each other by f. And on the other hand, by just the same kind of argument, we see that this map of M into a module where f is invertible is universal. Namely, that for every a module n, such that the homotopy by f in n is bijective, it's an isomorphism, and for every homomorphism of m into n, a modulo homomorphism, there exists a unique homomorphism of f in n into n, which makes the triangle commutative. But this is trivial checking in the same way. So MF appears as universal, as a solution of a universal problem, mapping M into modules, n modules, in which the homotopy by f becomes an isomorphism. And therefore, we see that MF behaves functorially on M if you have a homomorphism of M into N. Then there exists a unique homomorphism of MF into NF, which makes the diagram here, where the horizontal arrows are the canonical homomorphisms of N into the localized modules. We call MF the localization of M with respect to F, such that this square is commutative. Because we look at this combination here, it's a morphism of M into a module in which F is invertible, becomes invertible, and therefore it factors in a unique way through MF. So we have already two ways of describing this MF, either as a direct limit of copies of M or as a solution of a universal problem. And we can again give a third description. Let's make the list. MF can be viewed as being the set of formal expressions x divided by powers of f, where the sum, the module structure, namely addition and multiplication by scalars, is defined in the obvious way, namely lambda x, where x is in M and where n is an integer, and where the multiplication by scalars is given by lambda x over f to the n. Lambda is now an element A, is equal to lambda x to f to the over f to the n, and where x divided by f to the n plus y divided by f to the n prime, let's say, is equal to what we obtain by the reduction to the same denominator, which would be what I call take as a shortcut f n plus n prime as a common denominator. So fn prime x plus fn x prime over fn plus n prime. And then you check immediately that among the set of pairs x comma n, there you can introduce an equivalence relation where x divided by f to the n is equal to x prime divided by f n prime, if and only if well, you just chase denominators. This would mean that f n prime x minus f n x is equal to 0. That's what we would like to write, but it turns out that this is not quite an equivalence relation. We have to remember that f is supposed to be bijective in the result, and therefore this relation should be in the module which we eventually want to construct equivalent to the same relation factored by f to the m. So therefore the relation is that there exists an m such that f to the m times fn prime x minus fn x prime is equal to 0. Now in M. So we look at this equivalence relation, And we see that the addition written down here and the multiplication written down here on pairs x, n are compatible with equivalence relation and turn the set of equivalence classes into an A module. And then this A module f becomes invertible because x over fn is equal to f times x over fn plus 1. This shows that f is surjective. And we show that f is injective because fx over fn equals 0 implies, I mean that's just, this here is just fx divided by fn, and to say that this is equal to 0 by the definition here just means that exists an m such that fn multiplied by fx is equal to 0. And this shows that x to the fn is equal to 0 because this is the same condition. All right, I mean, you can introduce in this way a calculus of fractions, and you show you map m into mf in this way by mapping every x into x divided by 1 by f to the power 0. Or else to map it to fx divided by f, or modulo to fn x divided by fn. In fact, the two descriptions are essentially the same because the map x goes to x over fn, and would be the canonical map of m identified to m1 to m identified to mn by the compositor. All right, so we have this construction. Now, when m is equal to a, then this construction gives us back the ring, the set which we have denoted by AF, which is localized ring AF. So it has not only the structure of an A module, it has a structure of an A algebra, in fact. It's a ring, and the homomorphism from A into AF, standard homomorphism, is a ring homomorphism. In fact, in this case, the multiplication in AF is written as x over fn multiplied by y over fn prime is equal to xy over fn plus n prime. So we have, in fact, AF has a ring structure, and A goes to AF is a ring homomorphism, and the modular structure on AF just comes from this algebra structure. So what more can we say? We can say, in a natural way, NF is a modulus by AF. So this can be seen in various ways, either by saying what is the product of a scalar lambda over lambda over fn belonging to AF times an element x over fm belonging to mf. Well, this would be lambda x divided by f n plus m. So this would be the silly way of describing the product structure, which turns MF into an AF module. Another way of saying things is the following. By AF as an algebra over A can be described by the universal property that to map AF into any algebra over A, commutative or not, is the same thing as to give in this algebra an element, how should I say, I'm sorry. We have a ring homomorphism, A goes to AF, and now if you have, and which is such that F in A becomes an invertible element in here. Now if you have any homomorphism of A into ring R, such that the image of F and R is invertible, R being a ring not necessarily commutative, then this can be factored in unique ways for homomorphism of A to R. Therefore, AF is a solution of the universal problem here in the category of rings, of mapping A into a ring in such a way that F becomes invertible. Ring homomorphisms here are supposed always to transform unity to unity, all rings have unities. And now, if you take the ring R to be the ring of endomorphisms of an Einstein group, call it, what do I know? n. Then to give a homomorphism of A into this ring is the same thing as to give over this on this abelian group a ring structure, a modular structure over A. And we say that to give a modular structure over an abelian group, an A modular structure over this abelian group, such that F should operate on it as an isomorphism amounts to the same as to give an AF modular structure on N. So to give a module over AF, therefore, is the same thing as to give a module over A, such that F operates as an isomorphism. Now, if you apply this to the particular case of the A module M lower F, and this A module, F operates as an isomorphism, and therefore MF can be viewed as being an AF module. That's a unique way of extending the scalar multiplication from multiplication by elements of A to multiplication by elements of AF in such a way. There's a unique AF structure on A which restricts on an F structure of an AF module which restricts to the given structure of an A module on MF. Alright, so there are various ways of viewing, of describing the structure on MF. And now, what about what happens if we have a variable F? Now assume that XF is contained in XG. Let's define a homomorphism of MG into MF. I say that there exists a unique homomorphism of MG into MF, which makes the square commutative, where the vertical arrows are the canonical homomorphism of M into the localized modulus either MG or MF. Here I am setting. So all I have to show is that if well, to give a homomorphism of MG into MF is the same thing as to give a homomorphism of MG into MF. I'm sorry. How is this? Does this work?
Represent the elements of MG and right.
So all we have to prove is that, let's see how it does this work. F at XG, yeah. All we have to prove is that the multiplication by G operating on MF is an isomorphism. That G acts as an isomorphism on MF. Because if this is so, then the given homomorphism of M into MF, which is a homomorphism of M into a module where G acts as an isomorphism, can be factored in the way through homomorphism of GM into MF. So we have to prove that if we have a module such as MF on which F acts as an isomorphism, then G acts on it as an isomorphism too, using this inclusion XF contained in XG. Now, here we have interpreted this inclusion in terms of commutative algebra. XF is contained in XG. If and only if we can find a power of F which is equal to multiple of GF, of G, then it's G8. Now if f is invertible in a module, then f to the n is so too. And therefore, both g and h must be invertible on it. Therefore, g must be invertible on it. So this defines the factorial law of mf for fixed m with respect to f. Of course, this map from mg into mf, whenever xf is contained in xg, is itself factorial with respect to m. And of course, because of the unicity of this map from G into MF compatible with the canonical co-augmentations from M into these modules, we have also transitivity. If F is contained in XG is contained in XH, then the map which we get from MF, I'm sorry, I'm supposed to open the direction, from MH into MF by the restriction just a composition of the maps which we have here. So we have the pre-sheaf on the category, I can say, of all atoms, on the ordered category of all elements of the ring A. So I have the data A and B. And now we could, in fact, if you wanted, that's how it is done. And the book with Dudonné, we could take the associated sheaf and be happy, but we want to prove directly that this pre-sheaf, in fact, on this category is a sheaf, then we satisfy this exact property when the f and fi's are tied by these relations. So let m tilde be this function. M goes to mf, then the main statement here, which allows us to work nicely and smoothly, is that m tilde is a sheaf. I should perhaps, before going to prove this, maybe I should make some more comments on the structures involved. So m tilde a priori can be viewed as being a pre-sheaf with values in Abelian groups, let's say, or in A modules, let's say the pre-sheaf values in the category of A modules, so it's what about, however, the pre-sheaf A tilde? Associates to the F, A over F. This is a sheaf with values, pre-sheaf, I'm sorry for the time being, with values in A algebras, and therefore also with values in rings. On the other hand, MF for every F is a modulo where F is. And of course, when we look at the restriction homomorphism, MF goes to MG if we assume XG contained in XF. We have also the restriction homomorphism AF goes to AG. This is the ring homomorphism, and then it's quite clear that this homomorphism is compatible with the ring homomorphism here. With in any way, whether by calculation, for instance, of these module structures. In fact, it amounts to the same saying that this is an A module homomorphism. It has been described as such a automatically an A module homomorphism. All right, and therefore M tilde can be viewed as being a pre-sheaf of A tilde modules. A tilde being a pre-sheaf of rings. Once we will know that everything are sheaves, then they can be viewed as being sheaves on the space X, not only on the basis of these open sets. And then A tilde will be a sheaf of rings, or if you prefer, a sheaf of A algebras, over this topological space, and M tilde will be a sheaf of modules over this sheaf of rings. And of course, as such, the structure as a sheaf of A modules will be stronger than will imply, or will be a consequence of its structure as a sheaf of A tilde modules, because A tilde itself is the sheaf of algebras over A. All right. So you have to prove that M tilde is a sheaf, namely you have to prove that for every element F in A and family of elements Fi which satisfy the relations written down here, that the natural diagram where we have MF here, the product of the MFIs here, and the product of the MFI FJs here, that this here is exact. So let's try to prove this. I hope I won't get mixed up in all these indices. So let's first prove that this here is injective. That means if you have an element x divided by Fn in M lower F, and if its images in the MFIs are 0, call this here, these restrictions, call them rho I if you want. And here you have restrictions rho ij. Alright, assume, prove that if rho I of x over Fn as an element of M lower Fi is equal to 0 for every I, then x over Fn is equal to 0. Now, in order to define the restrictions, what did we have to use? That some power of Fi is equal to a multiple of F. So, replacing these, I should have said that because we have a pre-sheaf on the F's, on variable F's, it follows immediately that NF is isomorphic canonically to M to the Fn, because F and Fn are equivalent in this are isomorphic in the category we have been working with, which is equivalent to the category of all open subsets of X of the type X over F. Therefore, replacing the Fi's by isomorphic objects, if I can say, of the category, we can assume that Fi, each of the Fi's is equal to a multiple of F, which will make things simpler. And so I assume that x over Fn is equal to 0 in M over Fi. Now I will write it down as being something divided by a power of Fi to make this explicit. So this x over Fn is equal to x,
Excuse me,
yes?
can you do this even if we have infinitely many indices?
Infinitely many years doesn't make a difference. Because this comes from the fact that if xf is covered by the xfi's, it's also covered by a finite number of them. And therefore, to check this exactness by putting here the whole family of indices or only putting those, the finite number among them, which we have picked, which cover already, it's the exactness of the two diagrams is equivalent.
I mean, to change the exponent, you do need.
Well, I mean, for every Fi, I replace it by F prime I, which is equivalent to it. You see, then the MFIs and these here would not have changed. So I mean, the diagram would not have changed at all. I didn't have to take here a common n. I didn't care. MFI, you see, doesn't change if you replace Fi by something which is isomorphic to it, and the category of all elements of A. For instance, if you replace by power of Fi. I mean, it depends just on the set xFi you see. All right. So x over fn, we will write it xhin, and as being an element of mfi, we will write it as xhin divided by f by f fi power n. I'm sorry, fhi power n is equal to xhi power n divided by fi power n. And what does it mean that this here is equal to 0? In MFI, this means that there exists an integer m, depending, of course, we are working for fixed I now, integer m, such that fi to the m xhin is equal to 0 in m. That's what it means. To say that an element in a localized module is equal to 0 means that the numerator multiplied by power of the element we are localizing, with respect to which we are localizing, is 0. And here we are localizing with respect to fi. All right? And so, in the first theory, if I multiply this by f to the n, you see, this will still be 0. But I have here fi to the n multiplied by fhi to the n. So this would just mean that fi power n plus n times x is equal to 0. This means that x is multiplied by some power of fi. So the fact that the element x over fn in MF becomes 0 in MFI means that x multiplied by some power of fi becomes 0 in M. In fact, I could say it differently because 1 over f is invertible in M over fi, you see. To say that this is 0 in M over fi is the same as to say that x is 0 in M over fi, namely that fi is multiplied by some power of fi is equal to 0. Right. And we have to prove that if this is true for every I, then x is equal to 0. I'm sorry, then is x, then is x multiplied by some power of f is equal to 0. So if for every I there exists an integer mi such that fi mix is equal to 0, we have to prove there exists an integer m such that fmx is equal to 0. That's what means, what the injectivity here means. But now we have to use the fact that the xfi is clever xf. We have not used it so far. We have just interpreted the meaning of exactness here. But it means that f, or some power of f, belongs to the ideal generated by the fi's. Or that the fi's generate the unit ideal. But in fact, we could replace as well the fi by the fi power mi if we wanted. So for simplicity of notation, making this statement, we can assume that fix is equal to 0 for every I. And now multiply this by gi, where gi is what comes in the relation f to the n is equal to gi fi. You get that sigma, for every I gi fi x is equal to 0. And summing it, you get that sigma gi fi x is equal to 0. Or what amounts to the same, sigma gi fi multiplied by x is equal to 0. But this here is equal to fn. So we get that x is multiplied. It's annihilated by the power of f. So we have exactness on the first step. Now let's prove exactness here. So assume we have a family of elements in here, which we can write down as fi divided by some power of fi. The image of this in mfi fj is equal who is the image of xj and fj in here. All right. So this means that fj xi minus fi xj multiplied by some power of fi fj, which might depend on the index ij, mij, is equal to 0. And I want to find an element in here, x equals an element, let's say x divided by some power of f, which gives rise to the xi over fi in these modules. Now, as I've noticed, I think we will have to use this fact. We can reduce to the case where the family of indices, restrict to the case where the family of indices is finite. Because Fn, you see, xf can be covered by a finite number of the xfi's, or what amounts to the same. Fn, this power of f, is a finite linear combination of the fi's distribution in the ring A. And so we can forget about the other indices. And in fact, this kernel here, this inverse limit of this diagram here, will not change when we replace a given covering by any subcovering. And that's a general nonsense fact of Czech homology. All right, and therefore, if we make this reduction, we can assume that the exponent which we have here does no longer depend on the indices we have. Now, this relation we can write as being, let's put it inside, that f j m plus 1 fi m xi is minus fi m plus 1 fj f power j xj. I'm sorry, f power j m xj is equal to 0. And let's introduce these elements yi equals xi multiplied by fi to the m, which enter in this relation in the natural way. So this is yi, and this would be the same notation yj. So the elements which we get here, xi over fi, is just equal to yi divided by fi power m plus 1. All right, so we just write these elements of the mfi's in terms of the yi's instead of writing them in terms of the xi's, and we get, and m plus 1, let it give another name. Let's call this now m if you want. So we have yi divided by f, or call it m prime if you like, random. These fixed changes. And our relation is that fj power m prime yi minus fi power m prime yj is equal to 0. That means that we just chase the denominators without multiplying by some extra power of fi fj. Writing the limits as yi divided by fi power m prime. And now now the fi's generating ideal, you see, the fact that some power of f can be written as a linear combination of the fi's implies that it can be also written as linear combinations of the fi's to the m prime. Because, I mean, what we have expressed by saying that some power of f can be written as a linear combination of the fi's is that xf is contained in the union of the xfi's, but the xfi's don't change if I replace fi's by powers of it. So I have a relation that some power of f, say f power n, is equal to a linear combination of the fi power m prime, let's say. So I use these gi's now, and I will take the element y equals linear combination of gi yi and if I'm not mistaken, the element y over fn will do. So instead of x, call it y now. This will give rise to these. Let's check. So we want to prove that for every I, the image of y over fn in mfi is equal to yi divided by fi to the n prime. That's what we want to prove. What does this mean? So forget about the row I because it just means this here. But using the fact that f is invertible in A over fi, so that this writing makes a sense. Now this means just that, so we have to check that fi m prime y minus f to the n yi is equal to 0 in m lower fi. That means that it's killed by some power of fi. That's what we have to check. And now let's just to see what this means. We are replacing y by its value here. So let's rather write this because I is fixed here and here is its summation index. Let's rather write it the summation as summation over j. So fi m prime sigma over j gj yj. We have to check that this is equal to fn yi in mfi. Now how we are going to do this? Well, let's enter this factor fi to the m prime within the sum sign. So we get fi to the m prime yj here, multiplied by gj. And we sum this over j, and we want to get we want to see what this is equal to. We want to find fnyi. But fi m prime yj is equal to fj m prime yi. In fact, in m even. Therefore, we just make this replacement. So by interchanging the indices g and I, now we get sigma gj fj m prime yi. And this here, now we see that yi goes out of it, and it's yi multiplied by the scalar gj fj to the m prime, which is equal to fn. So we get fnyi, which we wanted to obtain. So that's the whole magic there is. In fact, so this shows that localization, you see, with respect, in a module with respect to the variable element f, can be just viewed as taking, as localization in the topological sense, namely taking sections of a certain sheaf over a smaller open subset than the whole of spec x, namely over x lower f. The value, of course, of this sheaf, if we have looked at the value of this sheaf m tilde over x, this is equal to m localized with respect to 1. This is equal to m. So we view m as being the module of sections of a sheaf of modules over x. And going over from m to mf is just taking the group of sections, not over the whole of x, but just over the open subset xf of x. So that's the interpretation that sheaf theory on the spectrum of the ring A gives us of the localization. And I think it's really quite important to keep this in mind if you want to make any geometric sense of quantitative algebra. I gave here the most, in a way, most stupid down-to-earth proof of this exactness. There are more fancy ways of stating and proving this fact here. For instance, one way would be the following. Look at the rings AFI and AFIFJ. Then the localized modules M with respect to Fi are just the tensor products. Okay, I didn't say this, did I?
No.
Yes, let's give this as a forced description of the localized module MF. So MF is a module over AF in a natural way. It's a unique AF module structure on MF, which restricts to the given A module structure. On the other hand, as we have said, the homomorphism from M to MF is compatible with homomorphism on the scalars from A to AF. It amounts to the same to saying that it's a linear homomorphism. And therefore, it's associated to homomorphism of M tensor AAF with MF. And this again is an isomorphism. We can view MF as being deduced from M by making the base, the ring shape from A to AF. So localizing can, from this point of view, can be interpreted just as making a base change with respect to a localized ring. The proof of this fact that this is an isomorphism would, I think, be evident, isn't it? In any way. This here would be then the natural morphism of M into the module deduced by base change. Let's see if we get the universal property back. Let's look at this homomorphism. First of all, of course, F being invertible in AF must be invertible in this tensor product. Alright, so this is the homomorphism of M into a module in which F becomes invertible. And now if you have any module N in which F becomes invertible, and any homomorphism like this of M into N, why can't it be factored like this? Well, to say that F is invertible in N just means that N can be viewed as being an AF module. And our homomorphism of M into N is compatible with the homomorphism of A into AF, and therefore factors like this. And it's really alright. So here we have the forced description of the localized module MF, and therefore, if we assume we have a finite set of indices only, then the homomorphism from MF into the product of the MFIs can be viewed as being the homomorphism deduced from A goes to the product of the AFIs by tensoring with M. And the same for the double arrow here into the product, double product of MFIFJs. This here is deduced from the analogous homomorphism in the particular case where M is equal to A by just tensoring this by M. And therefore, the statement that this is exact for every M just means that this, after I tensor it with any M, becomes exact. Now let's call this product of rings, let's call this A prime. Or let's call it A prime. Then we see easily that this second product is just the tensor product of A prime by itself over A. Because take the tensor product of an algebra over A, which is a product with another, which is a product, you get that this tensor product should be isomorphic to the product of the tensor products of AFI tensored over A, AFJ. But this tensor product here is clearly A is localized with respect to FI, FJ. That comes from the universal property again. To make Fi and to make Fj invertible in algebras over A, for instance, making the product of Fi and Fj invertible. So this diagram of rings can be interpreted as being the diagram A prime, tensor A prime, where A prime is a certain algebra over A. And now one can ask, now this problem now of looking at the exactness of MA prime double arrow MA second, where MA second is this tensor product. M being a modulo by A, and A prime being deduced from it by the base change to A prime, and here we have 2 times base change to A second from A prime. Here. So you can ask the question, is this always exact? And of course, you can't expect it always to be exact if A prime is 0, for instance. Then this and this are 0. And this could be exact only if M was 0, you see. So that the exact is some assumption on this algebra A prime over A. But which turns out is that this is always exact if A prime is faithfully flat over A. And it turns out that in the case we were interested in, where A prime was a product of localized modulus of A with respect to Fi's, and when the Fi's generates unit ideal, which means that the XFI's cover the spectrum X, then in fact A prime is faithfully flat over A. But here we have a considerably more general situation, which is of importance in algebraic geometry, which covers this, but I think it's comes to. Should I give some indications about what faithful flatness means now, or reserve it for some other time, and give the indications, because the proof is surprisingly simple. You don't have to play with indices and nothing. It just comes out almost trivially from the definitions. So should I give the definition? In fact, flatness is a very important note in algebraic geometry. We'll have to speak about it a lot when we speak about passage to quotient for group objects, for instance. And anyway, it deserves to be dealt with in a rather careful way, but let's give a few definitions. If A is a ring, let's say commutative or so, doesn't really matter. In N a module, then M is said to be flat over S and A module. By definition, if the functor N goes to M tensor AN, cancelling with M over A is exact. Now this functor is known to be right exact. Whenever we have an exact sequence 0 and prime and second 0, then the corresponding diagram M tensor n prime, M tensor n, M tensor n second is exact, but I don't put yet a 0 on the left. It's not true that an injection by tensoring with M in general is transformed into injection. And so we say that M is flat if this is exact also on the left, if M tensor n prime goes into M tensor n is injected, whenever n prime goes into n is injected. So it just means that tensor with M transforms into injections. Now, if we have an exact functor, that means that it commutes with forming kernels, co-kernels, images, co-images, etc. Means really that we are very much at ease when working with this functor. However, it means that if some things, this functor calls this T of n if you want, T lower n of n, it depends on the choice of m. This means that if we have some diagrams with respect to n, and if these diagrams have certain properties involving kernels, co-kernels, images, etc., then the corresponding diagram obtained after tensoring, applying the functor, has the same properties. But now we want a stronger property where we can come back again and conclude that if things are true after tensor with M, they were true before. And in terms of functional nonsense, this is nice. Functor will be nice in both ways if it's not only exact, but if it's more faithful. Now for an exact functor, to say that it's faithful just means that, do you know what perhaps I should define what a faithful functor is. So M will be called faithfully flat if and only if, by definition, N is flat, that's the first condition. And second, that is the functor Tm equals M tensor with an argument is exact. And second, this functor Tm is faithful. Now if I make an exact functor from an abelian category to another, to say that it's faithful means that if the image of an object is 0, the object must be 0. The two are equivalent. That's an immediate exercise to check that the two are equivalent. And then we find that in order for a morphism of n into n, of a module n into another n prime to be injective, respectively surjective, an epimorphism, a monomorphism, respectively epimorphism, respectively isomorphism, it's necessary and sufficient that after applying the functor, maybe after tensor with M, the corresponding morphism in the category of abelian groups, let's say, of A modules, should be a monomorphism, respectively epimorphism, respectively bimorphism. So, we know what it means for a module to be faithfully flat, and therefore, in order to check that a certain situation has of the case of A modules involving A modules Ni has a certain property, it's necessary and sufficient that the property should be satisfied after applying the functor Tm equals tensor with M. And now, if we have in algebra A prime over A, we say that the algebra is faithfully flat, if it's faithfully flat as a module. But this just means that what is now the functor n goes to n tensor A prime. This is just the base extension functor which goes from A modules to A prime modules. And to say that this functor is exact, viewed as being a functor from A modules to A prime modules is just the same as to say that it's exact as a functor from A modules to A modules. And the same with faithfulness. So here these properties of the tensor product functor are just properties of the base change functor. And if this functor is exact and faithful, then we will say that the algebra is fully faithful. And now we come back to the situation here. I claim that if A prime is fully faithful over A, then when we look at this diagram here of A prime, of A algebras, or A modules in fact, and if you tensor it with any module M, so for any module M I look at the module reduced by base change to A prime and to A second, and I have this diagram here, then this diagram is exact. In fact, much better is true. This is just here. This just means that M is isomorphic to the H naught of A prime over A M. And in fact, we can define introducing higher tensor products. We can define as a simplicial object in the case of A algebras, and the Hi of this solution M will turn out to be 0 in positive dimension. Never mind. So you have a complementary statement which says that Hi A prime over A M is equal to 0 for every strictly positive I. And the two are proved in fact simultaneously the following way. So it's a property for a sequence of modules over A. Here it means that the sequence of modules is exact. It means that if I map M into A prime into MA second by the arrow, which is the difference of these two, we have an exact, and if we put a 0 before here, we have a short exact sequence. Well, we have an exact sequence with 3 terms. And we want this, we want to prove that this is so, and for this, it's sufficient to prove it after we tensor with some module which is faithfully flat over A, or after we tensor with some algebra which is faithfully flat over A. So some algebra B here, which is faithfully flat over A, so that we get the same situation here, reduced from this situation by making the ring extension, but then B prime becomes an algebra over B, just as A prime was an algebra over A, and B second is just the tensor product of B prime by itself over B. So if we know that the property which we are looking for here is true after we make a faithfully full base extension, by forgetting about this situation and looking at modules over B, and looking at the sequence MB, MB prime, MB second here, then it will be true here too. Now what we will take is to take B equal to A prime. And I say in this case it's trivial now that the diagrams which you can construct from this situation must be exact. Because in fact, taking B to be A prime, we have made exactly the universal choice, so that now we have a section like this, that we have a homomorphism of B prime into B, B algebra homomorphism. But that's again some general nonsense about Czech homology, that if you have a section of, here it would be a section of spec B prime or spec B if you want. It would be a whole section if you work in the pattern of rings in fact. Then the Czech homology, of which we are computerization mode, is trivial. Namely, Czech homology is computed any functor, like the functor M transforms an algebra B prime into M tensor B prime. Here M, of course, is just the value of the functor on A. So if we replace A prime A second by B prime B second, it would be MB here. So that's a much nicer proof, and which gives a lot more. Okay, essentially, it gives the beginning of the yoga of basically Feld's descent in algebraic geometry. I think we should stop here, perhaps. So last time we interpreted in terms of quantitative algebras what it means to give a composition law an affine algebraic space G that turns it, let's say, into a monoid or into a group or something like this. Or what it means that such an object G, let's say an affine algebraic monoid, operates in another affine algebraic space. So such that the unit element will operate as a unit, and such that one has associativity of the operation. And also when we look at the functor defined by module M over K, by associating to every K prime the module MK prime as a functor in K prime. So we saw what it meant, how it was interpreted that G operates on this functor, or as we will say shortly, that G operates on M as this function is determined by M. We just say that G operates on M. Now, all what we wrote down was kind of just straightforward. It was just using a dictionary that we had set up before, just making it explicit in this particular case. Is there anything that wasn't clear that you would like me to explain more, or can we go on? Let's just recall the few features. If G is associated to the algebra A over K and X is associated to an algebra B over K, and the module is associated to itself, then to give the composition law on G, namely to give a map from G times G into G, means that we can have a homomorphism, an algebra homomorphism pi from A into A tensor A. And to say that we have an action of G satisfying a bunch of axioms, which I will not write down again, it will take the hour again, I'm afraid. That G operates on X, we have seen, amounts to giving an algebra, namely that G times X is mapped into X with certain axiom, means that we have a homomorphism from B into B tensor A or A tensor B, as you might prefer. I like to write it B tensor A, however. Maybe I'm wrong, but so called as omega. Omega is the initial of operation, together with some axioms. In fact, one axiom is that this is an algebra homomorphism, of course, and then there are two more axioms. So this is kind of self-evident. We are always speaking of algebra homomorphism in this context. And let's write down the other two axioms. Or let's do it for M, because they will be the same as in the case of M. So now what does it mean that G operates on the module M? This means that we have a homomorphism but of modules now from M into M tensor A, satisfying some axioms. And it turns out, call this U naught if you want, and it turns out that these two axioms are the same as those which we have to put here. The only difference is that here we assume B to be an algebra and this to be an algebra homomorphism. In other words, what this could be seen a priori, to have G operate on X is the same thing as have, let's say on the left is the same thing as to have G operate, one has to distinguish sides, as to have G operate on the right on B, on the affine algebra of X, in such a way that the algebra structure is respected, which just means that this homomorphism is a homomorphism of algebras, not only of modules. Now let's write down the axioms for an action of G on M. So perhaps we should, however, say how is giving such a map. We should recall how this allows us to make G operate on M. So we have to show how, if we have a point of G with values in K prime, how this defines the homomorphism Gm, which goes from M lower K prime into M lower K prime. So we have to define this Gm in terms of this homomorphism. So what we do is that to give a homomorphism from Mk prime into Mk prime, a K prime linear homomorphism is of course the same thing as to give a K linear homomorphism from M into Mk prime. So in fact, it's the same to know Gm or to know its restriction to M, let's say, through this canonical homomorphism, which we might call Gm naught, something like this, upper naught, which means that we restrict to M. And so it's Gm upper naught which we'll define. G element of Gk prime is just a ring homomorphism, an algebra homomorphism, I'm sorry, from A into K prime. So that's our G. So we can do it here as being from A into K prime. And therefore, if we take the identity in M tensored with G here, we get a homomorphism from M tensor A into M tensor K prime. So this is identity in M tensored with G. And when I look at the compositum of this with U naught, I get what I was looking for. In a way, U naught was just this map GM naught from M into M prime in the, so it's a universal case, and we took K prime to be the group algebra, to be the affine algebra of the group G. Alright, so this is here, I hope, and now let's write down the two axioms which express that the one element operates on any element at any point of the functor M, K prime at a point as the identity, and the fact that G prime X is equal to X. Yeah, all this stands, of course, for the relations obtained by taking any points within any K prime. So the axioms are expressed in terms of primitive algebra in the following way. If you look at U naught, which goes from M to, call it rather delta now, or U naught, because there will be no U anymore after a while. So maybe delta M, that's the diagonal map for M, let's say. From M into M tensor A. And if we look here, well, we should take here G equals 1 in here, that corresponds to the fact of the natural augmentation of our algebra A. So I take identity M tensor by epsilon. This compositum here should be the identity. So that's the first axiom that says, and now let's see the second. One has to map M into M tensor A by delta, and this we map into M tensor A by the identity on M tensor with the co-multiplication on A, and we can also map, we can again map M into M tensor A by the same delta, and now we have another homomorphism of M tensor A into M tensor A by delta, which is a homomorphism of M into this factor here, and I tensor it by the identity in A. Alright, and this diagram should be commutative. Now I think that I did things correctly, and this does in fact express this axiom that the group G operates on the left on M. If I had the opposite axiom where G prime, what? This is a strange axiom. If G applied to G prime X is equal to G prime GX, namely if G operates on the right on M, then we would have the same, this axiom would be expressed essentially the same way, except that this arrow here would be the following. We map M into M tensor A, but taking these two factors and tensoring it by the identity on A, but putting it in the middle. So that means that instead of taking the arrow that is written down here, we take this arrow followed by the identity on M tensored with the symmetry on A tensor A. Alright. And in fact, it's, I think, useful when speaking about, even when speaking about algebraic groups over K, to take also the case of modules, because this forces us to be careful about the sides left and right. On a group, we don't have to distinguish too much about operations on the left and on the right, because one passes from one to the other by the antipodism G goes to T minus 1. But for monoids, there's nothing such, and one has to be much more careful about what one is doing. And I mean, it's kind of good to see formulas where we don't have to introduce G minus 1s. All right. And the remark we made, and I want to emphasize a little more on this, I think that's worth it, is that in fact, if we have a monoid, let's say, over K, an affine monoid over K. Therefore, we have an algebra over K with this co-multiplication, and if you have a module M over K, then to let G operate on M on the left, let's say, is something which does not depend on the algebra structure on A, but only on the coalgebra structure on A. Namely, it's given by a homomorphism from M into M tensor A. Now, this makes a sense to say this without using the algebra structure of A. In such a way that these two diagrams are commutative. Now, these two diagrams never make use of the algebra structure of A. As I written there. And we said that if we have a coalgebra A, namely over K, namely a K module over a K module endowed with a K linear homomorphism like this, never bothering about whether A has a multiplication to it, just a module with a multiplication, satisfying which axioms, or the two axioms which correspond to unity and associativity, which we will come back to it a bit later perhaps. Then we will say, so it involves, for instance, unity involves that we have an augmentation epsilon from A to K, which plays the role of a unit, which corresponds purely when there is a group G giving rise to A, it corresponds, or a monoid, it corresponds to unit section. All right. Then we will say that the module M over K, that if you have a module M over K, we will say that we will call a co-module structure over the coalgebra a structure like this of a homomorphism from M into M tensor A, following satisfying these two axioms. Well, this is called the unity axiom, and this is called the associativity axiom. We will say also that the coalgebra operates. Well, let's say on the left, on the right, what should we say? On the left, let's say. Yes. But the coalgebra operates on the left on M if we have these axioms, and if it operates on the right on M if we have the symmetric axiom instead here. And now I want to interpret this notion in terms of functors again. That's really the best way, I think, not to get mixed up in the errors and to give the proofs without getting mixed up in the diagrams. You see, because they are not transparent, these diagrams. So, and therefore, what I'm going to say is the following: that to give on a K module A coalgebra structure is the same as to give on the module function that represents V of A, which associates to every algebra K prime the set of homomorphisms of A into K prime, but now not of algebras, because A is no longer an algebra, just the K linear homomorphism. This was the function we called V of A when A was any module over K. So I say that to put a coalgebra structure on A is the same thing as to put an algebra structure on VA, algebra, over the canonical ring functor O, which transforms K prime into K prime. So this makes the meaning of it very clear. And what about the comodules of a coalgebra? I state that M is a comodule over the coalgebra A, if and only if, let's be clear about which side, the left comodule, let's say, if and only if V of M, now be careful that V of M depends contrariantly on M. So we would expect this to be a right module under something. So Vm is a right Well, Vm is a right VA module. In a way compatible with, of course, with its O module structure. So a priori, you see V of M is an O module, according to our definition, and we replace just A by M. And VA is an O algebra. And you know what it means, that the O module structure is extended to a VA structure, the structure of a module over the algebra. So we are going to make this point of view explicit now, and so let's see. Assume we have to forget about I and M for the time being, and assume we have three modules P, Q, and R. I want to interpret homomorphisms of R into a tensor product as being pairings Vp times Vq into Vr in the opposite direction. Pairings, of course, understood, that are O-linear. Or in other words, I want to define a bijection between the homomorphisms, which are K-linear, from R into the tensor product P tensor K, and the set of bilinear maps from Vp times Vq into Vr, bilinear over O. We could write it also as the linear homomorphism of the tensor product of the two functors. So hom over O, if you prefer, Vp tensor Vq into Vr. The tensor product is just defined because we are working kind of pre-sheaf, it's just defined argument-wise. All right. What is really important for us, for the interpretation we're going to make, is that we have this homomorphism, and it turns out that this homomorphism in fact is bijective. Otherwise, if you didn't know it was bijective, all we could say is that if you have a co-algebra, then VA carries the structure of an algebra functor. But in fact, it turned out to be bijective. Now, I don't think I'm going to give the proof here. I will just define the arrow. Now, all right, so I assume that a homomorphism like this is given. And I want to define from this a pairing like this. So I take a ring, an algebra K prime over K, and I want to define a pairing K prime linear of Vk K prime times Vq K prime into Vr K prime. K prime the linear mapping. That has to be defined in terms of the homomorphism U that was given here. Now, a Vp K prime is just the set of homomorphisms that are K-linear from P to K prime. The other is a set of K-linear homomorphisms from Q to K prime. And here we have the set of homomorphisms that are linear from R to K prime. All right, so we have now to see how, if you have a homomorphism from P to K prime and another from Q to K prime, how to define one from R to K prime. And in such a way that depends bilinearly on this pair. But if you have these homomorphisms, we define a homomorphism from P tensor Q into K prime tensor Q. Let's say that we have an element alpha here and element beta there. I take here alpha tensor beta, which goes to k prime tensor k prime, and I follow it with the multiplication homomorphism, which goes from k prime tensor k prime to k prime, which transforms x tensor y into xy. Call this here what do I know? P. And I get a homomorphism from p tensor q into k. So I will, and that will be it. So the image of alpha comma beta will be p composed with alpha tensor beta, which is clearly bilinear with respect to alpha and beta. Right, so in this way, I get an arrow, and it turns out that this arrow, in fact, is even bijective. So this, now let's specialize the situation to the case when R, P, Q are all equal to the same module A. So then it means that to give a homomorphism from A into A tensor A implies, in fact, is equivalent to giving a pairing from VA times VA into VA. When I say pairing now, it always means with respect to the O module structure. So it means that we have an algebra structure on VA, except that so far we don't put any X function on an algebra structure except by linearity. And now the fact that this comodular structure is unitary just means that the algebra structure admits a two-sided unit. You just repeat the diagram in terms of the functors. You see we have this complete correspondence between modules and the corresponding functors Vm, so that everything can be interpreted. And to say that our co-multiplication is associative just means that the composition now here is associative. And so both together just means that we have an associative unitary algebra, which is really what we like to have. All right, so this much for A. And now what for M now? What does it mean that we have a homomorphism of modules from M into M tensor A? We are given K module M. This means that we have a pairing of Vm times Va to Vm. So this means in a certain sense that Va operates on Vm with using Vm. And now, assuming that A is a coalgebra, namely that Va is an algebra functor, this axiom here means that the unit element of this, or the unit section, let's say rather, of this algebra functor operates as a unit on Vm. And this axiom here means that we have associativity so that Vm becomes a right module over the algebra Va. So to give a left comodular structure on M over the coalgebra A is the same thing as to give a right module structure on the functor Vm over Va. And in this here you see the groups that we had used in order to come to such coalgebras completely vanishes. There is no multiplication anymore on A. Now I wanted to develop this sugar little cursor. So I go on forgetting about G, the existence of some G. For the time being, I won't assume any algebra structure on A, just coalgebra structure. Now let's look at VA which is an algebra functor. Let's look at its values. On K, this is just H hash. That's the dual of the K module A. I note the dual by hash here. So this is therefore a K algebra. Sometimes it's called the algebra of distributions of the co-algebra A. We will develop this terminology in the case when A is a ring, an affine ring of an affine algebraic space. So you should think of these elements of A hat as distributions on an algebraic space, for instance. All right. And of course, if M is a left commodule as before, then Vm is a right module functor over Va, and a fortiori the algebra Vak equals A hat will operate on the right on this functor. So Vm will be, as a functor, will be an H hash module. It will be a functor with values in capital of H hash modules. Vm is a right H hash module, where H hash stands, if you want, and for the constant K algebra H hash minutes, it's a constant functor. And on the other hand, we know that Vm and M determine each other mutually, meaning that in fact Vm is a dual of Wm, and Wm I mean is, and M determine each other mutually. Wm comes from M just as Wm, and M comes from Wm as the values of Wm on K. You see? We get that this means also that Wm, let's say first this, because Vm and Wm determine each other mutually but in a continuant way, is a left H hash module, or what amounts to the same. In other words, H hash operates on this functor Wm on the left in a k-linear way, or what amounts to the same. M is a left H hash module. So whenever we have a co-module M over a co-algebra A, well then it defines a module functor over an algebra functor, but it even defines a two-honest module without functor, anything, over a well-determined algebra. And it defines that M itself becomes a module over the K algebra H hash. The module structure of M over H hash, of course, being compatible with its K-linear structure. And now we want to make a little gymnastics of seeing how far does the comodal structure, can the comodal structure be reconstructed from knowing the module structure of M over H hash, which now is just a usual module structure without even speaking of functors. In general, remember, you see, I will have to make extra assumptions on the module M over the ring A. Remember that in general cases, if we don't make any extra assumptions, we can reconstruct the comodal structure from just giving the module structure on M over H hash. We should know, in fact, the module structure not only over H hash, which are the points of VA with coefficients in K, but we should know it also the operations on M lower K prime for every element of VA with any K prime, whatever. By the way, hey, something which I should have said, perhaps when I said that M is a left co-algebra, co-module over A if and only if Vm is a right V of A module. Well, this can be also interpreted as saying that Wm, which is a dual of V of M, and of which V of M is a dual, is a left V of A module. You can say it this way. W of M, remember that's a functor. K prime goes to M tensor K prime. And so here what we are doing by looking at this module M over H dash it is that we are just looking at the module structure which we obtain when we take K prime to be equal to K. And in general, that's not enough to reconstruct the whole story, but in some cases it is. And now these cases, and I want to make explicit. I should perhaps also make explicit in terms of the diagram how an element of H dash operates on M. It's pretty trivial, of course, just follows the definition. So the structure of M is defined by M tensor, M goes to M tensor over Ka. Now, assume that we have an element psi of H dash. That means a linear homomorphism of A into K. Psi goes from A into K. And therefore, define the homomorphism from M tensor Ka into M by taking just the tensor product of the identity on M with this homomorphism psi. And the homotopy defined in M by this element of the ring of operators is just a composite term. This here is the action of psi on M. That's all. Now, yes, let's make a very restrictive assumption first before getting a little more sophisticated. And let's first assume that A is, as a K module, which is projective of finite type. So this implies that H dash as dual also is projective of finite type, and that we can recover A as being the dual of its dual, essentially to say that biduality holds. Anyhow, you assume A to be projective of finite type. All right. Now, when this is so, then to give a homomorphism of M into M tensor A, you see, is just the same thing as to give a homomorphism of H dash into hom MM. Everything K linear. Because M tensor A can be interpreted in this case as being just hom over K of H dash and M. And to give a homomorphism of M into a hom is the same thing as to give a homomorphism of M tensor H dash into M, and reversing the direction of the product is the same thing as to give a homomorphism of H dash into hom and M. That is, it's the same thing to give a homomorphism of M into M tensor A, the same thing as to have the K with the H dash operate on M the same as in M. And now, of course, if A is a coalgebra, then a homomorphism from M into M tensor A turns M into a, let's say, left co-module if and only if the operation of H hash on M, which we get here, turns M into a left modulo by H hash. And therefore, in this case, A being K-module projected of a finite type, we see that it's equivalent to give a structure of a K-module on M, or to give a structure of a co-module, left co-module. I'm sorry, to give the structure of an algebra, I'm sorry. If A is projected of a finite type, it amounts to the same to give on M a K-module. A structure of a left co-module over A, or to give a structure of a left module over the algebra, H hash. So in this case, the 2 points of view are completely equivalent. The M here has disappeared from the picture. We are just not working with functors now, but with K modules. Now let's generalize this somewhat, and we will assume that A is the direct sum of projective modules of finite type. For instance, A is a free module over K, which will be true if, for instance, K is a field. So what we will say now will be applicable if K is a field. Now, let's see. How we will then do things. I want to generalize this formula here. Let's even put an n here, if you want. And n, any 2 modules, m and n over k. I will consider now H hash. This is a K module, but it's a topological K module. It's a topological module. In fact, A being a direct sum of projected module of finite type, by taking the finite subsums, we get that A is a direct limit from a set of indices alpha, let's say, of submodules A alpha, which are projected for finite type. And H hash will be therefore the inverse limit of the R alpha Chechens, and here not only will be the transition morphisms, because of the way in which the direct system A alpha was obtained, the transition morphisms in this inverse system are surjective, so it's a strict inverse system, but also the homomorphisms of the inverse limit to each of the factors A alpha are surjective. So the A alphas appear just as quotients of H hash here. And now, when A is not a finite type, like here, but let's say, for instance, such a direct sum of projected modules of finite type, it's important to keep in mind that H hash has a topology, namely the inverse image topology of the discrete topologies on each of the A alphas. It can be also interpreted as being, in terms, if you view H hash as a functional space of k-linear functions on A, it's the topology of the simple convergence. All right. And now, this formula here will be true provided we replace homomorphisms by continuous homomorphisms. So the formula is that we get here continuous homomorphisms of H hash into hom k and m, where I guess here we have again to take the topology. What is it? Yes. Of simple convergence. Let's say what it means. That we have an element in here. It means that H hash operates on M with values in M, that we have a pairing H hash times n goes to m. And that means that for every x in n, the corresponding map which associates to every psi in H hash, psi applied to x, which is an element on m, which is a map from H hash to m, should be continuous when we put on m the discrete topology, namely that this map should vanish on one of the kernels of H hash goes to A alpha, or otherwise stated, it should be factorizable through one of the A alphas. Now, so we have this formula. It's a little exercise to establish it's true. Maybe it's not. I will not prove it here. I mean, it's a little exercise in linear algebra. Now, this formula shows us that the homomorphism from n into m tensor A is known, can be reconstructed when we know the corresponding x of H hash on n as well as in m. In fact, we get exactly those actions of H hash on n as well as m which are continuous in the sense I made precise. These correspond exactly to these homomorphisms. And now let's take the case where n is equal to m. So to give a homomorphism from m into m tensor A is the same thing as to have H hash operate on m in such a way that the property written down here of continuity should be satisfied. Operate in just linearly, so to say. And now what does it mean that this morphism satisfies the axiom number 1, which we have erased? It means that the one element of H hash operates as identity. And what does it mean that the axiom number 2 is satisfied? It means that H hash operates on M in an associative way. That means the two together, that M is in left algebra over H hash. So here it amounts to the same to give an algebra to give a structure of a left comodule on M over the coalgebra A, or to give on M a structure of an left H hash algebra in such a way that this action should be continuous. That for every x in M, the map psi goes to psi x, which goes from H hash into M, should factor to one of the A alphas. So it's a continuous action of the algebra H hash on the module M. Now, what about giving the co-module structure, the co-algebra structure in the first place on A? Now, assume that K is not as yet a K algebra over K, but we still assume that as a module is the direct sum of projective modules of finite type. Now, what does it mean? How can we express a co-algebra structure on A, namely giving such a homomorphism in terms of an algebra structure? I can that this is the same as to give on H hash an algebra structure if we don't make any axiom on this error, with some continuity conditions, which I will make precise. So it's a continuous map from H hash times where the product is a continuous bilinear operation. If I don't make any axiom here, I won't have any further property here. The axiom that this co-algebra structure is unitary means that here we have a two-sided unit, that's the element epsilon of A check, which is an augmentation of A, and to say that this codiagonal map, this diagonal map is associative, just means that's the algebra structure here. It's associative. So the two together, so to say that A is a co-algebra in the more restrictive sense, unitary and associative, just means that A check is a topological algebra. So we have to prove this correspondence, which is now again a thing of pure linear algebra. It comes from the fact that if, which I will just state, I will not prove it because it's just little chasing around with limits, with diagonal inverse limits. If P, Q, and R are 3 K modules, that's it. Which each of them satisfies the same property as A. And each of them are sums of projective modules of finite type. Sums of projective modules of finite type. Then, to give a homomorphism of R into P tensor Q, this of course defines a homomorphism from a bilinear homomorphism. Let's say, I don't have too much to write down tensor products here, of P check times Q check into R check, and in fact it's not only bilinear, it's continuous. So that's in fact always true without the assumptions on the modules. Every homomorphism from R into P tensor Q allows us to define such a bilinear pairing which is continuous, and if PQR satisfies this rather strict condition, but which is always true when you're working over a field, then this here is a bijective homomorphism. So to give a morphism of R into P tensor Q is the same thing as to give a pairing of P, a continuous pairing, bilinear pairing from P check times Q check into R check. And so this if A, let's once again sum up what we have obtained so far. In the particular case when A is a direct sum of projective modules of finite type, then to give a co-algebra structure on A with the axioms that we like, unitary and associative, is the same thing as to give an algebra structure on A check that is continuous, where the composition was continuous. And if M is a module, to give a left comodule structure on M is the same thing as to give a structure of a left module over A check, which is continuous in the sense I have explained, such that psi goes to psi x is a map from A check into M is continuous, whatever the choice of x. And now, let's apply this to studying subcomodules of comodules and quotient comodules. Now, for the moment, let's assume A is just a general coalgebra. Okay. I don't assume any particular other property like A being a direct sum of projective modules of finite type. I just assume it's a co-algebra. And I assume that I have also a comodule M over it. And now let's look at the situation with a submodule and a quotient module of M. And I want to see, to define what it means that m prime or m second are stable under the action of the co-algebra, or that they are sub-comodules or quotient comodules of M. Now, there are various ways of doing so. Let's look at the corresponding morphisms for the functors v, vm second. The modular functors vm second is mapped to vm, is mapped to vm prime. Now, things are particularly nice for m second, because m going to m second being surjective, it's clear that vm second goes to vm is injective. Remember that the points of vm seconds are just so k-linear homomorphisms of m second into some algebra. What do I know? Into some algebra or k prime. And the points of m are the homomorphisms from m into k prime, and of course, because this is surjective, a homomorphism from m second into k prime is known when we know the compositor. So the functor vm second is embedded in the functor vm. In fact, it's a closed inversion of affine algebraic spaces. That's it. Because the symmetric algebra of m is mapped surjectively to the symmetric algebra of m second. But never mind. We don't care whether these functors are represented or not. Alright, so it makes sense to say that the subfunctor of the functor Vm already being an module over Va, that this is a submodule, and it's stable under Va. When this is so, we will say that the quotient module m second is stable under the comodule structure. So let's introduce m second is stable under comodule structure. Definition: if Vm second contained in Vm is a sub Va module, and then there's a unique induced module structure on Vm second over the algebra Va, which will turn therefore m second into a comodule over A, which, and this comodule structure will be called the quotient comodule structure. Now, in terms of diagrams, the comodule structure on M was given, here it is, by delta over M, by this diagonal map. And if we express things diagrammatically, we see that the fact that m second, the quotient m second is stable, just means that we can find a homomorphism from m second into this tensor product, which makes the diagram here commutative. If this is so, because m goes to m second is surjective, the axiom of unitarity or of associativity, which is satisfied here, will be automatically satisfied there too. And therefore, m second in its own right will be a comodule. And we see at once that the inclusion of Vm second into Vm, because of functionality of this business, is induced by the module structure of Vm. So here there is no difficulty whatever. But now what about m prime? Unfortunately, it's not true in general that if m prime is injected in M, that Vm goes onto Vm prime, for instance. Certainly it doesn't go. If this was surjective, then it would make a good sense to say that Vm prime is a quotient. That the algebra structure on Vm is compatible with this surjective homomorphism. That's the constellation defines is compatible with the module structure of this algebra, and therefore passes to quotient. We can take things in the other way around, and we can look at the diagram Wm prime goes to Wm goes to Wm second. And this now goes to 0. Where the Wm's, I recall, Wm is a functor which associates to every k prime m tensor k prime. Now, because tensor product is right exact, this here is surjective, but this may not be injective. And we are faced with the same difficulty. If this was a subfunctor, if m prime goes into m was so injective that it remains even injective after tensoring with any k algebra, so if this injection is a universal injection, then it would be pretty obvious how to define stability. It just means that the subfunctor of Wm is stable under left multiplication by L's of points of VA. All right. So what should we do now? Well, we can always, of course, put a definition and then point out that the definition in general is perhaps not too handy. We might say that we might look at we may say that M prime admits an induced comodule structure. Let's say it this way: if we can find a comodule structure in prime such that the arrow goes from M prime into M should be compatible with the homomorphism of comodules. Let's say it this way. Now, what does this mean? This means that we can find a homomorphism of M prime into M prime tensor A, delta M prime, in such a way that the diagram here commutes. Now, if we only knew that this homomorphism here is injective, it's deduced from M prime goes to M by tensoring with A. It may not be injective, but if you knew that it's injective, then of course this delta M prime will be uniquely defined. And so there will be a unique induced structure. And otherwise, there may be several. I have not tried to make an example here. I think it's safer not to speak of induced structures except when we know here that we have injectivity. And now I will give a few examples where we have injectivity. So, but before doing so, let's make a comment that in this case, you see, we have vertical exact sequences here. That is, we have a submodule M prime tensor A of M tensor A, the quotient being M second tensor A, and we have a homomorphism delta M of M into M tensor A. Here we have a submodule in the quotient, here we have a submodule in the quotient. It amounts to the same to saying that the homomorphism transforms the submodule into the submodule, or that it transforms the quotient into the quotient. So it amounts to the same that M prime is stable, or that M second is stable. So in this case, the notion of stability for the submodule or for the quotient, they correspond to each other. Now let's give a few examples where we have this injectivity. Perhaps the most important one for application is the case when A is flat over K, which just means that tensoring with A transforms monomorphisms into monomorphisms. But then we can say a little more. Then we can say that stability of submodule, stability of submodules M prime, submodules M prime for the co-algebra for the co-module structure is stable under sums and finite intersections. I guess also finite intersections, by the way. Let's see. Yes. No, it's not finite intersections. That comes from the fact that the functor m goes to m tensor A will be an exact functor, and therefore it will transform sums of submodules here to sums of submodules here, and intersections, finite intersections, I'm sorry, of submodules here into finite intersections of submodules here. That it works for arbitrary sums comes from the fact that the functor here m goes to m tensor A computes also with like limits, not only with finite sum. All right, and from this, the conclusion here follows. Brilliant. All right, other two examples are the ones where m second is flat over k, and third example, when m prime is a direct factor. Now, these two cases, they're not too handy, you see, because they're specific to the module m. And I like condition which is true for all m, so that one is safe. So let's rather look at this condition here. And now I would like to interpret this stability in terms of stability of a usual module structure and an HH. But perhaps before doing so, I should make a comment. And what stability means when A does correspond to an algebraic monoid. So that means if A has a structure of a commutative algebra such that pi is an algebra monoid at the same time. So then as we said, the K module, the left A modules, the left comodules of A, they are just the modules over K on which G operates on the left. And through the interpretation with these diagrams, it's evident to see that if you have such an exact sequence of modules, it amounts to the same to say that the m second as a quotient of m is stable for the comodule structures, or to say that this quotient is stable for the operation of G on M. Namely that there exists an operation of G on M second, such that this homomorphism should be compatible with these operations. If this is so, that the operation of G on M second is uniquely determined. And the same thing for this inclusion, to say that M prime is stable in M under the co-module structure just means that there exists an operation of G on M prime such that M prime goes to M is a homomorphism of compatible with the action of G. But there might be, of course, several actions of G which have this property, except when we make an assumption of injectivity here. And here the important property is that ensures is that A is flat over K, or as we say also that the algebraic affine algebraic space G is flat over K. This doesn't depend on the composition law, this depends just on the underlying affine algebraic space. Alrighty, now let's come back to the case when A is not only flat over K, but let's now assume that A is again a direct sum of projective modules of finite type. By the way, what I said here for finite direct sums of projective modules of finite type might be true whenever we have a projective module, but I couldn't prove it. I'm not completely sure it's true. Maybe it's known. I'm not too sure about it. That might be. Is it true that a projective module is a direct sum of projective modules of finite type? Well, then all the better. It's a nice term. That would be a beautiful term.
Yeah, it is.
Yeah, projective modules are really very, very special.
Oh, no, countable generator, a direct sum of countable generators. Every projection has a direct sum of countable generators.
That's nice, but
No.
I would think it's true for any molecular modules. They are so very special, but never mind. I think we are mainly interested in what happens over a field after all. So then we have some leeway. Then I claim that, so let's recall that in this case, to give a co-module structure on M over A is the same thing as to give a structure of a module over the algebra HH. And we will see immediately that M prime, this sub K module of M, is stable for the K module structure if and only if it's a submodule for the HH module structure in the dictionary that we have set up. Use it immediately in this case. Now, I want to deduce some corollaries of this by making this assumption here. So let's see. Corollary 1. For every sub K module, M prime in M, there exists a smallest sub K module, let's call it M prime Czech, M prime BK, sorry, containing M prime and stable for the co-module structure. Let's just say the smallest sub-co-module of the given co-module. And we obtain it in the following way. M prime BK is just the sub HH module generated by M prime. Now this statement here is trivial once we have said that the sub-comodules are the submodules over HH. And what we are mainly interested in for this is that if M prime is finally generated, then M prime as a K module, I want to say over K, then M prime Czech is also finally generated. It's a module of finite type over K. Why is this? All right, if M prime is finally generated, so it's generated by xi's I between 1 and n, and the module, the sub HH module generated by M prime is just the sum, direct sum of the sum, I'm sorry, not the direct sum, of the submodules HH xi. But each HH xi is a submodule of finite type, because remember that the map xi goes to xi x when x is fixed in M is a continuous map which factors through some E alpha Czech. And E alpha Czech is a projective module of finite type. In fact, if you look at the smallest sub-K, if you look at the smallest sub-co-module generated by 1 point, for instance, it's just HH, that is the image of the map xi goes to xi x. And if this sub-module, call it, what do I know, call it xpk if you want. It's immediate to see it's also the smallest submodule of M such that delta of x, which is contained in xpk tensor A. There exists submodules of finite type in M such that that delta x is contained in all, let's say, capital N tensor A, but there's the smallest one. This is, and this is just x bk, so that's another way of getting it. And therefore we get as a second corollary that any comodule is a direct limit of subcomodules that are finite over K. It's the filtering direct limit of subcomodules Mi finite over K. That means of finite type over K. So this much for M. So if you like to go back to the case when A corresponds to a monoid, to a finite algebraic monoid, this means that when the monoid G operates on a module M, assuming that the algebra of this affine algebra of the monoid A is a direct sum of projected modules of finite type, which will be true over a field, then M is a direct limit of submodules which are stable under the action of G and which are finite type over K. So if K is a field which are vector space of finite type, which are vector space of finite dimension. Now let's look at the case where M is equal to A itself. So A is a coalgebra, it is endowed, it's a diagonal morphism, and using this diagonal morphism we can view A as being a coalgebra, as being a comodule over itself in two ways in fact, either writing M equals A and putting M on this side, or if I dare say putting M on this side, namely composing pi with a symmetry here. On the one hand, one would get a left comodule structure, on the other hand, one would get a right comodule structure. Another way of viewing this, we have to see that V of A operates on V of A on two sides, but V of A is an algebra functor, and the algebra operates on itself on the left and on the right. All right, so we should view a comodule, we should view any coalgebra A as being a comodule over itself in two ways. There is the left canonical representation, the left regular representation, the right regular representation. And now we can repeat what we have said here for these representations. In fact, I like to view A as being a bi-comodule, if I dare say, over A, with left and right operations together. And I'm interested in submodules B of A, which are stable under both the left and the right law. And now we could, if you wanted, apply this corollary to this situation, because to give this pi structure just means that we have a structure of a comodule over the tensor product of A and the opposite of A. So there would be such a reduction possible. I don't want to make it explicit, but we could also directly, if you don't want to make the Sourit, the little Sourit about tensor products of comodules, which is kind of trivial anyhow. We could also repeat this argument replacing M by A, and we would find the following, that for every sub K module B of A, there exists a smallest submodule BK containing B and stable under both comodule structures, the left and the right one. Namely, we just take the we just view A as being now a module over the algebra H hash, both on the left and on the right, and I take the sub-bimodule generated by B. That's all. And if B is of finite type over K, if B is finite over K, then by the same token I see that B BK is also finite over K. I always make, of course, the assumption that A is the direct sum of projective modules of finite type in this here. So that stability is expressed in terms of stability under a module structure. And now I want to express what it means that a K module in A, contained in A, is stable under the left and the right operation. So let's see what it means. To say that it's stable on the left operation means that if you look at the morphism induced by on B by pi, it maps B into B tensor A, means that B is stable on the left operation, so the M was here before. And the other symmetric condition, that B is stable under the right operation, means that pi induces something contained in A tensor B, where B now is put on the other side. Alright, but here we are taking tensor product over K. But because A is flat over K, we know that this intersection must be equal to the K. Is it so or not? Let's see. I want to write that this intersection is just the tensor product of B by B, K. So this is contained in here because A is flat on the right, and this is contained in there because A is flat on the left. And what about this? We don't even know that it's contained in here. Therefore, we better now, let's assume that we know that B tensor B. We want to have no trouble. Yeah. So what have we to assume? Assume that this exact sequence 0 AB, B over A 0 is universally exact, remains exact by tensor with anything. Which this would be true if B over A is flat also. And now we are out of trouble if K is a field. So assume B over A, I'm sorry, A over B is so over this way. So if A over B is flat, then the intersection of these can be interpreted as B tensor B, which then happens to be contained in A tensor A. And then we see that the fact that B is stable under both operations left and right just means that B is stable under the diagonal map of together, under the, that's it, under pi. That means that the induced structure of a coalgebra on B. So these are just what we could call the sub-coalgebras of A. And so we see that with the assumption we made here, well, the assumption made here, let's be now honest, and let's assume K to be a field, so that then we know that any vector space is direct sum of projective of finite type is field. Right. Then we find the following thing, that any coalgebra over vector space K is the direct limit of subcoalgebras which are of finite dimension over K. So this gives now a last 411 if you want. K is a field. Any coalgebra A by K can be written as a Dieck limit, filtering Dieck limit of sub coalgebras AI finite over K. If you want to express things dually in terms of H hash, which was defined as a topological K algebra, you see, it was an inverse limit, it was linearly compact, it was an inverse limit of finite dimensional modules over K, of modules of finite type over K, here of finite dimensional vector spaces. It wasn't clear a priori that these quotient spaces could be taken as quotient algebras. However, that's what turns out now. H hash is the inverse limit of, AI hash can be viewed as being the inverse limit of algebras over K that are finite over K. The transition morphism, of course, being surjective homomorphism. And so homomorphism of H hash onto each of the AI shapes being surjective. Now, let's come back to the geometric situation of schemes of groups and schemes of monoids. Affine algebraic groups and affine algebraic monoids. We get the following proposition: let K be a field, and let G be an affine algebraic monoid. By K, respectively an algebraic group. Then we will have a stronger conclusion. So first of all, G can be written as being the inverse limit, filtering inverse limit of GIs, monoids, algebraic monoids, respectively groups, algebraic groups, and makes a strong assumption before, where each of the GIs is of finite type over K. Here the indexing set I is filtering. And B, if G is already of finite type, there exists a closed immersion of G as a subgroup of the full linear group of order n for a suitable n. So a group homomorphism, a monoid homomorphism here, it's just a monoid to the closed immersion. So every affine algebraic group which is of finite type can be realized as a closed algebraic subgroup of the full linear group in n variables. And for monoids, they're the same. It's a closed submonoid of G and n for suitable n. Now, let's prove this. We'll just take, I think, a few minutes and then go through. So G corresponds to a bialgebra. It's a co-algebra which is over an algebra, and the sum of this entire goes to A tensor. A goes to A tensor A as an algebra homomorphism. I know already that A is the Dieck limit, filtering Dieck limit of its submodules Mi, which are sub-coalgebras. Namely, which are stable under left and right translations. Now for every Mi, look at the algebra it generates in the sub-K algebra it generates in A. this is now an algebra of finite type contained in A, and it is clear that this algebra will be stable also under left and right translations. Which means that AI is both an algebra and a coalgebra. Therefore it corresponds to a monoid GI. And to say that A is a like limit of these AIs of finite type just means that G is the inverse limit of the GIs. Now what about the case when G is a algebraic group? I contend that now I can take the GIs to be also algebraic groups, which just means that the AIs are stable under antipodism, which we have in A. But of course, if you have a submodule M in A, then sigma M, the image of the submodule by the antipodism, which is of square 1, you see sigma is equal to identity. Then sigma M is another submodule of the same dimension, so and M plus sigma M is stable under sigma now. On the other hand, to say that M is stable under left translations and the left operations of G just means that sigma M is stable under right operations. And to say that M is stable under right is to say that sigma M is stable under left ones. And so if M is stable under both, sigma M is stable under both, and the sum is stable under both. In other words, these MIs here could be chosen to be not only sub-coalgebras, but sub-coalgebras stable under the antipodism. And then the algebra that generates AI also stable under the antipodism, which means that the GIs are groups. Alright, now what about this here? Well, the idea is essentially the same. If A is already a finite type, then we can generate A as an algebra by sub K module of finite, by sub K module of finite type, which we may assume to be stable. Here it would be suffice under, let's say, left translations. Therefore, the regular operation of G on A by left translations induces a linear transformation, a linear operation of G on M. In other words, we get the homomorphism of the monoid G into the monoid odd M, which if N is the dimension of M, is just the monoid G and N. And now I contend that this is a closed immersion. And, well, this must be essentially trivial now. In other words, if I have the homomorphism which goes from the affine algebra of this group variety to the affine algebra of G, this should be surjective. Now, in fact, this is contained in, not as a subgroup, but as a sub-affine algebraic space in affine space of dimension n squared on the underlined M, the functor of endomorphism of M. And in fact, what I say is that the compositum, even this here is an open immersion. What I say is that the compositum here is in fact a closed immersion. In other words, that the morphism on the rings from here to there is surjective. What will be evident is that the homomorphism on the rings here will have an image which contains M. So let's write this now. And as M generates A as an algebra, we will be through. Now let's write this. Let's phi be an element of M. Let's show that phi is in the image by just writing it in the natural ways being in the image. So let's look at G applied to phi, where G is a variable element of G with coefficients in some variable K algebra, K prime, so G is anywhere. And let's look at the value of G phi for the unit element of the group. Phi, I remember, phi are just functions on the group with values in the scalars, with values in the affine line. All right. In this way, we get for a fixed phi, we get the function in fact g phi applied to E. Maybe the notation is not quite appropriate, but that would be just phi applied to GA. That's the definition of the left translated on functions. So that's just phi of G. Therefore, we recover the function phi by viewing phi as being an element of M, letting G operate on phi because G operates on M and taking the value on E. But of course, this here, C comes from a function on here, namely U applied to U phi, scalar product E, or U phi at E if you want. Taking the value at E is a linear form on M. So in fact, if you want, the phi's in M appear as coefficients of the linear representation, which we have defined of G and M. And so we are through, yes?
If G is monoid, you get the image of G became G of N. I think the proof shows that you get it independent.
Well, the image is contained, of course, you don't get the role of G and N. No. I mean, you have just to show that you get subgroups or submonoids of the full linear group. That's all. So you can see as an exercise, for instance, takes a monoid E1 multiplicative as a multiplication. So that's not a group, it's just a monoid. How can it be embedded into G and N? You see, it won't be stable. The image will not be stable by passage to the inverse, of course. That's all. And if you work with multiplication this time, and I said it will give you something completely different. So it will not give you something multiplied. What is the check for that?
Maybe not to math with the moment of the distance. Highly non-outside.
Well, you have many maps of I and you multiply the space. You may have many maps of I and non-outside space. If the maps into I then. Yeah, but every time it's not to actually all these possibilities.
Yeah, but we do it nice in the house now. Any nice map of I into space and take I into the house now. Solid space.
No. No, take it into the chaotic space. I mean, there's just two open sets and everything. Let's put on the line the chaotic topology and take the density map. I mean, it's continuous from the usual line to the chaotic line, and the image will not alter. I think you have that too. Today I like to distributions on algebraic arithmetic and algebraic group. But before starting with this, I have to make a rectification. There was somebody who wrote the letter, who wrote the pointing out maybe some mistake. Anyhow, I had noticed that I had made a mistake in the last statement which I made on Anfang an drei Groups over here. Let me recall the statement which we made. So the proposition G being affine algebraic bauen affine algebraic group over K as here. Then we have two statements. First, G is the inverse limit filtering of GI with affine algebraic monoids and groups. In fact, if G was a group itself, where the G1 are of finite type. That means that the algebra assigns a generated over K. So this is perfectly correct. The second was somewhat incorrect. If G is already of finite type, if G is of finite type, there exists a homomorphism of groups, of monoids. I set of G into the full linear group, but it's not in the full linear group, and that's too good. That would imply already that G is a group, in fact. Includes the full linear monoid in that last case. Mn over K. This is a monoid functor which asks to get every K prime. All matrices n by n over K prime with multiplication of matrices and multiplication, which is the monoid functor. Represented by standard affine states of n squared, which is a closed immersion. And of course, in the case when G is a group, then this must factor. This must factor from G into G and N. Okay. This will transform point to end up to the point of the monoid, whatever point of G is not enough. Alright. And so where I made the mistake in my argument was at the following point that I should recall how things went. I mean, I made this kind of mistake. I had tendency to make it several times during this course. And I always to assume, because in fact I practically never work with monoids or with groups, so I have some wrong reflexes. So I always assume that representations of linear representation of monoids are by automorphism. But they need not be by automorphism, they will be by endomorphism. So that's all. If a monoid operates on a module or a vector space or whatever, it needs to operate by automorphism. So what we did was the following in this case G. G corresponds to an algebra of type over K. That's because G is an affine algebraic space of finite type over K, or as you would say now an affine scheme over K. And the multiplication law on G, you recall, is given by co-multiplication in the algebra A, which turns A into a bialgebra. Pi, yeah. And we use the fact that every submodule M of finite type of A is contained in the larger one, M prime, which is stable, if one can say, under co-multiplication. M prime of finite type also, such that phi of M prime, which is a subspace of A tensor A, is contained in M prime tensor M prime. Now, what I did was to take a submodule M of A which was of finite type and which generated A as an algebra over K. Then I embedded it into a submodule of finite type which has a stability property. So I can already assume, if you want, by replacing n by n prime, that delta M is contained in M tensor M. Moreover, alright, we are in the case of a monoid for the time being, so there is no antipodism. And in fact, what we are going to do is uniquely the fact that phi m is contained in m tensor A. That's all we need. Because then phi will induce on m co-diagonal map which will turn m into a comodule by A, which means that less comodule, let's say, which will mean that G operates on M. On the left, it's an induced representation induced by the regular left operation on A itself, A being the function on G. And it's just stable. And then what I said is that the corresponding morphism from G into, well, it's not into GLM, you see. It's not into automorphism, it's into the endomorphism function of M. The isomorphic is M is of rank N to the scheme of N by N matrices, which is isomorphic as with multiplication of matrices. It's isomorphic to E cells are in space times N squared, but if you disregard multiplication law. So that this morphism then will be an inversion. We don't know the factors who the subfunction of invertible elements on M, which is just the function of automorphism of M, which is just isomorphic to G and N. And I wonder if the proof that I gave of the fact that the morphism which we obtain here is a total immersion whenever M generates the algebra A, was it proved here or not? Or should I repeat it? I was a little quick there. Should I repeat it? Alright. So, G corresponds to an algebra A. This what algebraic monoid, affine algebraic monoid corresponds to an algebra B over K, and this homomorphism corresponds to the homomorphism of algebra B goes to A, and what we have to prove is that this homomorphism of algebras is surjective. That's clear. And what I'm going to prove is that this homomorphism of algebras contains in its image M. And in fact what I will show is that there is an embedding of M into B, that we can find an embedding of M into B, such that this morphism induces the identity on M. Alright, when I do this, I'm true, am I not? So I will show how an element of M defines an homomorphism. It defines a function on the scheme. Alright? So, ho ho ha ha. What is it? Yes. If let X be an element of M, I will be the homomorphism and that I'm going to describe. I will define Ix as being a function on M, that means a function with values maybe 1 or O or whatever you call it. So that's what I have to define. That's a function on M. Everything else is viewed as a function. So I take a point on M that's with comes in some algebra K prime over K. So U is an endomorphism of some nk prime for some algebra K prime over K. And I have now to define Ix applied to U. And this will be an element of E1 of K prime and of K prime. And I should do this in such a way that this could be functorial with respect to variable K prime. Alright? And what will I do? Well, I take U of X, use a homomorphism and grant it to M K prime, x can be used as an element of nk prime, defined as this x element of n, and therefore defines the element of nk prime. Now, ux being an element of nk prime, recall, is contained in ak prime, because n is contained in A, and ak prime are just the functions on 0 k prime. So u of x is a function on 0 k prime. And I take the value of this function as the element 1 of the monoid. If x is part of the basic element of n, you see, and if the linear form 1 on n is viewed as being an element of the basis of the dual vector space, n prime just means that this function is one of the coefficients of the matrix, that's all. Also gerade runter und hinten ist Here the function is good. There's a k prime n by n matrix over k prime, and comes out that we take one of the coefficients as being the function with respect to the diagonal matrix, so one of the Boolean. And now I want to see what is the composition of this with this function. So u now will be the image of g in endomorphism, that's u over g, which is just the left translation in M. So u lower g applied to x is this g applied to x by the left translation. Now x, to recall, is a function on g on 0 k prime according to k. Now we will rather ask k as the limit of nk prime. And the left translation of gx, that's just the function that takes every g prime x of g prime g. Yeah, I'm sorry, that's the left translation on functions, because we have monoids, we have to interpret them as also into right translation on the monoid. Never mind that. Alright, so that's the new function. G prime goes to x, g prime g. We have translated the function x by g. Now I have to take the value of this for g equals 1. Oh, I'm sorry, for g prime equals 1. That means I have to take x of g. So the composition of this here with the function I will just describe in terms of a given x. So this moment we call it phi. So I of x applied to phi is just equal. It's a function on, I'm sorry, I of x composed with phi. It's a function on g whose value at g is equal to x of g. That means that we compose I of x with phi here, so that we get the element in here. This element is the n. The element x and n we started with. Sure. Curious to the logic now. In the end, if G is a group, alright, then every element of G instead of something being invertible, is left as an invertible element of in here, therefore it's left as element of G and N necessarily. Therefore, when it acts as a representation of a group for automorphism. And therefore we are very close into splitting into arms here. Of course, if this homomorphism is such that its composition with something is a closed inversion, then this already is a closed inversion, because assume that C is the algebra defining this object, that the homomorphism which goes from T to, which goes from G to A, the composition of T goes to C, which is adjoining to this inclusion, and C goes to A. So this is the homomorphism, this must be the homomorphism. I'm sorry, this is a surjection. This must be a surjection too. here. Let's make a little comment on what happens if we have a monomorphism and an embedding. Just a monomorphism, if you have a monoid and if you have a monomorphism of this monoid into GLN or more generally into any group group scheme, if we find, or more generally into any group function, in fact, that's enough. To say that we have a homomorphism of a monoid functor to group functor just means that the left and right translations on the monoid operate injectively. That's what it means. Because that means that we can embed the monoid function to a group functor by taking just added groups to the monoid where, how do you say it, with simplification law. Alright. Now, it can be shown that if you have an endomorphism of a scheme of finite type over Fx is a scheme of finite type over any ground ring K prime. Maybe you better have finite presentation. So in the case when X is affine, that means that the algebra by K prime that defines X is an algebra of finite presentation. Right? And if you have an endomorphism of X, X goes into X, which is a monomorphism, then one can show, although this is by no means trivial, that I is an isomorphism. And a monomorphism within a scheme of finite presentation over any ground scheme, let's say over ring K prime, is an isomorphism. It's a very funny remark, even over ground field, let's say. You have an affine scheme over ground field. The fact that an endomorphism is a monomorphism is an isomorphism is something pretty subtle. The only proof I know is an arithmetic proof by reducing to the case. When you have a situation of finite presentation over a ring which is itself of finite type over the integer, then reducing to a situation of finite type over a finite field, and then working with arc rings and using that arc rings are finite rings. Because the endomorphism of a finite set that is a monomorphism must be bijective. That's the only proof I know. It's a very funny proof. But this is sometimes kind of a useful term, because it will imply that the monoid in this case must be in fact a group object. Why this? Well, you have to prove that for every K prime over K, G of K prime is a group. That's what you have to prove. And this also means that we add that every element in GK prime is invertible. That means that the left translation it defines as bijective. ES defines a left translation which goes from 0 of K prime into 0 of K prime, which is an isomorphism. That's what you have to prove. But GK prime is a scheme of finite presentation over K prime because it comes from G, which is a finite presentation over K, because over field finite presentation finite type is the same thing. And we know already that this is a monomorphism, and therefore it must be an isomorphism. So definitely, monoids that are of finite presentation over any ground scheme, ground ring over field, for instance, and that can be embedded into groups, they're actually already groups. So the statement which I gave about monoids being embeddable into the linear group was just false. I mean, if you take the simple cases, let's say, for instance, take the functor O with multiplication, which transforms every K prime into K prime itself with multiplicative law. So this is a monoid functor. K prime for multiplication has a unit which is 1. Now this is certainly not embeddable, because this monolith function is not a root function. This element 0 of k prime is not invertible. Except if k prime is 0. If k is not 0 itself, the function is not a root function. So this function sec is the function m1. That's the reference function. So the function m1, which derives the function which is capital K of function mn, is not a good function, that is not embeddable into any good function. So, some of you had some time to do some homework. I think it would be kind of amusing trying to prove this theorem about monomorphism being isomorphic. And if you have any scheme of finite presentation over, take it even affine, that will make it things simpler. Otherwise, you have to throw in a little bit of more terminology about schemes. So let's say X is an affine scheme of finite presentation over a ring, let's say K prime. So the situation is that what is an algebra A over K prime of finite presentation. You have an endomorphism of X, which is a monomorphism. That means that you have an endomorphism of the algebra A, called U, which is an epimorphism of algebra. That doesn't mean it's the third vector, you see. Then it would be, I guess, too easy because of the term. Well, even then it's not quite clear, but just an epimorphism of algebra. Namely that means that an homomorphism of algebra of A into A of things of A into any ring B is known, then we know the composition. Alright? Then I claim that U is an isomorphism. Isomorphism of A.
What's the conditions on A?
Finite presentation. It's the quotient of a cylinder ring and finitely many variables by finitely many equations. If A is a field?
No.
Okay.
Polynomial ring over a key?
No, over any ring. And we use this fact not only over the field, even when we started with the field, but we had, you see, to replace K and an arbitrary K prime. So in fact, and that's almost all the time, even if you're interested in outwriting over a field in this context, in order to do it properly, you have always to replace the field by an arbitrary algebra operator. So we really have needed we want to prove that the monolith that is embeddable in a group, we have to use the theorem over, at least over algebras that are finite type over a field. Doesn't make it any simpler because that's not the field property that is important, it's the property of how far remote one is from the integer.
How about you not feel like that finite is a finite of finite type and the x to x i's are epimorphism and cannot once the i's are also
If x goes to x is an epimorphism? No, that's not true, because take x goes to x squared, for instance, in Gn, you see. But epimorphism in which sense now, of course? One has to be very careful when you speak about epimorphism of schemes. But I think it should be pretty easy to construct epimorphism of schemes in the strongest sense, that there are sections, let's say. That is very strong, you see. And that are not. So epimorphism of an object onto itself, morphism onto itself so that there is a section, and which is not an isomorphism. I think this should exist. Otherwise, epimorphism is in a weaker sense, take for instance lambda goes to lambda to the n of Gn to itself. At least the corresponding homomorphism for the ring homomorphism is kt t minus 1 of Ga into Ga for that matter. No, so this wouldn't be it. Well, alright, why not? You see, then, or from Ga into Ga, the corresponding homomorphism of rings would be kt goes to ks by mapping t into s to the n. I mean, this is a monomorphism of rings. So if you want to define epimorphism of schemes by monomorphism of rings, which is not very reasonable, by the way, then this would be a contact member. Well, I'm pretty sure you can get the better examples, the examples of sections. Here you don't have a section. But, what one can prove is if x goes to x is a raditional morphism, which means that it's injective on points that settle in fields, so that's less strong than a monomorphism. So if the monomorphism on field value points, then x goes to x must be a surjective in the tetratic sense. So that's an another statement. But one has always to start here with the monomorphism type property, and then to come up with an etymorphism type conclusion, not the reverse. It doesn't seem to work the reverse way. So in this sense, you see schemes are kind of alike to finite sets. I mean, there are very strong kind of properties inherent to them, which seems to come from arithmetical reasons, because schemes of finite permutation over any ground in K come from sheet of finite permutation over scheme of finite permutation over a ring that is a finite type in the absolute sense. And therefore, I mean, what happens there can be reduced to schemes of finite permutation over Artin rings that are finite rings. And I mean, that is kind of standing up anything. So it doesn't. So I think that this kind of theorem would be hard to prove also. And even for non-trivial algebraic varieties, let's say, in the test that set up, and one doesn't break through the setup of ground field difference. Take even, let's say, still an affine space, that's an isomorphism of still an affine space, that's an isomorphism to an isomorphism. Everything is expressed as units and set of n units and variables. Take just one polynomial. I don't know if it's so trivial. Perhaps it's pretty easy with one, but with two I'm not sure there's a non-arithmetical proof of it. Take two polynomials and two variables. Express that you have a ring ecomorphism defined by it, and prove that it's a ring of automorphism. Alright. Now I want to define distributions on algebraic varieties that are kind of analogous to Schwarzschild distributions on differentiable varieties. Little bit of a joke, but it's a joke that sometimes is useful. So I'm working well for simplicity about ground rings. We could now, of course, already start with ground schemes, but never mind. And let X be an affine algebraic space over K. So X is just associated to an algebra A over K. X and A determine each other mutually. And I will define the sum of distributions of X to be the scheme of distributions, or an algebraic space of distributions, which is preferred to remain in the context of an algebraic space, on X, to be V of A, the vector bundle associated to A, so as a functor on level K prime, this K prime goes to from of K modules and of K algebras of A into K prime, which is just the same as homomorphisms of K prime modules of A lower K prime into K prime. And we know that this is representable by the symmetric algebra of A over K. Of course, it's a little better than just nothing otherwise space over K. It has also a module structure, yes, pointed out several times, over the standard ring functor O k prime goes to k prime, because this here is a k prime proposition, and the k prime function is factorial. So the distribution on X, we do it being a vector bundle, and therefore it has a modular structure. And the values of this functor at a given k prime, k algebra k prime, we denote by this because this is of X with coefficient on k prime, of course. So that's this X of k prime. So that's the set of homomorphisms. And of course, we are partially interested in the k values distributions of X with values in k. So maybe the functor we will perhaps we underline here, and then the value of the functor on k perhaps we just denote by this of X without an underline. Maybe can we do that. All right, now what about the formalism of this conclusion? So, first of all, this X, just I recall, is representable. We have already said it by symmetric algebra of A over K. The second statement, it's functorial with respect to X, functorial and covariant in X. If we have X goes into Y, then the algebra P of Y goes into algebra A of X, and this being a homomorphism of algebra a fortiori is K linear, and therefore the vector bundle associated to A goes into the vector bundle associated to B, because the vector bundle the way we defined it as contrariant. So, and this here is just distributions on X, and this here is distributions on Y. And now what about multiplicative properties? We want to compare distributions on X, distributions on Y, and distributions on X times Y. Well, what we have is in fact a pairing like this, which we will call, if you have a distribution here, or how do we call distributions? I don't know how this is called. What name is it? Give alpha, let's say. Something you convolute this, let's say. Alright. Alpha, comma beta will be mapped into, as we could call it, the square tensor product of alpha and beta. There are not from to tensor product on the product of X and Y. So I will have to explain how we get this by linear pairing. It will have in fact a certain universal property. Alright, this distributions on X, these are just elements of P of A, if X for the spectrum of A. I mean, distributions on X, that's just V of A, vector bundle associated to A. Distributions on Y is just V of P. And distributions on X times Y, that's just V of A tensor V. So what we have to define is a bilinear pairing of V A times VB into V A tensor V. So that's something we have already explained, in fact. That is a canonical, in a way universal, pairing like this between vector bundles associated to a sheet of modules. It comes like this. If you have a point of the first of VA, that means a homomorphism of modules of A into K prime, of K modules. And if you have a, or let's rather do it this way, of K prime modules of A K prime into K prime, so let's call it U. And another V of BK prime into K prime. then U tensor V will be a homomorphism of U K prime tensor V K prime into K prime, the tensor product will be taken by K prime, and this is just A tensor B lower K prime, which is mapped to K prime. Alright, that's what I call the tensor product. Why did I put a square tensor sign instead of the tensor sign which appears here? After all, here it's just U tensor V. Well, maybe it was more greater precaution than needed. It's because we can, of course, look at the tensor product of the functors VA and VB. And because we have a pairing here into VA tensor V, we have a homomorphism like this. And it's pretty clear that this homomorphism is not an isomorphism at all. It is not true, you see, that the space of linear homomorphism of A tensor V into K prime is the tensor product of the space of linear homomorphism of A K prime into K prime and of B K prime into K prime. This is true only if either A K prime or B K prime are projective of a type over K prime, etc. You see, and morally that's the only case, known case, practical case where it's true. Therefore, except to make a very strong restriction on A and B, that either X or Y is finite state of representation over K, and that A or B is a projective finite type over K, it is not true that this homomorphism here is an isomorphism. But on the other hand, of course, we have the canonical pairing into the tensor product, that we would call alpha tensor B, beta. So it's not this one we are taking. However, what we have already noted when we made our general nonsense explanations about co-algebra structures and relating them to algebra structures elsewhere, it is that this pairing into VA tensor B is universal, and we look only to bilinear pairings into vector bundles, namely into things that are of the type V of n. We have seen that to give a pairing of VA times VB into Vn is the same thing as to give a homomorphism of n into A tensor V, or what amounts to the same as to give a homomorphism in the opposite direction of vector bundles of VA tensor V into Vn. Alright. And therefore, in order to express this universal property, we just write that we have an isomorphism between VA tensor V and VA tensor square tensor VB, where the square tensor expresses just universal, the solution of the universal property of having pairings of this time this and some vector bundle. All right. And this pairing, in fact, is functorial. But I prefer to look it up here. This is functorial in X and Y. All right. So we have these structures. What else can we say at first sight? Yes, that the functor x itself is the subfunctor of this x. Maybe I can erase it here. X is embedded in this x in a functorial way. Well, x is a functor. K prime goes to homomorphism of K algebra of A to K prime, and this is contained certainly in the homomorphisms of K modules of A to K prime, and it's controlled. So there is included. So x can be identified as a subfunctor of this distribution functor. And now we can ask ourselves, how can we reconstruct x in terms of distribution on x? What is a subfunctor? Now, in order to express this, we have to put some extra structure on a particular thing distribution of x. And when we describe distribution of x as being a vector bundle over k defined by the k module A, we did not use at all the algebra structure of A. We used the algebra structure, of course, in order to define the subfunctor, define this inclusion, because x was defined as being the k algebra homomorphism of A. Now, what does it mean that we have an algebra structure on A in terms of linear algebra over K? It means that we have a homomorphism of A tensor A into A, having satisfying certain axioms, and a homomorphism of A tensor A into A in terms of the corresponding vector bundles, meaning that we have a homomorphism in the opposite direction of VA into VA square tensor product VA. That's what it means. Alright. So what we have now to put as an extra structure on distribution on X is what I would call a diagonal map. That's delta over X. And when we want to interpret what's a diagonal map, geometrically, let's recall that distribution on X times distribution on X with a square tensor product is just distributions on X times X because of C, and therefore we have to define a morphism of distribution of X into distribution of X times X, and this is of course reduced from the diagonal morphism of X into X times X. That just means that in terms of rings, the diagonal morphism from X into X times X is associated with the ring homomorphism of A tensor A into A, which is the product homomorphism. X tensor Y goes to XY. And this, in fact, let's write a little f here. Of course, we have the fact that we have that this delta x is reduced from the usual diagonal map can be also interpreted by the commutativity of the diagram. This x goes into this x times x here. How will we write it? Let's write it under this here, perhaps. Here, in the vertical arrows, we have x goes onto this x, which is what we have set in D, and here we repeat the same thing for x times x. Here we have epsilon lower x times x. Here we have epsilon lower x. Maybe I will attempt to put epsilon because maybe we use it otherwise it's super epsilon for units or for units. I don't know. And here we have the diagonal, the usual diagonal morphism, and the square here is commutative. And now I will reverse what I said last time about a coalgebra structure being the same thing as an algebra structure, a coalgebra structure on some module A being the same thing as an algebra structure on D of A. I will say that an algebra structure on A is the same thing as a coalgebra structure on D of A. That is, if we give an A, it is just if we give something that we like to call distributions on some X, but for the time being A is only a module over K. And we look at D, the issue of distributions equals, let's say, D of A, viewed as being a module function. The delta is the same thing as the algebra structure, the most more sense. An algebra structure
without exponents. It's just by linearity. It's by linear algebra. There's nothing. And now, to say that this algebra structure is associative just means that this diagram map is abstractive in a rather evident way when one writes down directly the diagram in terms of operation of vector bundles and data, and to say that it's commutative, that algebra is commutative just means that data is commutative, meaning that data composed with symmetry here is delta. And the same way one can express the fact that the algebra structure is unitary by saying that there exists, so what does it mean that it's unitary? That means that there's unit in A, that means that there's a homomorphism of K modules of K into A. An element here being just viewed as being the element of 1 by an homomorphism, which has certain properties. A homomorphism of K into A corresponds to a homomorphism of VA into V of K, which is just O. Therefore, unit structure which would be just a homomorphism for an epsilon. Maybe you have an IS. I listed of the two. Alright, a homomorphism epsilon V into O into the ground ring equals to 1, that's 1, such that epsilon is related by two commutative diagrams to delta, which express, maybe I don't write them down, to express that the two-sided unit. And now if you have all these things, if you have in a given vector bundle D, if you have a diagonal map data which is associative and commutative, and which has a unit, then this can be viewed as being equivalent data to giving an affine between X, to giving, let's say, an algebra A over K, which is commutative, associative of course, and unitary, namely, just of these one of these algebras we are working with for 2 weeks already, and that means also that we're giving a scheme affine between X over K, or affine algebraic spaces. So we have recaptured, exactly the role of X, and we have given the corresponding vector bundle with the extra structure delta satisfying some property. And now I want to say how do you reconstruct X, so to say geometrically, in terms of these data. So what is the subfunctor X of the functor list X equals, let's say, V of X? How can you reconstruct the subfunctor in terms of just this data and some actions on it? Alright, the property is just the following. If you have a point X of dk prime, k prime in algebra over K, then X is in capital X of k prime, X is a point of capital X, if and only if delta of X, which will be an element of D square bracket D applied to k prime, is equal to X square bracket square tensor X. That's a really well-known relation. In group theory, I think that the logical counterpart to commutative elements. Multiplicatively commutative elements. When you derive this relation, you get delta X is 1 delta X plus X squared. Never mind. So let's prove this equivalence. Well, so we have to express the fact that the homomorphism of modules of AK prime into K prime, or, well, maybe of K modules of A into K prime, so that's X, is compatible with the multiplication. It's an algebra homomorphism. And here maybe I could add an extra property, and epsilon of X equal to 1. You have to take otherwise 0 would do, and 0 doesn't. Plus epsilon X is 1. Take these two property together. So we have to express that the homomorphism of A and K prime is an algebraic. So this fits into two. First of all, that x transforms 1 into 1, but x of 1 is equal by definition to epsilon of x. So that's the second relation here. And second, you have to express that x of, maybe we call it other u, no? That u, so that's what u. That u of xy is equal to ux uy, and again that this multiplicative property is just this here. Now let's do it in terms of the data. So how do we get xy? It's by taking a tensor a goes to a. This is the multiplication, which we call delta, which transposes the data that we have given here. All right. And so here we have u goes to k prime, and that should be the same as ux uy, which is taking u tensor u here, which is mapped to k prime tensor k prime, and composing it here with multiplication. All right, we have to prove the commutativity of the diagram. But the composition of u and delta by definition is delta of u. That's how the delta here was defined. And so what of a tensor a and k prime deduced from u and u by taking the tensor product. So was not what we call u squared by that u. All right. So that's the way, working throughout, you see, indicator of functors without passing through the rings again, of expressing the subfunctor x of d when d is endowed with the associative, commutative, and unitary co-multiplication. Now, what happens if g is endowed with, I'm sorry, there's no g, there's an x. More for that. So, I still have my upper and right space x over k. What happens if x is endowed with the composition law? We have a morphism of x times x into x. Alright, this will define us a morphism from the distribution of x times x, which is just the distribution of x tensor with distributions on x, square tensor product, into distribution on x. If this composition law is pi, this corresponds to composition law like this here, which just is the same thing as a pairing of distributions x times distributions x towards distribution of x by using the property of the square tensor product. So to give a composition law on x is essentially the same thing as to give this pairing here, with the exception that we should know that this pi here is compatible with the diagonal map in order to know that it corresponds to the morphism of x times x into x, so that we know that it induces an homomorphism of the subfunctor into the subfunctor. Up to this extra condition, we have to put on the composition law on distribution of x, so that means that this law is compatible with the co-algebra structure, with the co-module structure. With the co-algebra structure, yes. That's just the same, that's the equivalent thing. And of course, it's an evidence that this composition on distribution of x, the distribution of x, induces on the subfunctor x the given composition law pi. So that's here all this pi hat, if you want, the extension to distributions. Here we have pi hat again, and here we have pi. So that's just a canonical extension of the distribution of Lawvere on X to the distribution law, to the composition of Lawvere on X, the composition law on distributions. And it's clear now that the composition law pi is associative if and only if it is so on distributions, the same for commutativity. And as for unity, it's unitary. This composition law on X has a two-sided unit if and only if the composition law on distribution of X has a two-sided unit which is compatible with co-algebra structure, namely which satisfies the property that epsilon of epsilon was this augmentation here. That epsilon of 1 over d, that's 1 be the unit element for the what is the general notation for the Dirac measure? Delta. But it's 1, 2, I have already taken the data. Well, never mind. That this should be a primitive. I'm sorry. Yes. Well, that's a unit element, and this X should belong to X, namely that it should satisfy these two conditions. It should have augmentation 1, and the truth is that it should be a mathematically primitive element. All right. So in particular, if G is a monoid with unit, then this X has a structure of an associative algebra with unit. If X, moreover, is a group, we couldn't say that algebra is a group, or we can say then, of course, it has an antipode, satisfying zero conditions. So, what we did essentially was to dualize, as I said already before, the interpretation of co-algebra structures on a module in terms of algebra structure on dA. Now I have been on the contrary an algebra structure on A, which I interpret as being a co-algebra structure on a certain vector bundle. And when I have both together on A, which corresponds to the case, let's say, of an algebraic space X over K that has a monad structure to it, let's say, then we wind up with an interpretation of bi-algebra structures. So we can interpret them also in terms of vector bundles, like here, endowed with both a diagonal morphism delta and a composition of pi, and these two being related in the way I have explained. Now, what about operations of monoids or modules? Now, X is an unusual notation for monoids, henceforth we will call it G. Of course, if G is a monoid, viewing it as contained in the algebra of distributions, it's stable under multiplication, and if G is a group, therefore, it will be contained in the subtrunk of invertible elements, which is again representable. So G is then can be viewed as being embedded in distributions X star, something like the units of an algebra. Now assume, but we won't necessarily assume that G is a group object, so let's just assume it's a monoid. Now, what does it mean that G operates on a K module M? Well, we've already said what it means. In terms of commutative algebra, that means that if we endow A with a co-algebra structure corresponding to multiplication in G, then M has a comodular structure to it, and the comodular structure is interpreted in terms of a modular structure over over V of A on the functor either Wm. This means that V of A operates on either, we should say whether the functions are left or right, let's say operator operates left, let's say, on the K module double on the K module M, if V of A operates left on the functor Wm, which is K prime goes to n tensor K prime, or on the right on V of M prime, on V of M, which is K prime goes to from K and K prime. Now V of A, that's what we call decisive distributions on G. Therefore we see that to let a module operate on a K module on the left is the same thing as to let the functor of distributions, the distributions of G, operate on Wm on the left. And we have given last time, we have given interpretations of this in more down-to-earth way when we make some extra assumption on the algebra A of G. If A as a module is a sum, possibly infinite, of projective modules of finite type, then the whole situation can be reconstructed in terms of V of A of K, the set of, which is the dual of A over K, provided we use it as the topological module over K, and now it's the topology of the simple convergence, and this is the distributions over G without underlines, namely the K-value distributions of G. Now this is just an algebra over K in the ordinary sense, no function anymore, an algebra over K, but however the topology on it is a topological algebra, and the algebra structure being continuous, the composition now being continuous, and we have seen that under these conditions to have G operate on the left on M is the same thing as to define a structure of a left module on M over the algebra of distributions in such a way that this operation should be continuous, namely that the action of this on any element factors through one of the discrete quotient spaces of this algebra of distributions. This was defined as inverse negative. Now, what's the interest of this general nonsense about distributions? I think it's kind of practical because this algebra of distributions contains both the moduli G or the group G whenever it's a group, and a lot of infinitesimal, practically all infinitesimal information. Infinitesimal information we can with on the monad object G. For instance, let me not be too specific on this, but just give some indications to situate this formalism. For instance, if we restrict, so G corresponds with affine ring A, and this affine ring A, because of the unit element of G, is augmented to K. So by augmentation, let's say epsilon. So let's say augmentation ideal I in here. Of epsilon with I, and let's put on A the topology defined by the powers of I, so-called iadic topology. Then, among all homomorphisms of K modules
A into some k prime, the k prime value distributions, we can look those which are continuous for this topology, which means those homomorphisms which vanish on some power of I. In this way, I get a subfunctor of the functor of distributions of x, which are called the distributions concentrated at the origin. For this here, distributions of G at the origin, comma k prime. And the functor is distributions of G concentrated at the origin. Now this will be in fact a subalgebra, which is called the hyperalgebra of the group object G. In fact, it's something like the distributions at the origin of a Lie group, you see, that form an algebra by convolution product. For instance, because of this epsilon, this here the direct sum of O, which corresponds to the augmentation epsilon, plus the, so it's an augmented algebra over O, so it's the sum of O plus the kernel of it, distributions, the kernel for this dist plus of GE, you see this here, contains, for instance, this ideal contains the Lie algebra of G at the origin. And the algebra structure of the Lie algebra structure of this Lie algebra is just the bracket operation within the associative algebra. You see, you have a lot of information contained already in this small piece of the space of distributions. So it's something that really contains a lot. After all, it has to contain a lot because when we know this algebra plus the diagonal map, you reconstruct the group. So, but it contains a lot in a rather handy way. If we are working characteristic P, for instance, then we know or not that these Lie algebras have an important extra structure, namely the piece power map. Then it turns out that the piece in characteristic P, the piece power of the derivation is again a derivation, which allows us to define piece power maps on Lie algebras of algebraic monoids. And this piece power map again is induced by the piece power map in the associative algebra in which G is embedded. So I mean everything is pretty well inside of this algebra of distributions.
This Lie algebra depends on I which you have chosen, isn't it?
Well, it's the unit section.
Oh,
Yeah. And the Lie algebra of a group one takes it as the origin. It doesn't really matter. Because of course, because of homogeneity, you see, if you have any other section, there's a canonical isomorphism by left translation or right translation between what happens around one section but what happens around the unit section. Yes, but
what is this thing I can do in the algebra?
What is this here?
No, just below. This plus.
Here?
Yes.
What is O?
Yes, I know what O is. What is the next one plus?
This plus GE, that's the kernel of the augmentation. I said that the distributions, what should I say? Yes. Yes. I said the distributions on G are augmented to O orbits, and that's what we call that is epsilon. That means that comes from the fact that G is mapped to E after all, therefore, because functionality distribution on G is mapped to distribution on E, which is just O. And I take the kernel of this to be distributions plus on G, but it turns out that also we have O mapped into distributions on G such as the compositor is the identity because of the unit element in G. Because we have E goes into G goes into E. E is the spectrum of K here. And therefore, distribution G decomposes into a like sum of O into distribution plus. It corresponds to the fact that the hyperalgebra of the group can be replace distributions by just the part that is concentrated at the origin. That the hyperalgebra decomposes into multiples of the unity, and then, well, I mean, what you view as being positive in it.
in characteristic 0, for instance, this distribution flux would be what is generated through multiplication by elements of the Lie algebra. In characteristic P, this would no longer be true. Now let's give one or two examples of these distributions to see how they look concretely in some cases. Sit down. Take, for instance, a constant finite group. And associate to this the constant group object in the category of affine algebraic spaces over K, the constant algebraic group over K defined by gamma. So this is the spectrum of the ring K to the gamma, where the ring structure is just the product structure, gamma copies of K. I mean, this is independent of the group structure on gamma. I just take ordinary functions on gamma with values in K. This makes us a algebra over K, and the spectrum of the algebra is taking product of copies of K is just taking sums of copies of the spectrum of K in number gamma. I pile them up, so that's the constant group gamma. All right. Now I've said what the algebra structure is in this affine algebra, this product structure. Now what about distributions? That's just the dual of this. Now the dual of K gamma, there's canonical basis here. It's just K to the gamma again. But the algebra structure will not be the same. This time the algebra structure should depend in an essential way on the group structure which we have on gamma, or monoid structures for that matter, if you want to be only a monoid. Never mind. And what is it? Well, I mean, K of gamma, that's just linear combinations with roots in K of elements of gamma. And it's well known that the group structure on gamma, which is a group structure on the elements of the basis, extends linearly to a group structure on K to the gamma, which then is generally denoted K of gamma, which is the group algebra of gamma with coefficients in K. Hi Justine, you didn't know what a group algebra is. So it is. So distributions on the constant algebraic group gamma, they are just elements of the group algebra of gamma, that is just linear combinations with coefficient K of elements of the group, and the multiplication is the one that is induced by multiplication on the group, that's all. Here you see we use the various distributions. I mean, an arbitrary distribution is a sum indexed by gamma of distributions concentrated on the various points of gamma. I mean, that's a trivial case because, I mean, gamma is discrete, it's dimension 0 K. It would be like a Lie group, a discrete Lie group distribution. That would be a trivial thing. And the fact that representations of gamma K in a module corresponds to representations of its algebra, I mean, it's pretty clear. It means, first, because of functorial nonsense, whether gamma is finite or not. You see, to give a representation of the constant group object defined by an ordinary group in some object M anywhere is the same thing as to give a group, an operation of the group gamma itself, just an ordinary group, by automorphism of this object. On the other hand, we know that to let a group gamma operate on a module is the same thing as to let a group algebra operate on a module. So this is pretty clear.
What would it be an example?
Well, it's 0, isn't it?
Yeah, right.
Yeah, this comes from the fact that I over I squared is equal to 0, and that's what it means in this case. I, the augmentation ideal, is what is the augmentation which goes from distributions to k. It's associated to a linear combination of elements of gamma, the coefficient of element 1. All right? But I'm sorry, it's on the other side I have to take now. I take rather the augmentation, that's it. Of a to k, which corresponds to the unit element of k. So it associates to a function of gamma, the value of this function on the one element. So the kernel of this are all functions on the group gamma, with values in k that vanish on the origin. But it's pretty clear, you see, that for the product function, that the sphere of the ideal is the same idea. I divided by I squared is equal to 0. When for this big group, one expects that the algebra could be 0, and that's what it turned out to be. It would be different if you took the group mu2, you see, of two roots of unity. One thinks of this as being the group z over 2z. The homomorphism of this into mu2, which maps minus 1 into 1 into 1 and minus 1 into minus 1. So this is a constant group object. This is the group of second roots of unity. And to give a homomorphism like this is the same thing as to give a homomorphism of the ordinary group z over 2z into mu2 of k, into the sections of this and this. And we have, that means it's the same thing as to give the image of the generator, which would be an image of order 2 here, order divisible 2, dividing 2. And he takes the section minus 1, which is a square root of unity. Now this homomorphism is an isomorphism of schemes when we are in characteristics different from 2, when 2 is invertible on the scheme we are working on, if 2 is invertible on k. But if we are in characteristic 2, the homomorphism is identical to 0. And so mu2 then completely escapes from the homomorphism. And mu2 now in characteristic 2, it's a purely intelligible group escapes that. So it has a V algebra which is of dimension 1. Very interesting V algebra. The second power of the canonical generator of the V algebra, x to the x squared is equal to x. The second power operation on the V algebra equals to is not trivial at all. Therefore, these kind of proofs, mu n's, alpha, p, etc., they have non-trivial V algebra. But those that come from ordinary finite groups, or infinite groups as for that matter, they will, the corresponding group objects are no longer affine, they are group schemes. So they will have a trivial V algebra. Yeah. So maybe we should stop because the bus may be leaving. So tomorrow we will some more examples, especially with diagonal line levels. Will be mapped by a diagonal map into the completed tensor product of k to the m tensors with k to the m. This will involve the multiplication law in M. So distributions on the multiplicative type group on the diagonal group defined by M, they are just functions on M, and the multiplication of in the space of distributions is just ordinary multiplication of functions. That's all. Very clear? Now let's apply this to determining the linear representations of this group G. In fact, what we want to do is for every module M over K, there's a little conflict of terminologies. So how would we call our module? V, let's say, or K. Although K is not a field, V will be a vector space. So every module V over K, to determine all possible ways of letting operate G on V, and from there to conclude what is the category of
representations of G on K modules. All right, and we have seen in the general nonsense that we have said before, because the affine algebra of G is 3 over K, that such structure of having G operate on V on the left, let's say, amounts to the same as to give a structure of a module on V over the algebra K to the M. But this structure of a module should be continuous in the following sense, namely that for every x in V, the map U goes to Ux, which goes from the algebra Km of distributions to V, should be continuous, namely it should factor through a finite quotient of K to the M, where the set of indices M here might be infinite, if M is an infinite group. So you have to see how the product of algebra K to the M can operate on a module in such a continuous way. Now, in this K to the M, we have privileged elements, how we call them, Pi, let's say. These are the PM, which correspond to the various elements M in capital M. These are the functions on M, which takes the value 1 at M, and the function 0 everywhere else. In terms of distributions, this would be the Dirac distribution at the point M. And what are the relations between these PMs? Every PM is such that PM squared is equal to PM. It's a projector in the ring K to the M. And the sum of the PM, this is now an infinite sum. But it will be convergent for the product topology in K to the M. And the product is equal to 1. And on the other hand, these projectors Pn and Pm prime are mutually orthogonal. And if we have an operation of this algebra on B, then the PMs will define n k linear endomorphism of V. Call them whatever I know, pi m if you want. Pm will go to pi m, and endomorphism of V. And what will be the corresponding properties of the pi m, which correspond to these? The pi m will be projectors. That means each pi m corresponds to a decomposition of V as a direct sum of its image and of its kernel. They are mutually orthogonal. Which means that the image of any of these projectors is contained in the kernel of the other, if the indices are different. And on the other hand, we know already, how should we say, that for every x, in V, all of the pi mx except the finite number must be equal to 0. This comes from the continuity here, because the isomorphism which goes from u goes to ux, which goes from k to m to b, should factor through a finite quotient of k to the product of k to the subproduct of k to the m, which means that it must be 0 on all pi m's except the finite number. So this in fact is a finite sum, which just expresses. And then we can also say that this being continuous, you see, for the product topology here, discrete topology there, the relation which we have here gives analogous relation. The sum of the pi m to the x is equal to x, and in order for this to make a sense, as it should, this means that it's only a finite sum. So what we really have is, to give such a set of projectors for any set M in a module V, is just the same thing as to give a decomposition of V into the direct sum of submodules indexed by the set capital M. So to give such an operation of G on V is just the same thing as to give submodules Vm and D, indexed by M, epsilon, and M, in such a way that the sum of all the submodules is direct and is equal to V. So V is the direct sum of these Vms. That's also what is called the graduation of type capital M of the module V. When we look how the group object G operates on V when we have decomposed V in this way as a direct sum of the Vms, we just have to say then how G operates on each of the Vms, namely what it does when all of the Vms except one is equal to 0. And what we see is the following. In order to express the result, we will look at the homomorphism from G into Gm, the character associated to M. I recall that we have a natural pairing by definition of G is the dual of M with values in Gm, G times the constant group with values M into Gm, and therefore for every element in here, we have a homomorphism of G into Gm, which I call chi lower M, is a character associated to M. And if G is an element of Gk prime, let's say, and if X is an element of the M cancelled over K prime, then the value of the transform of X by G is equal to chi lower M G X. If we make explicit what it means for an image of element of V to belong to a projector, you see that just means this. It means that the element transforms under the action of V according to the character pi M. Therefore we see that any representation of G on a module V decomposes the canonical way according to the characters of the diagonal group G. It's a direct sum of modules on each of these. It's just some representation by multiplication by this character. So, we find that the category of representations of G on K modules is equivalent in a canonical way to the category of graded K modules graded by the set M. In this description, the composition law in M has not played any part. What's the importance of the composition law for this category? Well, this category has more structure than just a K-linear structure. In fact, there's a tensor product within the structure. And it's in order to express the tensor product within this category that we will need the group structure on M. In fact, if we have two modules V and V prime over K, which we endow with the degree M and the degree M prime, so that G operates on the first by the character chi M and on the second by the character chi M prime, then the tensor product of the two will be the tensor product of V and V prime, but where G acts according to the character M plus M prime. That's pretty clear, you just write the definitions. So we know that it's a tensor product, we actually have to see how G operates. Well, it operates on here by chi M of G and here by chi M prime of G. It operates on the tensor product by the product of chi M G times chi M prime of G, but chi M times chi M prime is chi lower M plus M prime. The product of characters corresponds to the sum of the indices. Of course, here I was working over a ground ring, which corresponds to an affine scheme S, but I could as well work with an arbitrary affine scheme S, or an arbitrary scheme S, not necessarily affine, and look then, well, at dm over S, the diagonal group over S. In fact, the diagonal group is defined as a group over spec Z, if you want, and therefore it's defined over any S, whatever the scheme S, because it lies over a spectrum of, and it takes it as image. All right? And so we can look at this diagonal group over S now, and we can look what are its representations on sheaves of modules over S. Let's take them for simplicity. I don't think it really matters. Crazy coherent sheaves of modules, so that in the case S affine we reduce the polyacid. Then we will find that this is category is equivalent to the category of sheaves of modules V over S endowed with a graduation of type M. And the tensor product corresponds to addition of the indices M. It's a tensor product of graded modules when the modules are graded by group. So that makes sense to speak of the tensor product graduation. By the way, we have defined in the meanwhile, since we started defining affine algebraic groups, we have defined in the meanwhile arbitrary schemes over S, over K for instance, and this allows then us also, as we just did, to extend the basis from being a ring to being a scheme. But my emphasis is now that we have also schemes over S which need not be affine over S. And for instance, for every set M, you can view at M lower S, rather than viewing it as being the constant function over S, which would be the direct sum of capital M pre-sheaves isomorphic to S. This is not too handy in our setup. It's preferable to view M lower S as being the constant sheaf defined by M, which would be the direct sum of capital M copies of S, viewed as being a sheaf, or still else, we know that direct sum of sheaves and direct sum of schemes correspond to each other. Then this M lower S would not just be an arbitrary function, it would be in fact represented by a scheme, which is just the sum of capital X copies of S, viewed as being local in space. Alright. And this function which associates to a set M the corresponding constant scheme over S commutes with in fact an exact function as a matter of fact. Commutes in particular with exactly. It commutes with finite inverse limits. Commutes also with finite right limits, by the way. But here, what is interesting for us is that it commutes with finite products, and therefore it will transform group objects into group objects. So for any usual group, whether it's finite or not, you have a group object MS over S. It won't be, even if S is affine, it will not be affine. It will be affine if and only if M is finite. This is independent, of course, of the group structure. M lower S will be a scheme over S. If S is affine, it will need not be affine, it's affine if and only if M is finite or S is empty. Because we know an affine scheme must be quasi compact, and being the union of capital M copies of S, it must be the finite union of such copies. And this is possible only if either M is finite or all the factors except the finite number of them are empty. All the factors as S, this would mean that S is empty. Alright, so I like, therefore, to view M as defining rather a group scheme MS over S, but it's no longer an affine group scheme anymore. It's not even of finite type, it will be of finite type over S only if the same way if either S is empty or M is finite itself. It will have infinitely many components, which is slightly unusual in the classical context. Consider algebraic graph, which has many components, but it doesn't really matter. All right. Now, the point I want to make is that the very definition of G, the diagonal group associated to M, is that G is the group sheaf or functor of homomorphisms, of group homomorphisms, of this constant group object MS into GM. I already made this remark, but by taking the constant functor instead of taking the constant sheaf or the constant scheme, this will be M over S. And it's just the same proof essentially, except that we're working now in the category of sheaves instead of working in the category of pre-sheaf. So by definition of this functor home underline, this associates to every S prime the following thing. We look at the group over S prime defined by base change, is deduced by base change from the two groups MS and GM lower S that we have over S. You get the two groups objects MS prime and GM S prime, because of course taking the constant object associated to an M on S is compatible with space change. And then she takes a set of group homomorphisms of one into the other. And for variable S prime, that's a functor. Again, that this functor is just the functor which we have called G equals D of M. Now, what is a homomorphism? Quite generally, if you have a constant object over some ground scheme S prime, and if you have another object X over it, for the time being, let's not consider multiplication. What is it? To look at the S prime morphisms of MS prime into X. Well, MS prime is just the direct sum of capital M copies of S prime. And therefore, by the very definition of a direct sum, this is a set of all homomorphisms of S prime of S into X, and by taking the m's power of this, which means that it's just a set of all maps of M into home S prime S X, where the first form here just means all maps. It's the home in the category of all sets. And now what if MS prime and X have composition laws on them, and that if I'm interested in group laws or unit laws or whatever it is, and if I'm interested in those homomorphisms from MS prime into X that are compatible with composition laws, well, you just look what it means. And you see that here you have to restrict to the homomorphism from M into home S prime X. That means the sections, that's just the sections of X over S prime. Maybe we write it like this. Gamma X over S prime. Or X prime perhaps, that would be nice. So X prime having a composition law, this gamma X prime over S prime has a composition law too. We assumed also that M had a composition law, and here we take the maps from M into this set, which are compatible with composition laws. So if both sides are groups, you just take the group homomorphisms. And now what if I take the case when M is just an abelian group, and when the X prime here is just GMS prime, I mean then the sections of GMS prime are just the units in the ring of sections of the structure sheaf of S prime, and I get back the definition of the set of whole group homomorphisms of M into the units on S prime. So therefore, the diagonal group associated to M is just the dual of the constant group object M, lower S, let's say, with values in GM. And now I may look at the dual of the dual. Let's look at DG, which by definition will be home underlined of S groups of G into GM. And because we have this pairing between G and MS is within GM by the very definition of G as being the home of MS into GM, we get a morphism of M into this. That's of M lower S into this. And that's no nonsense about brackets. Nonsense about pre-sheaves even. So pre-sheaves turn out here automatically pre-sheaves, these home pre-sheaves. That any group object is mapped into its bidual with respect to any other group object. It's in fact two or four modules instead of Z modules. They are nice. Alright. And now the theorem I like to prove is that this here is an isomorphism. Namely that G is reflexive with respect to Gm. That M, that's a constant group with value M, is reflexive with respect to duality into Gm. It's isomorphic, that's the natural morphism of system with bidual is an isomorphism. So let's be careful what this means. This doesn't mean that any homomorphism from G into Gm comes from a unique element M of capital M. Doesn't mean this. It would mean so when S is connected and non-empty. What it means is that any homomorphism from G into Gm comes from a section of MS over S, or it amounts to the same, comes from a locally constant function of S into M. Because a section of the constant sheaf with value M over S can be viewed as being just, well, I mean, we already described what are morphisms into direct sum, you see. Decompositions of S into a direct sum of schemes indexed by the set M. So it just means that S is written as a direct sum, as a disjoint union of open subsets as M indexed by capital M. That's what it means. Gamma MS, comma S is a set of all these partitions of S into open subsets indexed by capital M. And of course, if S is connected and non-empty, then only in this case is there one-to-one correspondence. What is this? That's it. Between elements of M and such partitions, because if and only S is connected and non-empty, can we find exactly for each such partition one and only one M, so that Sm is equal to S. I mean, that just means that give such partition is the same thing as to give a map from S into M, which is continuous when M is endowed with a discrete topology and S with its own topology. And continuous maps of topological spaces into discrete sets need not be constant unless the space is connected. And the value is determined in a unique way if, moreover, the space is non-empty. Alright, so we have to be a little careful about this, but of course if you have a connected scheme, for instance the spectrum of a field or the spectrum of an integrity domain, then the statement will mean that every homomorphism of G into Gm comes from a uniquely determined element M and capital M. But we couldn't expect this to be true in general because this home underlined you see is a sheaf. So the best we could have for is that the sheaf associated to a constant function M, which will be precisely M over S. Now let's set out to prove this. So we know already what the best thing we can hope for to obtain, and let's prove that it's true. And therefore I will use the fact that the Gm we are homing into here can be treated as the group sheaf of automorphisms over OS of OS itself as a function of the scatter of all schemes over S prime, Gm over S. Put the TET over perhaps in order to indicate that we are looking at the ring functor on the scatter of all schemes over S, and here on the module functor on the scatter of all schemes over S. Of course, to give an automorphism for every S prime lying over S, to give an automorphism of OS prime root as being a module over itself is the same thing. And an endomorphism of OS prime is just an it's just a homotopy, it's just a section of the sheaf of rings OS prime, and it's an automorphism and only the section is invertible. So I mean, that's clear that GM can be interpreted in the way I said. And therefore, to give a homomorphism of G into G and S, that means to give a point of this scheme over S, which is a section over S, is the same thing as to let the group G operate on the free module of rank 1. This clear? All right. Now we know what it means to let a module operate on a free module, on a free sheaf of rank, on any quasi-coherent module. It means that this module V OS is decomposed as a direct sum of VMs indexed by M. Now here we have a module of a very special type, OS itself. What does it mean that we decompose it into such a direct sum? Well, I mean, we see that it's hardly different in any other way than to associate just one single degree to the whole of OS, except for the phenomena coming from the disconnectedness of S. Now, if we want to do things in a formal way, what we will say, we may go back to our PMs. We have seen that we have expressed such a decomposition by giving a family of projectors pi m in the module V, which are mutually orthogonal and whose sum is equal to 1. It may be an infinite family, but the sum has a sense all the same, as I explained. All right, what would it mean here? So what is a projector on V? Well, V is the module OS itself. And the end-dimensional OS, as I just said, is a section of the sheaf of rings OS. So the pi m's now are sections of the structure sheaf of S, and these projectors, that means that they correspond to, we see easily that to give a projector in gamma SOS is the same thing as to give a decomposition of S into the sum of two pieces, so that pi m is equal to 1 on one of these pieces and to 0 on the other. And to say that these projectors are mutually orthogonal, pi m prime equals 0 for m different from m prime just means that these open pieces are mutually disjoint. And to say that the sum of these pi m's is equal to 1 just means that the union of these open pieces is the whole of S. So this just means that we have decomposed S, that to give such a graduation on OS itself is the same thing. The same would be true for any invertible module, by the way. That it's the same thing as to get a decomposition of the space S into the sum of open subsets, disjoint sum of open subsets Sm, so that on each Sm, the degree of our module OS becomes M. So that in fact, I mean, the module is decomposed according to the decomposition of the space into a direct sum. Direct sum of its restrictions to the open sets. And that's exactly what we wanted to obtain. Of course, if S is affine, more generally if it's quasi compact, then there's only a finite number of these open sets which are non-empty. So in this case, the graduation is a finite graduation. So we see that a constant commutative group object over S, group scheme over S, is reflexive with respect to Gm. And of course, because reflexive groups correspond to each other by the constraint functor of taking homing into Gm, that implies also that G itself equals Dm lower S is reflexive. So it's the rule of the reflexive group, which is a duality functor. When that's pure general nonsense again, establishes an anti-equivalence between reflexive group objects and reflexive group objects. Reflexivity with respect to a given group object Gn. Now, in fact, this duality with values in Gm really can be said to dominate the theory of abelian group schemes. Of course, we can't expect a group scheme to be reflexive unless it's abelian, because it's by rule is abelian, being a home with values in an abelian group. So, it turns out that there are many group objects, group schemes that are reflexive. So group objects that are affine or close to affine ones, like constant ones. They are reflexive, and in fact this yoga of this duality factor extends even to the to case of complete, for instance, algebraic groups, so which are very far from being affine, provided we look not only at home underline of groups G with values in Gm, the usual home of duality, taking the more naive duality 3, but by complementing it by the x1 factor, x1 underlined of G with values in Gm. If G is an abelian variety, this x1 factor is in fact a dual abelian variety, and we know that duality between abelian varieties of abelian schemes over a ground scheme S is again a perfect duality. And if I want, one can set up kind of a mixed setting where the homes and the x1s are tied together by R homes, PGM, having a nice biduality statement for large amount of groups. So we won't do this here because we don't have the prerequisites. And
What could you read about that?
Well, in various references. There is the group of Gabriel and de Mazur, where you will find duality for commutative groups, developed rather extensively, including its treatment for Dieudonné's theory, you see, for formal commutative groups. In one of their chapters. I mean, it's dealt with throughout. So that's, but they don't speak at all of abelian varieties. Now, for abelian varieties, is there any good reference? Probably that I would think that that Mumford's book probably on abelian varieties that was published in Tata should be a good reference. I don't know. You see, there was an extensive seminar in Orsay about abelian schemes, but unfortunately it was never written down. So I mean, things are known by the people around. You see, it's in the folklore, they know how to do things, but it's not sure things are written down as they should. So at least various pieces of this duality I'm referring to, you probably will find them in the literature. So let's say Gabriel de Mazur's book, or in this seminar of de Mazur and myself, and then about abelian varieties, I would think that probably most of it is in Mumford's book. As for putting these things together, I'm not sure even that anybody has written it up completely in a satisfactory way. One kind of knows that it can be done, and I mean that there are various statements that one could give, I mean that I could improvise right now, but I mean one would like to have some pretty nice and encompassing, and I don't think it has been worked out. But I want to give a very elementary particular case of this duality, which is Cartier duality, which plays an important role both in Dieudonné's theory of formal groups and in the duality theory of abelian varieties. And this would be the case when G is finite over S. I should perhaps make explicit the definitions, and locally free over S. So if S is a scheme, another scheme X over S is said to be finite over S. By definition, if and only if X is affine over S, we have seen what it means. Id est, X is isomorphic to the spectrum of a sheaf of algebras A, which is basically coherent as a sheaf of modules. In fact, A being isomorphic to F star of OX, where F is a projection. And if moreover this sheaf of algebras A is finite over OS It's a sheaf of modules. It's a sheaf of modules of finite type. Then we'll say that the morphism is finite. If you knew what a proper morphism is, then I could state that the morphism is finite if and only if it's proper and if the fibers are finite. But we don't know as yet what a proper morphism is. And the theorem I'm referring to is not quite trivial. That finite morphisms, as defined here, are proper and have finite fibers is about evident. The converse is not so evident. Never mind. We take this as a definition, and we will say that F is a locally free morphism. Sometimes one adds, if one feels any confusion, locally free or finite type morphism. If it is finite, and moreover, if A is locally free as a sheaf of modules. And of course of finite type, because we want the morphism to be finite. That means also, turns out that this is equivalent to saying that F is finite on the one hand, then it's flat moreover, that the sheaf of rings here is flat over the sheaf of rings there, but means also that the sheaf of modulus A is flat over OS, and that F is of finite presentation. But the trouble is that we have not defined either of finite presentation, except when everything is affine. Well, in the case that it's affine, it means that the algebra A over K, which defines X, is an algebra of finite presentation. That comes from the fact that the module is locally free of finite type if and only if it's of finite presentation and flat. All right. So this. What we want need these equivalences. What we really will need is that we're interested now in schemes over S that can be described in terms of sheaves of algebras over S that are a sheaf of modules locally free of finite type. And in Cartier duality, we will look at schemes of groups over S, that, such as the underlying scheme structure, is finite and locally free over S. In fact, we could even write down the duality theory for schemes in monoids. Why not do this? And then the group, the case when we are dealing with groups will come out immediately. In fact, I don't know of any an example of application of Cartier duality, except for groups. But I mean, it comes out formally nicely. We take monoids. So let G be a monoid over S that is locally free over S and which is commutative. All right. We'll see in due course where these assumptions will enter. And I look at its dual, the dual of G. It's the functor home underline of groups of G with values in Gm. And first of all, we will show that this functor is representable. And it's not only representable by a scheme over S, but it's representable. It will be a scheme of monoids. By the way, if you take a monoid, we better don't take Gm here, but we will take, well, how would you call it? O with multiplication, which is just a scheme of monoids also. O with multiplication. O plus, how is this sign called? Times. O times of S prime is gamma S prime OS prime, which is a ring, but where we take as monoid structure as multiplication. So the invertible elements in here are just the units in gamma S prime OS prime, so that GM appears as being the largest group subobject in O times. Alright, so dealing with monoids will replace in our duality GM by this here in due course. Of course, if G is a group, then the homomorphisms of G into O times is just the same thing as the homomorphisms of groups of G as well as in GM. That's quite clear, and therefore we get back to the previous definition. And now I say that it's representable by a scheme which is finite and locally free over S. That's the first point. Of course, this scheme will be a scheme of monoids because the function of group of monoid morphisms, homomorphisms of G into O times, is again a monoid function. Therefore, we can take d of dg, that makes a sense, and we can look at g goes to d of dg, and I claim that this here is an isomorphism. And this isomorphism is called Cartier duality, if you want, or the Cartier duality is the functor, if you want, d, and this here is the biduality theorem. And you will see that things come out very nicely. So that this functor is representable comes in fact is true whenever G is, well, you'll just see what it means. Let's look at the points of this functor as well as in some S prime. So there are group homomorphisms of, or monoid homomorphisms, I'm sorry, of G lower S prime into O times lower S prime. Now this here is the affine scheme over S prime represented by OS prime of T. If S prime wasn't affine itself, you see, with algebra K prime, it would be the scheme over K prime represented by K prime of T. Whereas here, we have the scheme over S prime corresponding to the algebra AS prime deduced from A by base change. Alright, and we give such a morphism of schemes over S prime is the same thing as to give a homomorphism of algebras like this. It's the same thing as to give a section of AS prime, and therefore the functor we are interested in can be viewed as being contained as a subfunctor, the functor which we call W of A, whose points as well as in S prime are just the sections of A lower S prime over S prime. Now we have to say what is a subfunctor. Yeah. We have to look at, so we have to describe when is a section of AS prime defining a homomorphism of algebras, when is a corresponding morphism which we have here compatible with multiplication. And I believe it's something we have already written down. Of course, now using the multiplication here in G, we have to use the co-multiplication in the algebra A goes, the algebra A, namely the map which we call, I think, pi from A into A tensor A. And this will define, after base change, a homomorphism from AS prime into AS prime tensor AS prime, homomorphism which we again will call pi, reduced by base change. Just means that G lower S prime is also a group object. Alright, and in terms of this, we see that the fact that we have a monoid morphism here, namely that it transforms units into units and which is compatible with multiplication, is expressed by the following two relations. First of all, the augmentation of, so I have a section of S prime, and a point of W of A is values in S prime, and I want to express something about this, a condition on this. First of all, is that epsilon u is equal to 1, where epsilon is the augmentation which goes from A into S, which corresponds, which is transposed to the unit section. So that expresses that this here maps unit into unit. And second, we have to express that pi of u, which is an element, which is a section of AS prime tensor AS prime, would be equal to u tensor u. So these are the two conditions. So we have to look at the functor of the functor WA defined by these equations. Now WA, because A is locally free of finite type, we've already seen is representable. WA, in fact, is the same as the vector bundle associated to HH. The dual sheaf of modules. And it's pretty clear that these equations, define a representable subfunctor whenever some subfunctor is defined by equation. But let's not insist on this in general terms about functors defined by equations. In fact, we could prove much more general representativity theorems in this connection, but which are quite trivial. A section of AS prime over S prime, namely a homomorphism of OS prime to AS prime, can be viewed as being a homomorphism of its dual into the dual of OS prime, into OS prime itself. It can be viewed as being a homomorphism of HS prime into OS prime. So we want to express an extra condition of such a homomorphism. But now recall that giving a diagonal map on A, namely giving a monad structure on G, defines an algebra structure on HH. And so here we have a homomorphism which is linear only of an algebra into OS prime, into the sheaf of rings over which it is an algebra. And you want to express an extra condition on this, and which we expressed here in terms of this pi that defines the algebra structure of HH like this, but this just means that this homomorphism is an algebra homomorphism. We have in fact already written down this interpretation. Therefore, what we get is that the functor we want to represent is a functor which we can also write hom underlined of O algebras. Of course, algebra homomorphism means compatible with units and with multiplication. So this means that it is compatible with units, and that means that it is compatible with multiplication. Hom of O algebras of HH, now, where HH or WHH if you prefer, into O itself. But this is by definition. Now we have assumed that our monoid is commutative. Alright, therefore, our algebra here, that means that our algebra here is commutative. Therefore, it defines a scheme over S, which is affine over S, which is the spectrum. And the homomorphisms, this functor of homomorphisms is just the spectrum of the sheaf of algebras. To get a point, by definition, I mean that spectrum represents which functor. To embrace prime, I associate all algebra morphisms of, if B is the algebra which we have over S, of B lower S prime into OS prime. Alright, here B is equal to HH. So what we really get is that if G is a spectrum of A, a monoid which is commutative and locally free over S, then DG is canonical isomorphic to the spectrum of HH, but using the fact on the one hand that the diagonal map for A defines the multiplication of HH so that the spectrum makes a sense, and on the other hand the multiplication of A defines the diagonal map for HH, so that the spectrum will be endowed with a composition law, and as you will suspect, that's the composition law of dg, which is evident from the geometric description of it. If g was not commutative, what would happen? After all, the function is well defined here, and the interpretation we have given of this function till now is correct, and it's even correct here. But here we take the homomorphisms of an algebra which need not be commutative into OS prime. So what should we do? We will go back to the algebra A which we have over S, and we will take the abelianized algebra A lower up, let's say, which is just the quotient of this sheaf of algebras by all commutators. xy minus yx, of course, global commutators. There need not be global sections. And of course, taking the abelianized algebra associated to given algebra commutes with any base change. So call this abelianized algebra, call this B. I'm sorry, it's abelianized algebra of HH. Call this B. Then the algebra homomorphisms of HH S prime into OS prime are just the same thing as the algebra homomorphism of BS prime into OS prime. That means that here again we get a representativity of the functor, but it is by the spectrum, not of HH, which wouldn't make a sense because HH is not commutative, but by HH made commutative, which scale is again crazy coherent. Very clear. Of course, then this move object which we obtain need not be locally free finite interval over S, because once we divide by this idea, I mean we have no control of how good or how bad this idea is. This quotient may be pretty irregular. But we had assumed that G was commutative, so no need to pass to the quotient by some idea. And we get dg in this way. What we can say also is the following. When we define modal objects over S which are affine over S in terms of sheaves of modules over OS that are endowed both with a multiplication and with a co-multiplication, delta and pi. In fact, the axioms for multiplication and multiplication are perfectly dual to each other, with the exception of one, namely, we assume that the multiplication is commutative, but not necessarily the co-multiplication. But here now we are dealing with commutative composition laws on G's, where we assume also that pi is commutative, and now the axioms for delta and pi are perfectly self-dual. And this means that this implies that if we restrict to A's for which S modulo by S by duality work completely, for which A is the dual of its own dual, let's say A locally free of finite type, that then the axioms on delta and pi, I mean, just dualize into the corresponding axioms for Z transpose in HH. And because passing from A to HH is an involution, they can be locally free sheaf of finite type over S. This implies that we get in this way an involution in the category of commutative modules over S that are locally free over S. In other words, if I take d of dg, if I apply just the same theorem, I will see that this is a spectrum of HH, which is just the spectrum of A, and of course, this multiplication, co-multiplication A being the one we started with. So this shows biduality. And at the same time, it shows that the involution which we get by homing into GM in the category of these monoids is just so obvious involution in the category corresponds when interpreting these groups in terms of algebras over S, in fact in terms of bi-algebras over S, it's just so obvious involution we get in them by passing over to dual modules and interchanging by transposing and interchanging the diagonal and codiagonal map. Is this kind of clear? Maybe I give an example or two. So take, for instance, the group mu lower n, when in fact that was already defined as d of z over nz. And therefore, its dual can turn as z over nz. So we see that the constant group scheme z over nz, which is finite and locally free over S, is dual to mu n, which no longer need be a constant group, of course. If, for instance, we have run over Z, for instance, none of these mu n's, if S is equal to the spectrum of Z, none of these mu n's, except phi n equals 1, when we have the zero groups on both sides, is a constant group over spec Z. That comes from the fact that it isn't even by taking the inverse image by taking the fibers over all the residual fields. Because if you have a residual field whose characteristic divides n, then the group you obtain is not even the geometric group you obtain over the algebraic closure of this field is not even reduced, you see. So you get something which will have unipotent elements. So we see in particular in characteristic P, let's say, any characteristic, but in particular in characteristic P, we have a duality between mu P and Z over PZ. Now Z over PZ, let's take an algebraically closed field of characteristic P, is a perfectly good finite, usual finite group, you see, of order P, whereas mu P is, as you have seen, a purely infinitesimal group, which appears here as being the dual of this, so that Z over PZ can be interpreted as the dual of this one. You see that Cartier biduality just wouldn't make any sense at all if you neglected unipotent elements. So I mean, we neglect the unipotent elements in the scheme mu P, just gets unit group whose dual is 1, not Z over PZ. So just another example, but I won't work it out here. It's that alpha P is dual to itself. But it's not true that alpha P to the n is dual to itself. Alpha P to the n is not isomorphic to the dual of alpha P to the n. I recall that alpha P was the functor which associates to every k prime the set of all lambdas in k prime whose p power is equal to 0. It's the kernel of Frobenius. And alpha P to the n, the same thing, we are adding d lambda to the p to the n. So for n different from 0 or 1, alpha P to the n is not what to do is alpha P to its own dual. But it would be a nice exercise to show that we have an autoduality here in alpha P. In fact, it's induced. Another one. It's pretty easy exercise. I won't do it now. I think that perhaps you better stop. So let's say in 10 or 15 minutes, there's going to be a little seminar on universal algebra. It's not at all needed for following the course, neither on algebraic geometry nor on algebraic.